so I can plug this in. Just waiting on a charge, or some way to charge my thing. Ah, perfect.
Use this microphone for the streaming.
Yep.
Okay.
All right, I think this works, so we can get started. Laptop is charging. Okay, perfect. So welcome to RClip day number 1. Hopefully maybe one of many. Okay, so the point of RClip day, I think, is fairly straightforward, which is that we have this big library called RClib. In fact, as I'm going to say in a second, we have 5 libraries, which we collectively refer to as RClib most of the time in an abusive language. And we're starting to have some interesting stuff in there, which I think is relevant to people who do form verification, but also people who do just protocol specifications and theory and implementations, and maybe the wider community that's here at ZKProofs. And so we had the idea that we should maybe try to have a day that's focused on this and on going over all of this in detail, since there turns out to be quite a lot of content to go through. And the context of all of this is obviously that at the EF we're trying to formally verify all of these ZK VMs, which was talked about last year at ZKProof and talked about in many other places. And for the cryptography track in particular, for that project, the idea was to be able to verify specifications, proofs of security, and implementations of the proof systems that we use in ZK VMs. And that includes, obviously, Fry, where all of those things everyone knows, and then in the long run, and I'll get back to that a bit later in this talk, obviously trying to bridge the gap from specs of single protocols to specs about the big proof systems that people actually run in production. And the core part of this track is this RClib library, which has been on GitHub now for well over a year, which was started by Kwong, and then which became a core part of the project. And now I think we have 30+ contributors on GitHub. Half of them are probably AI, and a nice group of kind of 9, 10-ish kind of core contributors. So as I said, RClib is really 5 libraries. RClib is the main one, where you have specification for snarks, and you'll find specs for things like Fry. But to actually be able to specify Fry, it turns out that you need quite a lot of things. And so we have, at this point, 3 foundational libraries. One of them is new as of yesterday. So VCV.io is probably the main one. VCVIO is where we have all the abstractions for things like oracles, which you need to do modern cryptography, and which turns out to be nailing what an oracle is and trying to specify what an oracle is to be able to support rewinding and caching and logging. And all of these features that you see in papers turns out to be fairly involved and require quite a bit of thinking. And in our case, it took a few iterations. And VCV was started by Devin, who will talk a bit about this later today. We've got Polyfun, which is a new library out of from yesterday, which is all about polynomial functors. And whether you think that fun is up to you. And interactions, because for all of these protocols, even a basic ZKProof protocol, you have two parties and you need interactions, and you need to think about how to model these interactions. So now we have one library for this, and the interaction framework, I think, is actually generic enough that it should be able to do maybe MPC, maybe distributed protocols more generally. And then we have another library again in terms of foundational stuff, which is that we have a fork of Iris Lean, where Iris is a separation logic framework that comes from the rock world, and that's been around for many, many years. And in that fork, we're trying to implement Bluebell, which is this program logic, which I guess Julian will talk a bit about in a second. And this is all to help us reason about programs in a nice way, and particularly in an ergonomic way in terms of doing proofs, so that we can actually start to do nice proofs. And then with all of this, we can actually define specs and security proofs in RClib. So there we have Fry, we have specs for all of this. We have security proofs for all of this that we're working on, and then we also have all of the mathematical prerequisites. We heard a lot about proximity gaps yesterday, and we have all of this in there. And I mean, RClib, obviously, Julian will talk a bit about the IUPPs that we have in RClib. Tobias will talk about KZGs, an example. And then Katie will talk about all of the mathematics that's in there, because most of the library at this point is basically actually coding theory. And then the other nice thing is that we then have another library called CompPoly, which has a formalization of polynomials which are computable, and where we're trying to have efficient algorithms that are implemented. And the idea there is that this allows us to turn our specs into executable specs that you can actually run. We want this for several reasons. One of these is to be able to test the specs. One of these is to be able to do differential testing against the specs without doing the full gamut of form verification. And in the end, actually, the other reason is that we might want to actually run this in production. And I'll get back to this. The idea is that obviously at the end of the day, we want to specify things, we want to prove things, we want to formalize all of these things in Lean. But the end goal is really to be able to say something about production code and say something about code that's running in production. We're looking at several different avenues for this. We're doing three in parallel. One of these is just extracting Rust code that already exists via tools like Hax or Neas, and both emerging, so the difference is a bit moot at this point. This is something that you'll hear about a bit later today with Derek's talk on CompPoly. The other things that we could do is obviously just write assembly. It turns out there's already a project writing an EVM in assembly, and we could do the same for things like verifiers and fairly small scoped programs. And then, of course, we could think about just compiling directly from Lean into a production code that's fast and efficient and formally verified. And this would most likely involve skipping Lean's runtime execution, so most likely this is going to involve just writing a compiler. There's a stand-in there, which would be MLIR, because we have MLIR re-implemented in Lean. And same for RISC-V, this is a stand-in. For a verifier, you might want this to be WASM or x86 or something else. But the end goal is to try to get RClib into production, and this is maybe something that will be touched on today, but maybe also something that we'll get back to next year as we first have to finish writing specs and making them efficient and computable, and having some prototype verification of some of these. So there's a bit more that I want to say now generally, beyond the basic architecture of what RClib looks like as a project. And one of these things is obviously that we started RClib in 2024, late 2024. And at that time, we were still doing a lot of things manually, but we thought that it was worth doing because Lean has this kind of huge ecosystem of mathematicians who contribute to MathLib. MathLib now has about 2 million lines of code, which is quite a lot, and covers, I think the tagline is that it should cover all the material you'd find in an undergrad course in mathematics, except coding theory, as it turns out. But we thought it was kind of interesting that mathematicians were contributing millions of lines of code to the Lean ecosystem, and computer scientists at that point were not contributing that much. Now there's a CSLib, which is only getting started, and there was nothing for cryptography, there was nothing for reasoning about programs. A lot of things were kind of lacking. And this was kind of strange, because obviously we're computer scientists, In many ways, snarks are actually a very interesting use case for form verification because you both have interesting mathematics, you have interesting proofs, you have million-dollar prizes for conjectures, where you might want to be able to check that something that you get out of these solutions to conjectures actually hold up. And then you also have specs, which are quite hard to reason about because you want to be able to compose specs and you want to be able to compose protocols. You want to do some arbitrary number of sum checks, for example, or you want to be able to plug in lookups for different parts, and you want to be able to build a big kind of proof system that you would have in production. And then obviously you have quite a lot to do when you want to then finally verify some actual code that runs in production. And this used to be very laborious. It used to take a long time to do. It used to take maybe many people to do. And we got started on this nonetheless. But then we were very lucky, and lucky is, well, we kind of knew the AI stuff was coming and we were very much banking on it. So thank you to the AI people for delivering. But in the past couple months in particular, we've had a lot of changes, which is that AI has become very good. AI went from, we can use it for a few things, we can try to play around with it, we can do simple proofs with it, to now we can do quite complicated proofs with it. In fact, like I guess there's not that much manual proving that's left to do in many cases. And so we've seen a lot of changes to the economics of developing all of this, and that has an impact on the speed of developing all of this. So we've seen a lot of increased automation in our work, both with AI and I think classical automation as well, better tactics in lean and things like this. But also it's made it much easier to run a library in the sense that it's much easier to trust contributors to your library when it's in lean. So we doubled, roughly speaking, our number of contributors in the last couple months. Most of them generate PRs, which I'm pretty sure are 100% AI. Actually, the replies that they give to your comments on the PRs are pretty much AI as well, as far as I can tell. But nonetheless, actually, some of the content ends up being quite good. And reviewing all of this is much easier because we can obviously trust, one, that the proofs are correct, which removes quite a bit of the review burden because we just need to check statements. And two, obviously, even when we need to check statements, because we have access to all the reference papers, thanks to all the cryptographers that write nice papers, we're able to actually kind of also use this to review PRs quite a bit, and doing the diff between a statement in lean and a statement in a paper is become much easier as well, and AIs have gotten much more trustworthy at this. So we still have some manual work to do, but all of this has gotten much better, and is also an exciting time in that sense. And what this has led is just community growth around lean in particular. So one of the very nice things is that adopting lean now is much easier. You don't need to learn, the concrete syntax on day one. You can start trying to prototype things in lean very easily and getting some intuition for how things work in lean. And this means that we've been able to leverage a lot more domain expertise, I think, over time, both in ArcLib and in other projects. In the sense that now, if you want to say you're a cryptographer and you want to do things, you can maybe just auto-formalize things. And we've seen this. There was a talk about this yesterday with Yoichi auto-formalizing the simplified round-by-round standards of Fry. At ZK Summit, obviously the Veil presentation by Ron mentioned auto-formalization. And this is kind of exciting as well, that people are able to start doing things very easily. A lot more people, therefore, excited about lean, and a lot more people are therefore excited about contributing. And this has been quite a big help to us in many ways. And I think I wanted to kind of bring this up because it means that it's also an invitation for people to come and contribute and participate without necessarily having to do, like a 6 months lean bootcamp at first, because it's now much easier to jump in and prototype and see how things work and maybe do something useful very quickly, whilst you also obviously learn things in parallel. And we've benefited from this with the lean ecosystem growing, because a lot of the problems that we have or that we thought we would have end up not being problems because someone else that we've never heard of tries to solve it and manages to solve it, and vice versa. I think we've actually had quite a few tools that might be used for other things. So some people doing AI for mathematics are excited about our computable polynomials. Signal, which is being formally verified now with the Beneficial AI Foundation, are using VCV, most likely, we hope. And so the lean ecosystem is growing and being incredibly helpful, and it's growing especially in terms of adding domain expertise from different fields and not just people who have a pure form verification background, which has been a very nice thing. In particular, so to touch back on proving with AI, since that's been quite a big deal with ArcLib, I have a picture here of when I did the proof of Polytrix Spielman in January this year, which I think was the first kind of meaningfully or interesting proof that we did in ArcLib, right around the time that the models just kind of started getting much better. This was the times of Opus 4.5 and GPT 5.3 or 5.2. And this was done with logical intelligence, and so we'll hear a bit about this as well. So logical intelligence have some people who we're very lucky are here today, and they'll talk a bit about all of the AI stuff. But this has been really nice, right? So you can take Polish-Spielman, suddenly proving it by hand the first time for humans, I'm going to say, took a bit of time. It's a valuable kind of contribution, and it was part of a PhD in the 90s, and then obviously the proof there was broken, and then Ben Sasson and his co-authors had to fix it in the proximity gas paper. And then I could just come along, write down an outline of the proof, write down some hints you can kind of vaguely see there on the screen that I did myself, and then I could give it off to the AI, and then the AI could do it. And this took about 8 hours and $200 worth of compute, which is roughly an hour of industry contractor time within those bounds. And so something that would have taken certainly more than 8 hours to maybe formalize by a human expert now is much, much easier to do. And so we're able to kind of really scale things. And one of the nice things is that this means that if you look at papers that come out now, and you look at what we have in ROOM3, and we have all of the foundational coding theory and things like this, and someone adds maybe one more theorem, stating it and being sure that the statement is correct is maybe not too much trouble, right? It can be just one statement, maybe 2, maybe 3, very tractable. And then proving these, especially if we have access reference proofs, becomes much nicer. You offload it to the AI, you obviously have the pen and paper proof to get some intuition and some sense of how the proof works, and obviously for your own understanding, which is still important. But you can quickly kind of get this added into your library and iterate very quickly. And this means that if new cryptography comes up, then hopefully we won't actually lag behind, which has traditionally been an issue for formal verification. So this is one of these very exciting things. But then obviously it comes with a big caveat, which is that for proofs it works very well because the lean kernel gives you some assurance about the proofs. For specs it doesn't work that well because it's very easy to have specs that are slightly off. And so there needs to be a bit of a slight warning sign here. Because we've seen obviously some things not go well when we've tried to use AIs for some things. I think Kwong in particular will talk maybe a bit later today about some examples of this recently, that in some ways you can maybe generate a categorical model of the UC model, and that kind of works out, and some other things that should be maybe simpler don't work out at all. So there's still quite a bit of care that needs to be taken about anything that isn't actually checked by the lean kernel. And this is also a bit of a maybe a bit something to take into account with auto-formalization, that some of the auto-formalizations we've seen have proximity generators which are axioms, oracles which are vectors of n elements, and things like this which are maybe fine for specific use cases, but maybe not general enough, and maybe certainly not capturing the abstractions that you have in the cryptography literature in the right way. And so we kind of want to take care of maybe highlighting this and not being kind of too overexcited about the AI stuff in general, even if there are things where obviously it's just solves an entire class of problems. The other things to say about specs is obviously that specs can be kind of tricky to get right, because for cryptography, the specs are quite live. So with Fry in particular, Fry has been around for nearly 10 years now, since the original paper. And it's gone through many changes in terms of how people implement it, in terms of the fields that it works on, but also in terms of the protocol itself. There's been a lot of optimizations and different ways of thinking about it, and implementations have evolved quite a bit. And so if you want to write specs that actually map to implementations and map to the kind of modern understanding, you can't just stick to the papers. And that turned out to be an interesting thing for Fry, which we had to go and do things in a slightly different way. We had to make it fit with the interactive oracle reduction framework that we have in ROOM3. We had to go and talk to cryptographers to validate this. I think Albert Carretta played quite a big role in validating that we weren't doing something stupid. And so that's another part of doing specs, which is you have to do specs in a way that is kind of smart, both for the use case for your specs, whether that's verification, whether that's just doing security proofs, whether that's something else, and in the way that you obviously validate your specs and then try to get good proof ergonomics to prove things against your spec. And I guess that'll be somewhat part of Julian's talk later in this session. The other thing that you need to remember is to try to keep track of everything. Dara is not in the room, but she would otherwise recognize this this slide. So this was an attempt that we had at HAX earlier this year to try and understand everything that would need to be verified to actually get an end-to-end proof for something ZK. We split 8 people into 2 groups of 4. And then we did it in parallel. The first thing you'll notice is that both things do not look the same. And so if you stick 2 groups of 4 people, they won't actually do the exact same thing, at least in terms of the organization. The other thing that is harder to notice on the slide, because the slide is unreadable, and that's somewhat part of the point, is that in actually both of them have things that are missing. So both of these things don't overlap entirely. Both of these have things that the other group forgot to do. Now, we were bounded by time, obviously, when we did this. But it's still an interesting point that obviously is quite hard to still come up with the entire list of things that you need to check. Now, some of this goes beyond the bounds of RClib. You have things like the guest program, the application protocol, and things like this, a part of this sketch. But obviously, at some point, you do want to connect things, right? And so we'll also hear about front ends for that reason today at RClib Day, and then part of the work in the coming year will be trying to connect these front ends to RClib and to have a proper front end and back end integrated system where we can actually do think about doing end-to-end proofs and try to grow the scope of what we verify as a whole, and rather than having everything be separated and isolated from everything else. So this is, I mean, this was quite a fun exercise, and then I've used it ever since on slides, and we've definitely found that the scale at which you need to verify things, even for a proof system, let alone an implementation, is quite big. The reason for this is, as I said before, the proof systems that we see now in practice are much more complicated than just one protocol. But also because at the scale at which RClib is, I think, which has probably in the hundreds of thousands of lines of code at this point, I would say, you have a lot of specs of code. Given 1,000 lines of code, you typically expect bugs. I think the measurements are usually that you have between 1 and 50 bugs per thousands of lines of code whenever someone's tried to measure this, regardless of the language. And one bug in 1,000 lines of code is considered kind of, whatever, top tier NSA military, high assurance grade or whatever. And so if we have pushing 100,000 lines of mathematics and specs, it's very likely that there are at least some statements there which are slightly off. We do find statements which are slightly off every time. Actually, Polish experiment, we got it wrong twice. So that's another thing to try to keep track of, which is that we still need to obviously validate that the statements that we prove are the correct statements, that the specs that we have model the correct protocol that we think it's modeling, and that we actually can check what we have. And that's another thing to obviously take care of, especially if we start using AI to write more specs, is keeping track of what we're actually doing, and keeping track to just doing what we actually need to do to verify what's in production, if that's the end goal, and not just have things that we can say are proven in Lean, which might not actually be that relevant or interesting, or be slightly off. And we've seen obviously errors of formally verified code, or claims of formally verified code, which turn out not to hold, because the spec against which something is formally verified actually has some things that it's not checking. So that's the main last point that I wanted to bring up, and that I think we'll keep in mind during the day. And then, so that's the schedule for today. Yeah.
Do you keep track of that anywhere else than this slide? Is there an outcome of that work that's captured elsewhere?
I mean, we do reviews in RClib.
But this graph that you're presenting?
Oh, no, this is just for the...
There's no mega map that came out of it?
No, because none of these turned out to be good enough to be final. I think one of them forgot Fiat Jamais, which is a bad one to forget. And then I think the other one forgot, I can't remember. But I mean, so one of the interesting things about this as well is you'll notice this for, one is that soundness is much easier. I think that's an interesting point. Soundness is much easier than completeness, in the sense that completeness, you need to verify far more things, because soundness has a kind of adversarial thing built into it, which is that the honest verifier, has to be resilient against, like a malicious prover. And a malicious prover could be like a prover with a buggy compiler or whatever. So soundness is kind of okay. And then completeness is really hard, because completeness, you have like 4 different, in a ZKVM, you have 4 different compilers. You compile the guest program, you compile the constraints, you compile the witness generation, you compile the verifier, you compile the prover. Some of these compilers are the same, but you have probably at least 4 compilers, if not more. And so that's part of the stack being huge. And that's part of the trust in code base. Even if you verify like your protocol, and you verify that the verifier is the right thing, if the compiler fucks you up, then that's it. I don't know if I'm allowed to swear on the stream. But yeah, the slide shows many things, and it's actually not complete. And like I said, one of the interesting things was that both don't show the exact same thing, suddenly not in the same ordering, and suddenly not with the same connections between the components. And then you have all the interfaces for precompiles and things like this, which right now are not like entirely specified. And so the range of things that you actually need to check to get an end-to-end proof of like this implementation of this very complicated protocols with some checks and WIR and log up GKRs and other things is pretty tough. And then you obviously need to connect that to the arithmetization and whatever thing is being arithmetized and the witness generation and all of this. And so one day maybe we'll have a complete outline. But obviously, so far we don't. And some parts as well, we don't know what to do, right? So recursion is, we need the cryptographers to also help figure that one out. So recursion, not entirely sure what exactly is the notions that we want to formalize to be confident about our formalization recursion and be confident about formally verifying some recursive proof system. And so that's, there's still many to-dos and still quite a bit of things to go through. But we'll start obviously at least discussing many of the things that we want to go through with today. And so we'll have a fairly simple schedule, which is that we'll look at some examples of protocol specifications. We'll start with KZG. Tobias actually presented his KZG formalization Isabel last year, ZKProofs. And so this year he's talking about KZG and Lean, joining the winning side. And then we'll have a slightly longer talk, obviously, reasoning about IOPPs. And so Julian there has worked on Fry and WIR and ArcLib and trying to specify them and trying to work on program logics to reason about all of these things. And so we'll see a bit about this. After that, we'll have, I guess, a coffee break, and then we'll have a bit more about the foundations of ArcLib to maybe get a better understanding of how the IOPP specs work. So the one main thing here is VCV IO. The paper for VCV arrived on preprint today at 6 a.m. So that's, you can look at the talk and then you can look at the paper. But there are interesting things there. So, it turns out that oracles are the free monad over the polynomial functor. Devin, I guess, will explain that in more detail. Devin is shrugging. But it's self-explanatory, yeah. Your Turing machine tape pauses to do the oracle query. That's an algebraic effect. That's all it is. But it turns out that specifying oracles is not easy, right? Once you want to do like things properly and you want to think, okay, cryptographers want these features out of oracles. They want things like rewinding is a pretty cool thing to have. Then you need to have oracles which are not just like a vector of answers to queries or something like this. You need to try to model things properly. And that turned out to be quite a long effort. It took several iterations, and that's something that you won't get from auto-formalization, because if you try to auto-formalize a single paper, you're going to get your paper, you give it to your AI, it's going to take the theorem statements that are in the paper, and it's going to write something down that seems plausible, but obviously it's not going to one-shot a formalization of oracles in all their complexity, because that's not described in the papers, it's just assumed. And same for more broadly, like the interactive oracle reduction framework that ArcLib is based on to specify protocols isn't something that's described in a paper somewhere. It's something that had to be done independently by Kwong and Devin, and took quite a bit of work, and has some novelty to it. So we're not actually just taking cryptography off the shelf, rewriting it in Lean. There's a bit of thought that actually has to go into how to do this properly, and that's also, I think, part of the point of these kind of foundation sessions is to try to understand this a bit better and to try to maybe also communicate the work and maybe some of the limitations of not doing this and not being able to model what cryptographers exactly want, and then potentially having gaps that come back to bite us in the end. So we'll hear about VCV. We'll hear about computable polynomials from Derek, which is the COM-poly library. There was joint work between ZK Security with Gregor, and obviously Nethermind with Julian and his colleagues, and then Derek more recently when he joined EF, where they were trying to have efficient field arithmetic in the end, and we're doing things like efficient decoding algorithms, and generally speaking, kind of any FFTs, NTTs, and all the computational stuff that you want to be somewhat efficient and fast, both so that we can actually verify what people are doing in production, but in the end also that we can think about making this fast enough to be in production. And then we'll hear about mathematical foundations. I guess this will be a good complement to some of the proximity gap stuff that was discussed yesterday, if you want to see how this ends up looking in Lean. And in particular, there'll be a mention of the the paper that's presented right after lunch in another room on polynomial generators that we're doing in parallel to them presenting it, or presenting it before them and formalizing it, at least started formalizing it before the paper ever got presented, which is kind of nice. Then we'll do front ends after lunch. There were several teams which have been building front end DSLs in Lean. This should be fairly self-explanatory. Circuits, we all know circuits. They're great. They're full of bugs. We should try to clean them up. No pun intended. And at least that kind of goes some way between bridging RClib to concrete things as well. And then the last session we'll have will just be first a talk by Kwong on evolving foundations of RClib. Kwong unfortunately couldn't be here today. He'll be remote, but he's been doing a lot of exciting work in the recent couple of weeks after Layer 0 freed him from optimizing all of their Rust code. And then we'll obviously finish off with some improving with AI, since, like I said, we've been using logical intelligence tools quite a bit to get a lot of proofs, certainly I have, and so that way I think it felt like a good time to actually have a discussion and a presentation of people who actually work on these tools to help us all understand it better. I think that's basically it for today. I tried to keep it short enough so that we can do the changeover and not run too late with the other talks, but I think we have maybe a bit of time for questions, and then we can do the switch over in parallel. Oh yeah, that's fine. Out of moment of doubt. Perfect. I'll get his slides. And so that way, because you have quite a bit of slides, so you might need a bit more time.
Yeah, I don't know. I switched slides quite fast. So how does this work? It's just like. Yeah, hello. My name is Tobias. I'm a master's student at TUM, and yeah, like Alex said, I worked on KZG before in Isabel, but now switched to Lean, and it seems like this talk is gonna be more a bit about functional commitments than KZG, but I assume most of you know KZG, so I hope that's fine. Let's get right into it. First of all, what do I mean by functional commitments? I mean the definition introduced in this lovely paper titled On the PHP Security of Succinct Arguments from Functional Commitments by Chiesa, Guan, Knabenhans, and Yu. And I want to mention Christian Knabenhans in particular, who's been my advisor for this work. So yeah, thank you to him. And what they do in this work is they introduce functional commitments as a generalization over polynomial commitments, vector commitments, linear function commitments, and so on and so forth. And how it works is you have in a functional commitment scheme an abstract query class which you can essentially instantiate to obtain a PCS or a vector commitment scheme and so on and so forth. Since this is RClib Day, let's jump into the definition RClib. It's really straightforward. A functional commitment scheme is made up out of three components: a keygen function, a commit function, and an opening. And the opening is really where the interesting stuff happens. Keygen, commit are just your typical functions as you know them. First of all, it's an interactive protocol. So we have a protocol spec which you can use to describe how many rounds, what messages to send, and so on and so forth. And then, of course, with this interactive protocol, we want to prove that our query and our response are consistent with some commitment. And this is where the query class stuff comes in, right? You can see the query and response types, they are dependent on some Oracle interface. This is really just a query class. And it does a bit more than give you just the query and response types. It also gives you essentially a way how to answer queries. So here's the query class for prime field polynomials, which we use for the KZG. And as you can see, it's fairly simple. query type is a prime field element, we answer prime field element queries with, again, a prime field element, namely by evaluating a polynomial, right? Pretty straightforward. So now, the main property of functional commitments is function binding, right? And I stole this graphic from Kristen's talk from last year, and as you can see, what it says is that function binding on a spectrum from evaluation binding to extractability lies somewhere in between. Intuitively, what it says is, if you, again, imagine these query and response pairs as being part of a kind of a relation, for example, the relation of valid evaluations of polynomials, then what function binding says is that no adversary can create values that are divergent from this relation, but still accepted by the verifier. So maybe you ask yourself now, okay, but why function binding if we have extractability and need that for our favorite soundness properties, for our favorite snarks? And that is a result from the paper mentioned earlier. Actually, you don't need extractability. Function binding suffices to, for example, prove your favorite soundness property about your favorite Planck snark or whatever. Yeah, and now we want to prove, oh no, sorry. Yeah, of course, since it's RClip Day, the definition of function binding in RClip might look a bit confusing at first, but trust me, it's really simple. Yeah, I know it's a lot of boilerplate. I'm sorry, but yeah. First thing, of course, we have to generate the value. So we go in with a keygen, then we let the adversary run to give us the commitment, the query, and the response, and then we let the interaction run to essentially get the verifier value. So if he accepts or not, and then we go on and check that, of course, that the verifier accepted all the values and that, in fact, there exists no underlying data that would have created these query response pairs honestly. So essentially the relation check. Right. So now we want to prove function binding for the KZG. And concretely, we want to reduce function binding to the RSTH assumption in the standard model. It turns out this proof is not entirely straightforward. There are firstly multiple cases, and one case in particular is a bit difficult. So given this and the fact that RClip is still evolving, as is VCVIO, we try to come up with a proof that is, or like a approach that is as stable to changes as possible. And for that, we came up with a somewhat more general approach that formalized proofs like this. And yeah, I think most of us know this, right? Most paper proofs, they follow this paradigm of assume an adversary is successful, then we can use this adversary to break some hardness assumption, right? And most often what they show, or what they mean, or what they show is that assuming the game conditions on the left-hand side of the game, right, that they have a reduction that somehow turns this game value, so the right-hand side of the game, right, into something that breaks some hardness assumption. So if you think about it, this is something very much acting like an implication. Oh, sorry, I forgot to switch that. Oh. Yeah. And now in RClip, we have this nice monotonicity lemma, which essentially relates an implication on the game condition sides to the complete game probability. And now I think you kind of seen where I'm going with this, right? So essentially the idea is to, if it's possible, try to take this paper-proof reduction map and somehow express it into such an implication statement, which you can then use the monotonicity lemma on to end up with a result like the one in blue above. And it turns out if you have this implication statement, there's a relatively simple proof plan which you can use to essentially get this blue statement above. Right. And now I know what you're thinking. Not all proofs are structured like this. You cannot always express them as implications, and you're right, of course. But still, I think there's a decent amount of proofs for which this is possible, especially for proofs like the ones for non-interactive functional commitments. And really, I think that this is the way to go for these proofs because of 2 or maybe 3 reasons. Firstly, with this whole implication structure, you're typically able to go pretty close to the actual paper proofs just because you have this whole assume adversary is successful and assume the left-hand side of the implication thing, right? And then secondly, at least from my experience, it turns out that AI formalization tools are way better at doing proofs in this very mathematical implication regime than doing game hops where you have monads and reasoning about state of oracles and all that. And then thirdly, you really minimize the breakage area. If RClip or VCVIO or something like that gets refactored, you usually don't have to refactor much of the implication statement. It's almost abstracting the real reduction from the game hops. So yeah, I don't want to show you the whole implication statement because that is maybe a bit difficult. But what I can show you is the execution of the proof plan for the function binding for the KZG, and that is really kind of simple. We start, of course, with applying the monotonicity lemma. So we start out with the function binding game and the function binding condition, and show via the implication that the RCH condition with a reduction map is implied, right? And then we drag this reduction from the left-hand side, so from the game condition level to the game level. Sorry, from left-hand side to right-hand side, right? And then we just go in and reorder this reduction applied to the game level, on the game level into the RCH game played by a reduction adversary, which essentially simulates the function binding game. And then as a last resort, we just say, okay, since this is an RCH game played, the probability of this being 1 is less than or equal to the RCH error. Okay, in all reality, we had to do one more game hop in the beginning, but this is just because the reduction from function binding to RCH condition needs a bit more values than the function binding condition. So that is one extra step you might have to take, but other than that, it's fairly simple. That's the point. Right, now I don't know how good am I on time. Pretty perfect. Then I can finally talk a bit about KZG. What I didn't show you last year in my Isabel talk was the KZG definition, and that was because honestly it wasn't that great. There were a lot of things I had to define prior to defining it, and this is different in Lean, right? If you take a look at this, all functions virtually, except for the Tower of Exponents function in the generate SRS, are already existent functions that could be used either from computable polynomials or from mathlib or from Lean standard library. So this definition to make is fairly straightforward because of the algebraic nature of the KZG, I guess. Now, I know the KZG is not the most complex polynomial commitment scheme or functional commitment scheme, but I would invite you to try to just write down your favorite, maybe a bit algebraic functional commitment scheme and see how far you can come. Because, like I said, with all this math development in Lean, I think there's really a good foundation for that. So, I think that is everything I wanted to tell you today. So, thank you very much. I'm happy to talk everything about RClip and functional commitment scheme. So, please come talk to me. Thank you.
Do you want to switch over, Julian, if you want to switch machines? And then whilst Julian faffs about with his laptop, if there's any questions for Tobias, we have probably a few minutes.
Nope. Thank you.
I mean, it's not a question. I just want to say it's pretty cool because this, how did you call it, function binding property of KCG is exactly equivalent to what we called code binding when we analyzed DAS. So essentially, you formally verified proof for PIDAs. It's pretty cool.
Benedict, what's the plan for post-quantum PIDAs? Post-quantum PIDAs.
Ongoing discussion. So current plan is encode using any code you want, and then put it in a Merkle tree, and then prove using a slam.
Oh, seems fine.
Done that collectively.
We have Merkle trees. Good.
Yeah, I'm ready to go.
All right, so next speaker is Julian from Netherminds. He's going to tell us something about reasoning about IOPPs in Lean, and I think has some, will open VS Code
At some point. Yes, yeah. Cool. Thank you for the intro. Yeah, so the first thing I'll say is that there hasn't really been coordination between people talking today. So I already have a little bit of overlap with people before me, and no doubt there'll be some overlap with the people after me. Repetition is good, there you go. So, but yeah, I'm going to start off a little bit by giving sort of like an overview of what the motivation of RClib is, which to some extent Alex has already done. But essentially, we're adding these ZKVMs to the Ethereum trust base because of the L1 proving transition. And so we're putting, a huge amount of money, apparently $56 billion at risk, and depending on this for its security, essentially. And the goal of RClib is to provide a general basis for developing formally verified ZK protocols. And as Alex pointed out, to do this, we need like a bunch of different things, right? And so obviously we're going to be formalizing a bunch of IOPs. Some of these I'm going to be talking about a bit about today. We also obviously will want to formally be able to formally prove their security properties. We'll want to be able to formally prove the correctness of the transform, the Fiat-Shamir transform / BCS transform, to convert these into actual SNOCs. And we actually want to be able to meaningfully compose these and relate them to actual real-world implementations. And so I'm also going to talk a little bit about that at a high level. So yeah, this is the overview of the talk. I'm going to start off with some background, which will be extremely boring for everyone because I'm sure that like everyone has seen the definition of an IOP and an IOR about 30 times by now. But anyways, we're going to go over that again. But we will be melding in the lean as we go along. So hopefully that will make it a little bit more interesting. And then we'll go over some basic prerequisites, some background required for Fry. We'll be then looking actually at, we'll be giving a quick overview of Fry and some of the generalizations that, well, I actually didn't even know about when we started this project, and I learned thanks to Ulrich and Nico and all of these people who very kindly gave their time to help, teach me a bit more about these. We'll then actually look at the formalization itself. We'll talk about Bluebell 2, which is part of this last bullet point from the previous slide, which is a probabilistic program logic that will allow us to sort of reason modularly and at scale about the probabilistic computations underlying all of these things, as well as allowing us to compose them effectively. And then I'll also talk a bit about the ongoing work on formalizing Stern-Wer, and then as well as future ongoing work by many of my amazing people I'm working with in the audience. So yeah, really excited to be working on this. But yeah, okay. With that, let's jump in. So yes. As everyone knows, an IP/IOP is a two-party protocol. You have a prover and you have a verifier. There's some notion of statement, some notion of witness. So these are types or sets, and you have some relation between them. And in particular, the prover wants to convince the verifier that it knows a witness satisfying a given statement without necessarily revealing this. And in particular, obviously, the key property we really care about in the context of L1 proving is succinctness. So this is the standard diagram you've all also seen n times, where you have the prover sending a commitment to the verifier, and then you have this challenge response exchange. Of course, this is fairly standard, but there are a bunch of protocols that use different interaction schemes, essentially. And as Tobias mentioned very briefly, there are these, we have a way in RClib to actually be able to specify arbitrary interaction schemes here. And the idea then is at the end, the verifier has some transcript verifier that either accepts, can see this whole transcript and then either accepts or rejects it. And in particular, as we note at the bottom, the challenges which are returned by the verifier are typically uniformly distributed in some type. And the difference between an interactive protocol and an interactive oracle protocol is the messages sent between the prover and the verifier can be oracles rather than just like a plain text, if you will, representation of the information. So yeah, so we start off with a little bit of lean, and we have this protocol spec that I think Tobias looked at very briefly, right? Which define basically it's a type that takes as an argument some natural number, which is a number of steps of interaction of the protocol, and we have this direction function that for each step of the protocol tells you whether the message is going from the prover to the verifier or the verifier to the prover, and we have a type function which for each step of the function of the protocol gives you the type of the thing being exchanged, right? So that can be a polynomial, that can be an oracle, that can be really whatever you want, right? So, and then, now that we've had a very quick look at IOPs, as no doubt most of the audience knows, there is this generalization, this relaxation of the notion of an IOP that in particular allows us to actually decompose these things and then in terms of these interactive oracle reductions, and then be able to recompose the protocol in terms by well, putting the sequencing these things essentially, right? And so the way that we sort of generalize this is rather than having at the end the verifier having this sort of like function that checks the transcript, instead the prover and the verifier in some sense output a new statement and a new witness, which will have a new relationship that we want to prove between them. And in particular, you know, we want to be able to prove that if the original relation holds between the original statement and witness, then the relation after this will hold between the new statement and the new witness. And of course, the converse, which is that if if it doesn't, then it will only hold between the new statement and witness with sort of very small, with negligible probability. Yes, and so essentially, obviously, these are quite important in terms of being able to allow us to define these protocols as a bunch of rounds, essentially, which we can then compose, so we can reuse the rounds that we've written in a bunch of different contexts, right? And we'll see a little bit about that a bit later on. But we define these as follows. So we have an oracle reduction which takes a bunch of arguments, which we'll sort of look into. So the first thing that you guys will recognize is, of course, the protocol spec, which tells you the interaction between the prover and the verifier, which we can see here, right? We also obviously have as we said in the context of an IOR, we have a statement and a witness at the beginning, and we have a statement and witness at the end, right? So we have a statement in, a statement out, and a witness in and a witness out. And because we're in the context of an IOR, an interactive oracle reduction, we also have this oracle statement in and this oracle statement out, which is parameterized by some indexing type that allows us essentially to have multiple oracles, as a TLDR there. And so, yeah, so obviously these are then composed of a prover and a verifier, which have the same protocol spec. You'll notice, of course, that the verifier, in contrast to the prover, is not parameterized by the witness, right, for the obvious reasons. And then these oracle provers and oracle verifiers, I actually don't give the exact definition of them, but essentially the oracle prover and oracle verifier is then defined in terms of a prover and a verifier, where the new statement in and statement out is basically just the sort of the product of the statement in and the oracle statement in some sense, right? And so then I mean, let's go for the verifier first, which is the very easy one. So it has this obviously it takes the protocol spec, the type of the statement in and the statement out, and essentially what it does is it takes a statement in, it takes the full transcript, and it does a computation in the option T monad, which also, well, with the option T on top of the oracle monad, which allows it to do probabilistic computations with respect to this oracle spec. So it can, for example, draw randomness or these sorts of things if necessary, right? And it returns a statement out, essentially, but of course can fail, right? So that the verifier is straightforward, and the prover is a little bit more complicated, but essentially it's made up of a bunch of things. There's prover state n. Basically, the prover state can, between all of the all of the rounds of interaction, can change over time. So we have basically this prover state is basically a map from a fin n to a type, which tells you, hey, this is the type between step 0 and 1, 1 and 2, etc. You have a prover input, which actually allows you to cast the statement, which is a computation that allows you to, from the statement in and witness in, produce the sort of initial state that the computation runs in. We have the prover round, which basically gives you, for each round of the protocol, allows the prover to know how to what to do when it receives a message or when it needs to send a message, essentially, right? And obviously, the reason that you don't have all of this complexity in the verifier case is actually the verifier only ever, we have some type that it has to return in one step of interaction, but it's just uniformly distributed. So we don't need any implementation there. We just need some notion of an Oracle interface that allows us to sort of like uniformly, randomly draw from this type, right, and return this to the prover. And then finally, we have the prove output that does the obvious, which is from the final state, which is this private state fin lost n, allows you to generate the statement out and the witness out, right? So these are this is the formalization of an IOR in Lean, which is due to, well, Kwong and Devon and a bunch of other people in the audience. And the goal, obviously, in RClib, it will be to use this basic, one of the goals, sorry, in RClib will be to build this definition, use these definitions to build various IOPs, including IOPPs. All right. Perfect. So then, of course, as we mentioned earlier, we're going to want to be able to prove the security properties on these interactive Oracle reductions. The standard ones here that you'll all be familiar with are completeness, right? Which just says that, hey, if I know for a given statement, I know a witness that actually satisfies the relation, then the honest prover will convince an honest verifier with all but probability epsilon c, the completeness error, right? And obviously we call perfect, when epsilon c is 0, we call the protocol perfectly complete. Which typically in these contexts we want because, well, liveness is important, basically. And then we have soundness, which basically says, well, if some statement is not in the language of the protocol, i.e., there doesn't exist a witness that for which the relation is satisfied for that given statement, then essentially a malicious prover will only be able to convince an honest verifier with negligible probability, which we call the soundness error, epsilon sub s. These were meant to be subscripts. Sorry, I just realized that didn't render, but anyway, not really important right now. And then we have the sort of like other properties, which we're not going to look at too carefully, but obviously members of the audience will be quite familiar with them, which is knowledge soundness. It's a little bit more complicated to specify because you need to be able to write down an extractor. So the assertion was a bit longer, so I skipped writing it down. But yeah, you guys know what we're talking about here. And similarly for the zero knowledge property. Cool. So let's actually look at how these are formalized in Lean. So we have the completeness, right, which is not too complicated. I mean, at least relative to some of the very large monadic things that have already been shown today. So yeah, but all that the completeness says is that basically if we have for all statements in and witnesses in, if it satisfies this relation, then essentially if we run, so this is the reduction, sorry, I should have gotten a laser pointer, that would have been good. But we have obviously as input with the relationship, the relation in, the relation out, so the relation that has to hold before and after. We have the interactive, well, the reduction itself, and we have the completeness errors as inputs to this predicate, essentially. And it basically says, well, as we said, for any statement in and witness in that satisfy the input relation, if we run the reduction using that statement in and that witness in, it will produce a statement out and a witness out that satisfy the output relation, as we can see here, with probability 1 minus the completeness error, right? And here we have the definition of perfect completeness, where it's just completeness, but you'll notice that the completeness error is 0, right? Straightforward. Perfect. Soundness formalized. Okay. So this is yeah, a little bit more interesting. So we take obviously as inputs the input language and the output language. So these are the set of statements for which there exists a valid witness, right? As I'm sure most of the audience will no doubt be aware. And we take the verifier once again because it's a proper. Well, no, not once again. The soundness is a property only of the verifier. And so here we only take the verifiers as input, and we have some soundness error, which is a non-negative, a real number. And all that this says is essentially for any witness, so for any input witness, essentially, if we have an arbitrary prover, which can be a malicious prover or an honest prover, but essentially if the statement in is not in the language, so there is no valid witness for it, right? Then it's the case that if we run if we run a reduction where we're essentially here, what we're doing in this reduction, we've just combined this arbitrary prover and the verifier that we have as input here. So if we combine these into a reduction and we run it with the statement in, then essentially it will only accept with probability less than the soundness error, essentially, right? Tell me. Well, I mean, it's what do you call it? I mean, it's the reduction sort of require it. But yes, you're completely right. That actually, it might be nice. So the answer is the type theory, which is not a very satisfying answer, right? But you're completely right. That actually it might be because in particular here we're in some sense not modeling the fact that essentially the prover in this context is a malicious prover and so has no witness, right? However, it is the case that this witness in that we have, it's an arbitrary witness in, and because the statement in is not in the language, it's not going to be a witness that is actually going to satisfy the that is going to be in the relation for the statement. Yeah, that's what I mean by it's the type theory. It's just like the run function needs to take a witness in.
You could have defined like a malicious prover type.
Yes, yeah, 100%, 100%. So that might be a slightly cleaner way, but this is definitely equivalent, right? In the sense that we know for sure that the witness is not a valid witness, and so this has to be a malicious prover in some sense, right? It just doesn't have information to be an honest prover. So yeah, this is fine, but yeah, I agree with you that it looks a bit funny when you know the sort of like standard definition, like why is there a witness here? It's a bit weird. But yeah, maybe there's a slightly cleaner way of defining this, but at least like this, we define this in a sort of unified. I'm not sure. I'll have a think about that. But yeah, definitely some good feedback for Kwong if he's watching. So. Probably, yes, yeah, fair point. So, okay, cool. And now I'm going to talk a little bit about before we actually jump into talking about the IOPPs. I know this talk is meant to be about IOPPs, and we're about 25 minutes in, and I've hardly mentioned IOPPs. I promise we're getting there. But I'm going to talk a tiny bit about the other ingredients. Oh, yes, sorry, go ahead, Ryuichi. Mm-hmm. That's a very good question. So for the moment, we haven't built any complexity reasoning into this, right? Which is obviously an issue, right? In the sense that a lot of the cryptographic assumptions are, in a sense, without the complexity part of the statement are actually false, right? Like, yeah, I mean, hashes do typically have like multiple things that go to the same. So this is definitely an issue. However, obviously, there's all of the CSLib stuff that's happening, and yes, yeah. So there are lots of efforts going in this direction. But we're not quite there yet. By the way, I noticed I should probably be handing, because then this won't, like the microphone to people when they're saying things, because otherwise this won't come out on the stream, right? Or do we have a second microphone? I don't know. No? Okay, fine.
Another thing is somewhat related to clarification. You mentioned the negligible probability, but it's not the 1 divided by any polynomial of security parameter thing. It's just some small concrete number usually.
I mean, yeah.
It's in VCV.
Yeah.
But the other thing as well, so
Yes.
And so the complexity stuff is what we've been able to like do without. It's mainly for Fiat Chame, we want the time M stuff.
Yeah, exactly. Right. So I mean, most of the things that we formalized for the moment are just hash-based schemes, whereas Alex said, you know, the definitions and the security properties are entirely information theoretic. So I'm just repeating this so people can hear on the stream. So cool. Okay, yes, yeah, sorry. So we were talking about the other ingredients that go into this. So obviously, we've been talking about IOPs mostly, and to be able to actually compile this to real-world protocols, like non-interactive protocols, SNOCs, we'll want the Fiat Chame / BCS transform. So there's already, what do you call it, a formalization of Fiat Chame. Actually, what state is that in? In progress. Okay, so there's an in-progress implementation. Yeah, exactly. So the Fiat Chame is in progress. Obviously, we want to be able to prove the soundness of that, and that's actually where the probabilistic program logic is going to come in, so which we're going to talk about a little bit later. The BCS transform we'll obviously want to also implement in the future, because, well, generally, obviously, here we've Fry is an IOP, and most of the things we're going to be talking about are IOPs, so we're going to need the BCS transform to handle that. We obviously need some, because we've been talking, as Alex said, primarily about these, what do you call it, IOPs, IOPs today that rely on information theoretic results. So obviously there's all of this coding theory, all of these coding theory results that Katie will be talking about later today. So talking about Reed-Solomon codes, correlated agreement results, etc., etc. There's also which Derek will be talking about. Ah, there you go. There's Derek. So Derek will be talking about later the efforts towards, well, particularly computable polynomials, but generally there'll be an effort towards having computable algebra operations. There might be some stuff on elliptic curves in the future, etc. And there, the idea is that actually we want these models to be computable, so that theoretically, I mean, two things: we can do differential testing / fuzz testing against these formal models. And also potentially, if the performance is good enough, actually run these in production, right? So there's that. And then, as I mentioned earlier, we will have this probabilistic program logic, which will allow us to reason about some of the more complex things here, where the things that will be happening here, particularly the Fiat Chame transform, BCS transform, that requires sort of complex modular reasoning about a bunch of sources of independently distributed entropy, essentially, right? And we'll be talking about that a little bit. And then, as Alex mentioned earlier, there's also all of this formalization of the MLIR, because we're hoping to eventually be able to to write in an appropriate MLIR dialect high performance implementations of the provers, verifiers, all of the elements of these protocols, prove simulation results with the high-level models that we've been talking about today, so that we then know that these implementations have all of the key security properties that we want, and then compile these through the LLVM pipeline to then get sort of like Sorry? Okay, well, or compile them apparently straight to the GPU. I'm not following perhaps as closely as I should, apparently, the developments on the MLIR / LLVM, formally verified LLVM pipeline developments. But yeah, essentially, yeah, the idea is there to be able to actually have binaries that are generated that are formally verified end-to-end. This is the ultimate goal of this project, right? And yeah, ... there are many more things, as I mentioned, elliptic curve stuff in the future, all sorts of things all sorts of automations, more IOPs that people are working on. Chung is working on Binius. Kwong is working on... Oh, Binius is done? Okay, Binius is done. My bad. Okay, there you go. Nice. My bad. Some check. Kwong is working on potentially done. I think that one isn't done, actually, right?
Actually, Spartan is pretty much done.
Okay, so Spartan is pretty much. Oh, there you go. Okay, fair enough. As of this morning, I only checked in the main branch, in my defense. So there you go. So perhaps I should have been looking at active PRs a little bit more. But anyways, such is life. Perfect. Okay, so those are the other ingredients that people are working on that will sort of go around this to be able to reach this ultimate goal of having end-to-end, formally verified implementations of these protocols. Perfect. Okay, so now you'll notice that there's a very sudden change in the style of the slides. And this is because it became very, very difficult. I spent like several hours last night at about 2 o'clock in the morning trying to convert all of this into the sort of like PowerPoint format from my original LaTeX slides. And I eventually gave up. And so for the next couple of slides, we're going to have like cutout images from Beamer. And I apologize, I'm just an old man. This is what I know how to use. And you're just going to have to live with it, okay? So there you go. Super. Okay, so I'm going to go over a bunch of basic definitions. We're just going to quickly go to like what even is an IOPP. Most people in the room will probably be familiar, but just in case not, you know, we'll go over that. So yeah, so firstly, we have some notion of a code, which is literally we have some a code has a sort of length, which we call n, it's a natural number, and we have an alphabet for it, which is typically called sigma, and we say that the code is basically some arbitrary subset of sigma to the n, all right? And we call the elements of C code words, and we call elements of sigma to the n, which are not necessarily in C, just words, all right? Then we have linear codes, which are basically just like linear subspaces, so they're basically just like generated by they're like basically a vector space basically generated by some linear transformation, i.e. some matrix on Fn. Right, and so Reed-Solomon codes in particular are instances of these. We're about to see a little bit more about this in a second. We have some notion of Hamming distance, which all of you will be once again bored to death with seeing the definition of, which is essentially in 2 words, what are the number of points in the word at which they differ, and we obviously also have the distance between a word and the code, which is the minimum distance between any element of the code and that word. And essentially, IOPPs are just IOPs that prove that some word that you've committed to is close to the code. All right, perfect. Okay, so then obviously Fry is, which is the main IOP that we're going to be talking about, although as I said, we're going to be talking a little bit about Sternway at the end, is an IOPP for the Reed-Solomon codes, which are simply the a code which corresponds to the evaluations of a polynomial on some domain, right? And so essentially, this is a linear code because we can write down this sort of Van der Monte matrix, which is so x1 through xn are the elements of the domain, is the enumeration of the domain that we're evaluating on. And so we have all of the powers up to k minus 1, which is the sort of degree of our code. And so by multiplying all like sets of k coefficients by these matrices, we get the evaluation of all polynomials of degree k on this domain, essentially. All right? That's the long story short here. Perfect. Okay, so now we can actually start talking about what Fry is. As we said, Fry is an IOPP for Reed-Solomon codes. It relies on this domain on which we evaluate being what we call an FFT domain, which just means that it is a two-smooth multiplicative subgroup, or its coset. We're going to say the or its coset parts later. In fact, in the very first formalization of this, it was literally just a subgroup, right? And we're going to talk in I think the next slide about the generalizations. But yeah, so D is just some subgroup of order 2 to the n for some relatively large, typically large n, or as I said, is coset. And the informal idea of the protocol is the prover sends some oracle access to the original word, which will allow the verifier to be able to query the original word on whatever points it desires, right? And then we repeatedly have this process where the verifier sends to the prover some arbitrary element of the finite field on which our polynomials are defined. And we then fold this polynomial. So we're going to see a little bit about the folding in a second, but this is essentially a simple algebraic operation. In the basic case, it's basically just splitting the polynomial into its even and odd parts and then doing even plus alpha odd. And so that's obviously a polynomial of degree of half of the degree of the original polynomial, and this will preserve some properties that the verifier will later be able to check using the oracle access. And so the prover then creates this new polynomial and sends a new commitment to this polynomial. And yeah, as we said, each round will halve the degree in the simple case of the polynomial, and right at the end we finally send the sort of like plain text, in quotes, the final polynomial after we've done n or k reductions, I should say. And then there are these consistency checks that the verifier does as part of this final check to make sure that all of the folds have, with high probability, been affected correctly. All right, perfect. Okay, so yeah, just having a very quick, this is just having a very quick look at the round consistency check, right? We have, in the simple case, we have the even-odd decomposition, but this actually generalizes to a sort of like, well, to an n case where we can actually split the polynomial, the polynomial according to this sort of like, what's the word I'm looking for here? What equivalence class the power is modulo n, essentially is what's happening here, all right? So this is the two case where the ones that are congruent to 0 modulo n, i.e. the even things go into FO, and the odd things go into F1, but this generalizes to the n case. Yes, basically we show here how this, what do you call it, the new polynomial is generated with respect to this alpha, and then this g is evaluated on a new domain, which is actually half of the size of the previous domain, which are all of the squares, or in the more general case, where we're doing the sort of like 2 to the n fold, the 2 to the n powers of the elements of the previous domain, essentially, right? Yes, and so at each step, the size of the domain is halved, the degree of the polynomial is halved, and after basically, k steps, we expect that the degree of the polynomial that will be revealed to us will be of size original degree divided by 2 to the k, where k is a number of steps, right? In the simple case where we're just doing even odd, in the more in the more complicated case where we have more, because in the most general case we can even have the splitting degree changing over time, and as Ulrich told me, like almost a year ago now, that's actually quite important in practice for reasons that we'll discuss in just a second. Oh yeah, perfect. So. Okay, so now we've gotten out of the LaTeX hell, so we're back to normalcy. What I described to you guys while actually trying to describe as I went along a little bit these generalizations, we said that the generalizations that we had, this was what we showed until now was basically the first implementation of Fry that we had inside of ArcLib. But we generalized this through comments from various people who'd worked on implementation or on the underlying theory. So D was generalized to being some arbitrary coset. We allow the folding degree to be sort of arbitrary 2 to the D powers instead of just even odd folding. And in fact, we allow the folding degree to change over time. And the reason for this, that we really actually want this to be the case, is that in the initial domains, the first domains in the first couple of rounds are very large. And so in some sense, it's kind of easier to lie there. It's easier to commit to some values that will never be checked. And so essentially, you kind of want the folding degree to be high initially, but then for performance reasons, you might want this to decrease as the domain decreases in size, right? And the other thing is sort of early stopping, in that in the sort of naive, well, the first implementation of the protocol, you had to run this until the polynomial was reduced to a constant, and then the prover returned the constant to the verifier against which all of these consistency checks were done. But in the more general case, in this early stopping case, you can return just a full polynomial against which all of these consistency checks are done. Okay, perfect. So now we're going to see some lean, and I'm realizing that actually holding this microphone while doing this is going to be interesting, but let's see how much coordination I have. Perfect, okay. So as we mentioned earlier, the ArcLib is based on the IOR protocol. I think I'm being told it needs to be bigger, right? Yes, for people in the back, excellent, 1 second. And I'll kill the info view to give us a bit more space. Perfect. Okay, I'm back. Hopefully this is legible for everyone now. Excellent. I'm getting a thumbs up from the back. Perfect. Yes. So as we mentioned earlier, we're going to RClib uses this IOR framework, so we're going to want to be able to specify Fry as a bunch of different rounds. So we're going to write the what do you call it? The individual reductions as a round, right? That sort of does the polynomial folding. We're going to write the final round as a what do you call it? As a that returns, rather than actually returning the a commitment to the polynomial, actually returns the polynomial in plain text. We're going to write that as another round, and then finally we have actually a third round that does the final consistency checks, right? So, but first, let's go over very quickly the parameters of this whole formalization, right? So we have some type, which is a non-binary field, is finite, and has some notion of decidable equality on it, which we're going to need for computability. Oh yeah, noting, by the way, that actually this is now a computable definition as of only literally yesterday. Thank you for merging that so quickly, Alex. So now we actually are using the computable polynomial work, which allows us to actually run this in practice. Then we have n, which will be the, what do you call it? The, well, no, sorry. First we have k, which is the number of rounds that we'll have. We have n, where 2 to the n is the claimed initial degree bound. So we're saying that initially the initial claim is that the initial commitment is to a polynomial of degree less than 2n. We have k, as I said, which is the number of rounds. We have s, which for each, oh god, sorry, this is not, oh, okay, great, amazing, thank you, VS Code. We have s, which for each round tells us essentially the folding degree. Right, so 2 to the power of that number is going to be the sort of folding degree that we mentioned, and we have d, which is sort of the bound on the degree of the polynomial that is returned in the final round, essentially, right? And so the first thing is we have this domain size condition that says that actually 2 to the n has to be greater than or equal to so this sum here, 2 to the power of this sum here, is the decrease in degree due to all of the folding rounds, right? And then we multiply this by the final claimed degree, and that has to be obviously smaller than or equal to the initially claimed degree, right? And then we just have this I here, which says that we're in the ith round. Long story short. Yes, oh, and very importantly, we have this omega, which is the left multiplicand of our coset. Right, perfect, cool. Okay, so now that we've gone that, so now we're going to formalize all of these, the statement, the oracle statement, and the witness for Fry. Right, so the statement is kind of, in quotes, obvious. It's for each round that's happened until now. So we're the ith round. We know we have some field element, which is the alpha that was returned in the what do you call it? The transcript at that in that round. Right, we have. The final statement is just the same thing as the statement, but for this last round that returns the polynomial in plain text, so don't worry too much about this for the moment. The oracle statements basically give us for each one of the previous rounds, right? We have a what do you call it? We have basically like the domain oracle that allows us to, on the appropriate domain for the ith round, allows us to evaluate. So this gives us the appropriate domain for the ith round. Trust me. And it allows us to basically then evaluate this, get the oracle commitment for that polynomial at a specific point in all of the previous rounds. All right. Final oracle statement is the same thing, but now you've done all of the rounds, so you're able to see all of them, right? And then you have your witness, which now it used to be a polynomial, and actually we should introduce some nicer notation to make this sort of easier to understand for the mathematicians, because there was some nice notation before that was for the sort of mathlib polynomials. that, what do you call it, that made it sort of a bit easier to understand. But essentially these are the sort of like the polynomial, appropriate polynomials of bounded degree that whose evaluation will be in the RS code, right? So that's a witness, and we also have some witness. Okay, we don't need to care about these theorems. Let's actually jump into the meat now. So there's also sort of like environmental type class stuff that's required to make this work, but let's not spend too much time on this, and let's actually jump to the interesting stuff. But before I do that, I'm going to quickly talk about this, which is the input relations and output relations. You'll note are sorried out, and we're actually hoping to integrate with Yoshi's amazing work on formalizing the simplified round by round Frey soundness proof due to Albert Greta and Nico Montblat. Oh, and Benedict. My apologies. Sorry, and Benedict, indeed. Perfect. So we're hoping to integrate because Yoshi has formalized this along with I think with Nico. And so we're hoping to formalize to integrate this rather into RClib, so we have basically this. So we'll be able to actually have the soundness result for our Frey model here. And the expectation, I think, is that that won't be too hard, although we'll see what happens in practice, as always. Perfect. Here we have the protocol spec for a single round of the a single round of this exchange. So this says that hey, the first message is from the verifier to the prover, and it's actually an element of F. And then afterwards is a message from the prover to the verifier, which is in fact an oracle, a domain oracle, which we define here. Right? Straightforward. Well, straightforward. Perfect. Okay. So now that we do all of that, then we can actually construct, once we construct all of these other type classes, the appropriate oracle prover for this round, right? Which, as we can see, takes appropriate statement, an appropriate oracle statement, and an appropriate witness as its input statements, and then similarly for the statement, oracle statement, and witness, you'll note that the I passed to it here is I.suck, so that's the the index of the next round, right? So this allows us to go from the statement, oracle statement, and witness for one round to the next. So I cast suck actually casts I from a fin k to a fin k plus 1 without actually changing its value. It's just a cast in some sense, right? And so so to do that, obviously we have to define some prover state, which actually I'm not going to go too much. I mean, I think it will just become clear from the send message and receive challenge definitions, right? So the first thing that we do is obviously we receive some challenge, which is some elements of statement fi suck, which as we know is just some sorry, we receive some challenge here, which is just some alpha, which is an f, right? And what we do is we append that alpha to the set of challenges that we've had until now. So basically what this means is we update our statement, which keeps track of all of these previous alphas, right? And also we actually fold our polynomial using the cpolyfold. And in particular, we take the previous polynomial, which is of bounded degree, and we do a 2 to the si fold with respect to alpha. Right, and this witness lift theorem basically just says that this thing is of appropriate degree, actually, because these witnesses, the witness types are just polynomials of bounded degree, as we saw. Right, so this witness lift is just a theorem that says, hey, this is now of appropriate degree, and then all that we do in the response is that we see in this formalized message is basically we send an oracle access over the appropriate domain to the new polynomial that we've now folded, right? And yeah, and that's basically it. That's the very simple. And then as we said, there's also this sort of like output thing that allows you to cast your internal state to the external state. Really, it's very it's mostly like proof. Really, there's not a lot of interesting stuff happening there. So I'll basically skip. The fold verifier in this case, because really the verification only happens in the final step, is very simple. It basically just keeps track of the new challenge and then just continues, right? That's basically it. Okay, and we assemble this into into the Oracle reduction for this folding step, right? Which we're later going to compose. How am I doing time-wise? Okay, maybe I need to speed up a bit, but yeah. Then we have this final fold phase where we said rather than returning the rather than returning an oracle commitment, domain oracle for the polynomial that we folded, we're actually going to return the polynomial. So it's going to be incredibly similar, except there's going to be a little bit of type difference to show that this is not an oracle. This is actually the full polynomial we're sending, right? And yeah. Once again, we have an input and output relation, which we're going to be integrating, hopefully very soon. We have another p-spec, which once again, the verifier sends to the prover an f, but now the prover sends to the verifier a full polynomial rather than this domain oracle, right? So okay, scroll through, all extremely similar, right? Where once again, the challenge does the appropriate fold and then sends back, now rather than sending back this oracle, it actually just sends back the full polynomial, right? That's just it. So it's very, very simple and straightforward. And we also have very similarly the final fold prover, which does one tiny thing, which is that it checks that the degree of the polynomial that was sent is actually smaller than the final degree bound d. Right? Very simple. And fails otherwise, right? So that would be the equivalent of the whole thing once it's composed, essentially rejecting, right? So this is all very simple, and that's assembled into an oracle reduction, and now things really go a little bit crazier, but hopefully we'll be able to follow, which is that now we only have a single thing, which is the verifier sends to the prover. Well, the prover is going to query, as we said, we're going to do these round consistency checks. And what that involves, I realize I didn't go into enough detail, but I'm going to do that now, is it picks L points in the original domain, the first domain for the first round. And it is going to then sort of recursively traverse all of the domains which we reduce through and do this round consistency check. But this basically is just the verifier telling the prover what are the points that it's going to query the oracle at, right? So here we send L points. These L points, as we saw, L is just some natural number, which are points in the zeroth domain, essentially, right? Very straightforward. Okay. Cool. So the query prover here really does very little. It it just at some point receives this challenge, which really is, well, I mean, you can't see it here because the types haven't reduced, but it's just this finel to the other thing, and we kind of just return it and don't do anything. But the real magic happens in the query verifier. So this is where we implement this check, right? So what happens here is we have as input essentially some. So firstly, we get the final. This is the final polynomial, right? That we return in plain text right at the end. We iterate L times. So this is where we're going to be choosing these L random points to query at, and sort of like do the recursively verify through the domains. We get the sort of element of the zeroth domain that we're going to be we're recursively checking from, and then we basically once again do this iteration over the k rounds. You're looking quite puzzled. I mean, it's not too complicated. Essentially, once again, yeah, we're just sort of iterating over these indices, which are in fin k minus 1, which are for k rounds, right? And what we're going to do is we're going to get the sort of like the challenge for the previous round. We're going to we're going to get the challenge now for the current round by powering, essentially. This looks quite complicated, but we're just powering to the appropriate power the challenge for the previous round, essentially. Right? It's just it's just this thing, which is a little bit opaque, but hey. And then we basically then query, yeah, all of this is, yeah, there's a lot of proof stuff required to prove that like the appropriate points are in the appropriate domains. It's, there's a lot of what do you call it, proof content here, which is a little bit complicated to navigate through. But essentially we get a bunch of points that we need to query the ith oracle at, and we then actually query the oracle at this point. Or in the case where we're actually checking the final round, so we've reached the point where I is equal to k, we actually just evaluate the polynomial at the appropriate point, and then we do the round consistency check, which is formalized here with respect to the appropriate values, right? And the round consistency check, we can go to the definition, has sort of the what do you call it? The definition that you would kind of expect if you're familiar with this. But in particular, we have actually proven, which is quite nice, the sort of like completeness result, which basically says that if you take some arbitrary polynomial and you fold it and you do the round consistency check between the polynomial and its fold, it will always return true. Right, so this is the completeness result for the round consistency check. Obviously, there's also a soundness result, which says this thing about proximity, right, which is that if we have something that's far away from the code, well, it will, after the fold, it will also remain far away from the code, but that hasn't yet been formalized, at least here. Obviously, Yoshi has done so. Perfect, and so all of that comes together into the final query oracle reduction. At the high level, we're able to then, and this, yeah, we'll just scroll through this. But the very, very nice thing is that once we have all of these definitions, yeah, sorry, go ahead.
So the final verifier, shouldn't it also check that the thing that the prover sends is of correct degree?
Well, that's done in the final fold, if you remember. That's actually, I mean, yeah, so actually I was wondering about where that sort of like morally, in quotes, should be, right? But if we look at the, where is it? Blah, 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 oh God, so much volume here. But if we look at the fold verifier, this is for the final folding round where we receive the plain text polynomial, right? We have this guard, the nat degree, the degree of P is smaller than D. Right? Yeah, maybe I kind of wondered morally where this should be, if it should be in the final verifier or it should be here. It doesn't really matter. It's there either way, right?
But I guess in practice, I mean, I'm not sure how implementations handle this, but there are different ways of checking that.
Okay.
Right? I mean, you just send the coefficients.
Well, here. Yeah. So here we actually send, you know, a computable. Oh God. A computable polynomial, right? Which obviously is basically like a finite map that maps degrees to coefficients, essentially, right? And so we can then. Sorry? Yeah. Sorry, you're completely right. You're completely right. Yeah. Oh, really? Yeah. I guess. Yeah. Interesting. Yes, but anyways, yeah. So you can computably extract from that what the degree of P is, right? And which so that check is there, is definitely there. No need to worry. Perfect. Yes. So essentially, then what happens is we can in quotes, I'm gonna say this very loosely. Because this is probably going to look quite, maybe a little bit, what do you call it, convoluted to you guys. But this actually sort of works out quite nicely, which is we have high-level operations within RClib that allow us to, and yes, once again, the types are very convoluted, but this allows us to very simply compose. It's a bit difficult for me to say the word simply compose while having that type in the background, but anyways, I'm going to do it anyways. But it allows us to simply compose these oracle reductions together. So basically what we can do here is we compose all of, so this thing allows us to sort of compose together all of the oracle rounds, which we then also compose with the final oracle round to get all of the fold rounds together into one big thing, right? And we just compose this into the reduction fold, and then the final Frey reduction composes that with the query oracle reduction that actually does the round consistency checks. And that formalizes the whole Frey protocol very easily. But the even nicer thing is that, well, we have the Frey protocol now, but obviously, as you know, anyone who's used the Frey protocol in practice knows, in practice, what is almost always used is the batched Frey protocol, right? And so now, because we've got the Frey protocol, we're going to be able to really easily, in quotes, construct the batched Frey protocol. So we can go over here and see that. Well, so we have a notion of a single round, which is going to do the thing that you kind of expect in the context of a batch Frey protocol, which is that it takes the polynomials and is going to create a random linear combination. As someone said yesterday, pretty much the only idea in ZK is random linear combinations. Everything is a consequence of that, so not really a surprise. But essentially here we have some, what do you call it, a batched prover that sort of does the obvious. It takes some set of coefficients and then does an RLC of these PSs, which are inside of the witness, which really is just like the L or M polynomials, essentially, right? And we batch them by doing this random linear combination, and the what do you call it? The verify basically once again does basically nothing, and we get this the batched oracle reduction from this, and then by magic, almost, not really, we then simply and of course the compiler's not working. Sorry, 2 seconds. I need 2 hands for this. Goals. Restart file. Of course. Thank you, Lean. Let's make this a tiny bit smaller. But essentially, all of this is then sort of works very simply by appending together the batched oracle reduction, which actually then, by batching these polynomials together, actually produces the input type, so the input witness, the input statements, etc., of the Frey. And so we literally just compose these things together, and boom, Bob's your uncle, no problems at all. You've got a batch Frey protocol. At the time that we were doing this, the composition operators in RClib were still very much in flux. It was a bit of a nightmare initially, but actually doing this allowed us to refine it, and now they're, in quotes, easy to use. So there you go. Okay, cool. So you guys hopefully have now gotten a flavor of how the Frey formalization worked. And so now we're going to return, hopefully, if I can find it, to the slides. Excellent. First, okay, so now that I've shown you the IOPP, the one IOPP that's been fully formalized in RClib, I'm going to talk a little bit about Bluebell, as I mentioned, which is this probabilistic program logic that we've been working on formalizing inside of Iris Lean, which is the Iris port of, the Lean port of Iris, right? This rock library that's been going on for about 15 plus years. It's a generalized framework for describing separation logics, and then I'm going to give a very quick update on the state of the stir and where formalizations, which are ongoing. So the Bluebell formalization is due to Bao, Dosualdo, and Farzan. Emanuele Dosualdo was actually my second PhD supervisor, so it was super, and we were not working on anything cryptography related at the time. We were working primarily on concurrency. So we were very excited when we discovered 2 years ago that somehow we'd reconverged to working on the same thing again, which I was very excited about. And Ozide Farzan was also one of our co-authors, so it was very nice to once again re-encounter all of these people from my previous existence as an academic of sorts. In this context. Essentially what it does is, I'm going to assume some degree of familiarity with separation logic, if that's, which might not be the best thing, but anyways, given that I've got about 10 minutes left, we're going to have to live with that. Essentially, actually now that I've said that, I'm going to try and give a tiny flavor. I'm going to assume that people are familiar with like predicate logic, at least. I think that's not first order predicate logic. Hopefully that's not too unreasonable. But essentially, we extend this with some sort of notion of a sep or separating conjunction, which is the star operator we can see here, which is quite, which basically in some sense abstractly says that both P and Q are true on disjoint resources, right? And this can be very useful, to give you a tiny flavor of this, this can, for example, be very useful in the context of reasoning about heaps. Because say you have, you know, an assertion that says x points to 2 and y points to 2, and then you have something in your code that says, oh, I update the value of x in the heap to some new value. Well, actually, you also need to prove that, to be able to show that, let's say 3, to be able to show that the precondition of that is x maps to 3 and y maps to 2, you also need to show that x and y are not equal, right? Because if they are, well, then it's updating both at the same time. So this separation operator allows us to sort of focus on only the resources that we care about, and this is called the frame property, frame away the rest and not have to care about it. Because otherwise, basically, in the heap case, you sort of have to keep around, if you have n what do you call it, cells in your heap that you're talking about, you need to keep around like n squared side conditions that say, oh, A is not equal to B, B is not equal to C, A is not equal to C, etc., etc. And that becomes quickly quite unwieldy, right? And can be quite difficult too when you're also referring to like ranges of memory and these sorts of things. You end up with all sorts of linear conditions, which can be quite annoying to reason about, whereas here in separation logic, you can very cleanly use the sort of like sep operator to just say, hey, these things are disjoint. Now, I've been talking about heaps for some time, so you'll probably say, Julian, what the hell does it have to do with probability? Well, well, hopefully we're allowed to swear a tiny bit on stream, by the way. Fingers crossed. So what does it have to do with probability? Well, it is there are sort of abstract notions of separation logics which are working over sort of partial commutative monoids, which is sort of like a mathematical generalization of the notion of resource. And it turns out that actually probability distributions satisfy this condition too. And in this context, star, the sep operator, actually means independently distributed. And this is, once again, you have the same thing when you're probabilistically reasoning. For example, if you wanted to prove things about the Fiat-Shamir transform and you're repeatedly drawing from your hash, your sponge, you're repeatedly drawing entropy from your sponge, you kind of need to know that the different values are independently distributed. And to do this, if you're drawing n values, once again, if you didn't have the separation logic, you need these n squared side conditions that says x is independent from y, x is independent from z, y is independent from z, etc., etc. And so the star allows us to very, very concisely reason about these without having massive assertions, but then also reason locally. So when I want to focus down on one single variable, because I know everything else is independent, I can just frame it away, I don't care about it, I reason about my thing, and then I put the state back together right at the end, right? But then you're going to say, but Julian, sometimes things aren't independent, right? And there we leverage this thing called the joint conditioning modality, which is really for people who are familiar with the Geary monad, which is just like a way of lifting probability spaces into having a monadic structure on top of probability spaces. We have this joint conditioning modality that allows us to make different values be related to one single sort of source of entropy that is what do you call it? That is taken from somewhere, right? And so this will allow us to hopefully reason about these sorts of complex probabilistic computations in a sort of modular and scalable way, perhaps even be used to reason potentially about the compositions of IOPs and these sorts of things. And we're embedding all of this into the IRIS-Lean framework, which will allow us to benefit from all of the automation which is being embedded into this framework as we as it continues to be, as the porting effort from ROC continues. And the status is that basically the IRIS-Lean framework gives you the setup where you just need to give it a model, prove that this model is this PCM, satisfies these conditions which are required for separation logic, and then, oh, magic, you have a separation logic. You will know that your star operator is commutative, you have all of the basic like predicate logic operators that you have, and all of this comes from just proving that your thing is a PCM. So we've proved that the we've developed the model, we've proved that it is what do you call it? Basically a resource algebra, which is what is required to embed this into the Iris Lean framework. We've formalized basically all of the propositional connectives of Bluebell. So there's a squiggle that means distributed like, and there's a joint conditioning modality. Both of these have been formalized, and then there's been quite a lot of work also on formalizing all of the proof rules of this. And to just, well, okay, I'm running very low on time, but very quickly, you can see, there's this embedding, which proves all of the properties that you need for this. It's quite long, I know. Then we've proven that these things that it's a separation logic that's affine, absorbing, and timeless, which then allows us to, and I'm going to scroll all the way to the bottom, to use what's known as the Iris proof mode, which allows us to prove these separation logic assertions sort of automatically. And so we can see that we have in our interactive mode, we have this weird thing going on where we have a turnstile within a turnstile, which is sort of the embedded proof system of Iris happening, and we can actually prove things with it. Perfect. And finally, just a very quick whir update. Essentially, we have the generalized folding, polynomial folding, formalized for which comes from obviously the stir formalization. We've proved that this maintains distance from RS codes. And similarly for the combine operation, essentially in stir. But now we're really focusing on whir because, well, let's be honest, stir is a little bit like people aren't that interested in stir, I guess. Whir is really the sort of because of it being a multilinear commitment scheme with all of the performance benefits. That's really the focus. So now we're really focusing on that, and we've gotten some initial results that are ongoing on actually like embedding this into the IOR framework. Okay, perfect. And yes, just to finish off, there's some other future work, and really, I had to write this slide. I wrote the slide at about 3 o'clock this morning, so I have not done justice to the extremely good work of all of my colleagues in the room and not here. But essentially, yes, we're hoping to integrate Yoishi's work into the Fry work to be able to actually have the full soundness result done. We want to formalize the correctness of the Fiat Shamir and actually then develop the BCS transform and also formalize this correctness to be able to compile all these things to SNOCs. We're also hoping, I guess, to formalize some of these top level protocols like DeepAli and these sorts of things. And as we said, through the MLIR formalization, we actually, or /Rust extractions, as Alex mentioned, we're hoping to then actually be able to formalize all the way to the binary. And many, many, many more things are being done that people will be talking about today. And yeah, that's it. Thank you for listening. Any questions?
So we have, I guess, a bit of time for questions, and then it's coffee break. So
Yeah. No one's going to ask any questions because they just want coffee, I guess.
Yeah.
So okay, no, there you go. Thank you. Oh, it's very possible, yeah. Amazing. Shockingly, at about 2 o'clock last night, I wasn't paying too much attention to the downstream.
Oh yeah.
So
There's a consistent instead of consists. This one is fine, yeah. Okay, so get back to all of this. So next speaker for the start of this session is Devin, who's going to talk to us about VCV.io, which is the library that does handles oracles and all of this modeling for fundamental bits of cryptography. I guess this is joint work with Kwong in particular, and there's ePrint as of today at 6 a.m.
And I don't know what city this is. If anyone does recognize it, that'd be interesting. But this is just the auto first slide. But yeah, I'm going to be talking about the foundational work we have in VCV.io to enable us to make these cryptographic arguments. You've already seen kind of a lot of VCV-related code, which maybe is the ordering is not ideal, because I'll be defining a lot of the things you've already seen, but hopefully it's also true. Also good point. Yes, so I guess the basic question to start with is, why do we need this at all? Why can't we just write these things in Lean as it already is? Is it not enough? And the basic problem we have is that we need probabilistic programs, and more importantly, these oracle calls. And we want to be doing interesting things with these oracle calls, manipulating them, logging things, etc. And if we do something as simple as just use distributions to model these programs in Lean, we can't capture that kind of operation. So the goal is that we want to define, and I'll get into more of what this is, but the idea is we want to define these this monad oracle comp that's going to sort of extend the base Lean language with the capability of representing these oracle calls and reasoning about them. And as an example, here's just like a program that's flipping a bunch of coins. It's non-deterministic, and we can embed it into Lean's I/O monad and actually run it. And we can also just run it by, say in this case, every coin comes up heads. So how do we actually define these operations? Well, first, I maybe won't spend too much time on this because it's not that long of a talk, but there's tons of great work on this already, and I think I might have made this image hard to read. Yes, okay. But there's been tons of work, and there's a lot of different trade-offs and different reasons you might want to use different ones. I mean, a big part of this is just that we want something in Lean because everything else we're already doing is in Lean. There is another recent work called CatCrypt that's also doing something similar in Lean, but it focuses on different things. And I think ideally they're both complementary tools, but CatCrypt also isn't released yet, so I can't say too much about it. And I'm not really going to talk about this much in the talk, but there are a lot of things that Kwong especially has worked on, state separating proofs, HACS integration to get end-to-end verification, representations of universal composability, these types of things. I'm going to just focus on the central framework here. So the main thing we're providing here is a DSL for computations with oracles. And the basic definition we have is we first specify what kind of oracles can we be calling. I think this was kind of covered in some earlier talks, but say we have iota is just the set of all possible oracle inputs. If you have maybe 5 different oracles, then it might be a sum of multiple different types. And this oracle spec is just mapping every input to the type of its output. And then we build this actual monad to represent the computations given some spec by saying a computation is either a pure Lean value or it's just this query bind constructor, which says we're going to query some input t, and then when we would get the result back, it'd be something of type spec t, because spec is mapping inputs to the output type, and we assume there's some continuation function that when it did get that, would continue on with another oracle computation. And given both of those, that's also an oracle computation. And then the simplest case, if you just want to query something and not bind, you can just bind the query to pure, so you're just returning it right away. And these are not the actual definitions. A lot of the language and the the design of this goes through this polynomial functor stuff, which now has its own library as of yesterday, I found out, which is great. I think really the only fundamental difference there is that this iota type is bundled into a structure, so it's not at this high level. Instead, we just keep a pair of that and the other, and these other things get built up in a very similar way. But this is essentially what's going on under the hood. And then, as an example, the simpler specification that we use, in almost all programs will have this as a subset of their oracles, is this uniform spec, which just maps on any input n, you're getting out a finite number in the range 0 to n. The n plus 1 here is kind of just a trick so that we don't ever select from an empty set. And then we'll say probabilistic computation is one that has access to these oracles, just these uniform selection oracles. And note, I'm not actually saying how we're implementing these. I'm not actually defining the fact that it's uniform or asserting anything about that. This is just a syntax that lets you write a computation as if you did have one. And that's, when I have these coins here, these are really, under the hood, just like select between 0 and 1. And then another thing is this language is very minimal. If you look at other work like EasyCrypt or, it varies a lot between systems, but oftentimes the DSL is sort of extensive or has a lot of features. And one of the things we wanted to do here was just keep the most minimal language we can have, which is basically we're just adding on these queries. It lets us reason about them much more easily. And when we do need things like, for instance, to be able to fail or throw errors, which this Rust Oracle comp is what's used with hacks to connect to end-to-end Rust verification. There's not much work on this, but it is doable, and I think maybe some basic examples are fully done with that. But we just use these monad transformers to extend the language rather than assume our base language has like a lot of features. And I can show really quickly that like if you actually look at, okay, what is Oracle comp actually defined as? It's the free monad over this polynomial functor of convert the spec to a polynomial functor. It's just a thin interface, but in practice it means these things. Okay, so we have this syntax in DSL. We then need to actually specify how these oracles behave or manipulate or change how they are behaving. I guess I'm using the paper's phrasing here of query handler, but it's called query implementation in the code. But we're saying if you have a specification of oracles and some new monad that you want to implement the computation in, you just give a map from every oracle input to some computation in that monad of an output for that oracle. And then we can pretty easily just define an inductive definition of how do we swap these into computations. Pure computations, if we make this swap stay pure, it's just a return. And if we have a query bind, we replace the query with this implementation of T instead, and then recursively simulate the continuation with the same implementation. So, for example, if you had this original computation and you simulate it with implementation, you'll get this new computation. It seems very simple, but it's actually quite powerful. We use it for quite a lot of things. So one aspect of it is that we can define these query implementations very modularly. So this definition pre-insert here is saying if we already have an implementation in monad M, and M can lift to some new monad N, and we have some other pre-computation we want to run NX, we can get a new implementation that just inserts NX here, and this is the monadic sequence write, so it just discards the result of this. And then the same with a post insert. You can say, okay, we add this to the end after. And so something as simple as logging is just, we can add logging to any existing implementation by just post inserting in this writer monad, telling it that input. And so then, if we had this example here again, we would now have inserted right here and right here, the logging. We have plenty, there's other things, query seeding, random oracles, rerouting things, especially in reductions. You sort of sometimes need to fake the behavior of oracles. That's all sort of done with this. And obviously, you do at some point need base implementations, right? But the identity function is like the easiest one. You can always just start by replacing things with themselves, and then you can add this kind of functionality on top of that if you need. Okay, so we can represent these computations, but now in the end, we want to actually make claims and prove things about probabilities. And luckily enough, probability distributions are also a monad, so we can just use this same simulation mechanism and just substitute in a uniform distribution, for example. That's at least sort of the default that this notation uses. But I mean, you can also substitute in, some sort of custom distribution or something. But in the end, we get that we can define probabilities so that, say, if you return something, the chance you get the same value back is either 1 or 0. If it is or isn't that value, some proposition might hold or not. A bind is maybe more complicated because we need summations, but these are all sort of the identities you would expect, I think. And note, there's no failure in Oracle comps, so at first it seems maybe dumb to define a probability of failure notation, but actually none of this is actually tied to Oracle comp. It's just sort of a separate interface based on a lot of type classes. So you can actually implement this, I mean, if you want to, on your own monads or what have you, but also when we build these monad stacks, like with option T and error T, which is how we're usually extending Oracle comp. I mean, even in ArcLib, right, there's this failure option T that Julian showed. We can still use this notation just as well on those stacks. The sort of tricky one is state, especially when we have things like heap and things like that. We often probably don't want to sort of take this approach, but for a lot of cases, it works fairly well. Another thing, we have some existing program logic stuff in VCV. Bluebell obviously will be great once it lands and hopefully makes this even more powerful. So I maybe won't go too far into this, but we have a lot of standard weakest precondition stuff. This is ERHL, which is sort of an extension of PRHL. And so we have these definitions. You can write proofs this way. I think it was mentioned in the KZG talk that it's not really written this way. That's a pretty explicit reduction. I think, as things scale, it becomes much more important to have this program logic stuff, and we'll probably have to invest a lot more in it. But you can also just, write direct proofs about reductions and probabilities and such. I'll give just like the simplest example. The only one I can fit on a slide is just one I've had. But one thing is we often make sure that all these things are parameterized over any monad, so the symmetric encryption algorithm shouldn't just be Oracle comp. You can have any potential monad, but usually that's the base of the stack. And I think definitions like this are already starting to show up in CSLib. And CSLib does have sort of some proofs along the lines of what you do in VCV, but they don't have this Oracle representation, or at least nothing quite as developed, and they're usually just working directly with probability distributions right now. So, it's you can only prove so many things that way. But anyways, these definitions might exist more broadly. But then, we can define perfect secrecy as just the property that getting a message and a ciphertext is the same as getting the message times getting the ciphertext, where the experiment here is just for any possible generation function mgen that generates messages and a validly generated key return both. Yeah. And then, we define one-time pads sort of how you'd expect, and you can prove perfect secrecy pretty much automatically. ideally, anything of this complexity, the idea is VCV should be able to handle it essentially automatically. Obviously, larger things will need more work, but I think this is sort of the level of thing that should be automatic, at least in almost all cases. Sort of a more interesting example, we do have fiat Shamir proven, not for what we actually need for all of this, but for Sigma protocols, which means we can do the most basic example. And it does show that the sort of rewinding work we've done and things like that actually are sufficient. This is sort of a very difficult thing to foundationally prove because you need these rewinding techniques in order to fork the algorithm if you've seen the proofs. But we are able to do it with this framework. On the other hand, a lot of this code for it came from an AI, so I thought it might be worth showing what the replay fork proofs actually look like. They're quite long. The AI is sometimes just proving things it doesn't need or things it thought it needed. It's not really using the tactics or the program logic, but it is getting there. It's producing these proofs over time, which again, I guess shows again that the AI is really powerful and it can do a lot of things. And we have to be really careful that the statements at the very end are perfect. But also, we don't have to look too closely at all these proofs, even though it would be nice if they weren't really gross like this. The fun part about writing lean is golfing the code, right? It's not writing the code. So anyways, it's probably for the best. And then I will also show maybe quick with this this run IO I showed in the first slide is just this function that takes a simulation and takes a computation with a uniform oracle and just maps it into, this is all the machinery that Lean provides for generating random things. So you can actually execute all these functions. You can see here maybe this is just like a for loop that's choosing a bunch of random values, and you can see you get a bunch out. Perhaps not that many values. So this is, I guess, the general overview of the framework. I don't know how much extra time I have. 5 minutes? Okay. I figured I'd save a little time. I can show code or answer questions. I'll also mention there is this paper up, this VCV.io. I don't know the best way to find it. I mean, the ePrint archive is just numbered, so you can probably just look up 2026 899 and find it pretty easily. But yeah. Oh, I suppose I have it right here. Yes, this ePrint IACR. And I can maybe show some quick things about the things I didn't really want to cover too in depth, but we do have, I said there's this program logic discussion. We have some discussion of state separating proofs. The UC stuff is in some appendix somewhere, and there's also a few case studies talking about comparisons with SS proof and such. Yeah.
So I think, Derek, do you want us to switch over your laptop, and then we can do questions in the meantime? So any questions for Devin?
Yeah.
So, like, this is more to do with using like AI with Lean.
Yeah.
So this is more of a general question to Lean guys as well. But like you said, that the AI produces like a lot of bloat. It's proving a lot of stuff it doesn't need. Do you guys? How much do you guys care about that? Do you actually take like steps to like removing the bloat or like cutting down on the proof sizes, or if it's just, even if it's 5 times longer than it needs to be, if it still proves and if it still verifies and you're okay with it?
I would say I'm probably the one who cares the most about this and does probably spend the most time trying to clean things up. And I think it is actually very useful.
We don't care about this, yeah.
But when you're doing that cleanup, it can actually be a really useful tool to find things that are missing or things that need to improve. Oftentimes when the AI does write a bad proof, it's because something's missing that it should have had access to. And in that way, you can actually sort of benefit from it. With the fork in particular, there's also the aspect that this paper needed to be submitted and the ePrint needed to be ePrinted. So that code has gone through a lot less iterations. I think if you look at the other examples, a lot of them are a lot tighter. But yeah, I think it is really important. Especially, I don't think we've had a major version update to Lean yet since AI became super heavily involved. I think 4.30 might be a little painful, but I guess we'll see.
Yeah. So the other thing is everyone is aware of the problem of like AI proofs being generally kind of ugly and overly long by a factor of 10 to 100. But there are also then tools being developed to also shorten proofs and clean them up automatically, which as of this morning are helping actually.
And is there a performance loss? Does it take
there's an increased build time, which is very annoying.
Okay.
But then so there is a discussion between. You can be very opinionated about the proof should be of the highest quality, and MathLib, for example, does this in Lean, so they merge 0 AI proofs. And then also something like RClib, where we want to obviously make contact with whatever the state of the art of cryptography is at that point and trying to move faster as a result. So we're straddling that middle ground, and yeah.
I mean, I'm very perfectionist about commit history, and this is not necessarily in Lean, but I imagine you can get Claude to clean up your proofs in much the same way as you can get it to clean up your commit history. No? What's the obstacle?
It's more the reason that the proofs are long are mostly that the AIs are very good at doing a lot of case analysis. And so instead of doing general arguments to progress the proof in one big step, they do a lot of tiny steps. And that just seems the way that they do things in general. They're also quite bad at using tactics, for example. So Steven said in his example, like there are tactics around that would make the proof that he showed much better. The AIs just don't use them. It's something we've given feedback to the various AI companies who have asked us for feedback. It's just the way that they're trained and the way that the harnesses work. But obviously, if you could give them a better harness that says like use grinds, develop a grind set, use dig tactic, which is in this place in the repository, especially for like repository custom tactics, then proofs would become much nicer, fairly easily. But I've had examples where I've removed a 15-line block of proof that I could just remove and proof by reflection.
How does this interact with, for example, a LaTeX starting point? At least for some of the targets, it's not like we don't have starting proofs and strategies that are already in papers, right? So those are like pretty good skeletons to start from. Does the AI just like forget them and reprove it like in some ugly way, or?
It follows the arguments, but it still does a lot of this case-in-case bias. So my proof with Polyshuk-Spielman, which was the first kind of big AI proof we did, was in total 2,500 lines of proof split across 30 lemmas or so. A tight proof written with like efficient tactics, I estimate would be 200 lines. And this, but this was in January, since it's gone on a bit better, refactoring has gone on better. And this is like, I cut out like 100, maybe a couple hundred lines of it myself, just going through the proof once to like check that it seemed reasonable. So the proof steps are still there. It just does a lot of like very tiny incremental steps instead of saying, here's a general argument or here's a tactic that just progresses the proof like a lot. It also just proves random things in the middle of the proof which are not needed. It just adds content. Yeah, of course, but it's like it doesn't always do it quite reliably. So the one way we've done it is actually, for example, for Polyshuk-Spielman. So there's a Polyshuk-Spielman.lean file, and that has like a nice proof. And then there's like the 30 disgusting lemmas, and they're like in a subfolder, and then you ignore them. You don't look at them. And the Polyshuk-Spielman proof, like actually, it does follow then the steps that are in the BCIKS paper. And so you can read the proof, and you can tell from the naming of the lemmas that like this matches your intuition. And then just the dilemmas of these kind of like very highly proof-specific items, which are in a subfolder for later cleanup, basically.
And maybe I'd point out, like with the paper comparison also, a lot of the things that are really big in like the fork proof, for example, in the original paper are just like, therefore, comma, the thing, and that's the proof, right? Like it's, people are just assuming it's true, where it's like kind of obvious to a human eye reading it, but like AI has to actually prove it in Lean.
Well, you have to do the like monadic faffing.
Yeah,
which you don't need to do on paper.
That's also true, yes. Computations are sort of some GUI thing in a paper.
Yeah, hence the program logics. Okay, then I think we'll switch over to Compoly. Okay, so I'll do a quick intro so that we don't lose too much time. So next talk is about Compoly, that is computable polymers in Lean, and generally turning our specifications into executable specifications that we can run. So this talk by Derek from the EF, and obviously kind of joint work with, as with every other thing we're talking about today, many other contributors from Nethermind and ZK Security.
Yeah, great. Yeah, thanks. In fact, okay, so one thing to mention is that I've written my slides today in Lean, and so all the code you see, unless it's a screenshot from VS Code because it was too hard to put into the slides, they all type check. And so, yeah, like Alex mentioned, loads of collaborators. I've listed all the GitHub handles of direct contributors to Compoly with this little screenshot, and then we also have our faithful AI contributors helping us all the time. But yeah, so all of this, lots of people in this room have contributed, and yeah, this is joint work with a lot of people. So, like Alex mentioned, we are the goal of Compoly is to make our specifications in ArcLib all computable, and I guess by computable we mean executable. And so we want to be able to run ArcLib as a proof system in principle. And so, in order to do that, so yeah, our ArcLib is primarily right now a specification framework for snarks in Lean. But because Lean is both a proof language and an actual functional programming language, the difference between specs and programs can be a little bit blurred. And so we're asking the question, can ArcLib be an effort to build proof systems in Lean and snarks and things? So the computable core of all of that effort is Compoly. Compoly is a little bit of a misnomer. It started out as polynomials. We've added field specs, and there are conversations to add loads more algebraic things, like was mentioned in Julian's talk before. So yes, it's meant to be the computable engine. Maybe the first question is, why do we want computable specs at all? I think there are lots of answers to this. I guess in the early days of formal verification, I forget what decade, maybe the 70s, 80s, there was kind of this battle between do we double down on testing to secure our software, or do we try to formally prove things? One of the arguments that has been salient over the decades and is still used today is that if you're writing software, the very process of writing down a specification forces you to think very precisely about what you're building and will help you encounter edge cases. So even if your specification can't even really be connected to the code in any formal way, writing down a formal specification is just a good idea. We've made so much progress in the last few decades of being able to connect code to actual formal specifications that we are now in a position where we can build these huge specifications in Lean, and trying to specify something like a proof system in Lean turns out to be a large engineering project in itself, and specifications are code, and so we want to take it a step further and ensure that our specifications are correct. So the first thing to point out is that formal specifications are programs. Just like the programs that we're trying to verify them against. And so they can have bugs, and therefore, if we can make them into programs that we can run, then they can be executed. And there's a long history of executable specs from a low level to a high level. Like TLA Plus is a good example of that. Of you write a spec and then you can actually run it in some runtime, and that will help you find more edge cases of your spec, which in turn helps you ensure that the program itself is correct. Second point to make here is that specs are very hard to write correctly. A specification, a formal specification, is supposed to be a description of what you mean by correct when you refer to software. And software is very complicated and has loads of edge cases at all levels of abstraction. So specs themselves are hard, especially for new and emerging technologies like snarks. And so the field hasn't had time to really make concrete, stable, and distilled the specs that should be kind of universally used. There's new research coming out all the time. And like Alex mentioned before, there's the research on paper, there's the implementations in the wild, there's the lore surrounding everything, and then in our formal specs, we're trying to sort of figure out what the quote-unquote canonical thing should be. And so part of that, so they're just hard to get correctly. And then maybe taking a very short, more philosophical take on formal specification is that the line between specification and program isn't a program that gets compiled down to bytecode, just a specification that you've written in a language where you're specifying your bytecode. And so there are many levels of abstraction. We're already, I would argue we're already working in specifications if we're writing code, and in RClib we're trying to be a higher level. And I would say maybe the very best specification in this case is actually a formally verified reference implementation, which is RClib. So, okay, there's more to say there, but it's too much of a tangent. So we'll just go straight into comp poly. So comp poly started with polynomials, and I'll be talking mostly about polynomials in this talk. Polynomials themselves, of course, are essential in snarks and everything we're doing, to the arithmetization, to the IOPs, commitments, to Fry. And like I said, there's more than just polynomials here, but yeah, very, very important. But polynomials are also just universally applied all over the place. And so a library like comp poly, and just like a computable, efficient, algebraic library for these primitives that are so important, has loads of applications all around, including computer algebra systems. So these first two examples I've written here are two ideas that are actually people in the wild implementing things who have been curious about comp poly. So computer algebra systems got a message just the other day. Turing machines, that's an ongoing project. But then, numerical methods, coding theory more broadly. And I think comp poly is interesting because MathLib already has a robust library of polynomials in Lean. They're, of course, non-computable, which is what we have been using in the past in RClib. But I think one genuine use case for CSLib is to implement well the non-computable definitions in MathLib and kind of have a mirror. And what we're hoping for with comp poly is that this can be a good, maybe a good example of doing that kind of set a precedent for other efforts to make computable definitions, certain definitions in RClib. Sorry, in MathLib. The goals of comp poly, the first goal, I guess, is to be a canonical reference of computable polynomials in Lean. We want this to be as widely used as possible and as robust and as efficient and as kind of nice and clean as possible. We want it to be flexible enough so that it can be used all through the Lean ecosystem for various things, and we also want it to be efficient. And that is something that we're working on right now. People in this room are actively working on making it efficient. And I'll talk about that a little bit later. And so in what remains of this talk, I will kind of give an overview of the structure of the library, the philosophy that we've taken in building it out, some of the roadmap and goals, and then this third point, I have some some new results as of this week of formal verification with comp.poly that has just started. Right, so the core definitions for polynomials is we have univariate, we have bivariate, we have multivariate, and multilinear. Of course, the univariate and the bivariate are special cases of the multivariate, and etc. But we've actually chosen different data types for each of these for various reasons. But we do have the relevant isomorphism theorems. So univariate polynomials are first defined, they're coefficient arrays. So in comp.poly, we have what we've called kind of the raw polynomial layer, where these coefficient arrays can have trailing zeros. And then we have this is canonical predicate, which just says that last coefficient in the array is non-zero. And then the canonical, we're mirroring the MATLAB definitions. So there's the polynomial definition in MATLAB, and we're just putting C in front of the relevant MATLAB definitions for computable canonical. So in this case, what we're calling canonical univariate polynomials are coefficient arrays modulo the is canonical predicate. And what I mean by that is they're just trimmed coefficient arrays. Bivariate is our nested nested univariate polynomial, so it's a polynomial of a polynomial. Multivariate is this is different. So I guess the univariate case, we have dense coefficient arrays. Multivariate case, the data type that is used is more optimized for for sparse polynomials. And so there's this extensible tree data type that's used to map the monomials to their coefficients, and this lawful definition is, so I guess I kind of put it the other way around. So there's, similar to the univariate case, there's this, in this case, there's an unlawful version which has zero coefficients, and then we quotient by the kind of trimming operation to get multivariate polynomials. And then there's also multilinear, which is a tree map from monomials to coefficients as well. Oh, sorry. Right. Which for multivariate. Let's see. I don't actually spend very much time. Julian.
I actually wrote this. So
Yeah, Julian wrote this. Yeah.
The first thing is a monomial, which is a mapping from fin n to a nat, which is basically for your monomial. It maps, the fin n's basically are the names of the different variables, and it maps to the degree within the monomial. And so it maps each monomial to its coefficient. So the extreme map maps a monomial to its coefficient naught, essentially. Right? Does that make sense? And then the third argument is just because the extensional tree map needs an order to be able to get the logarithmic performance in fetching different things, and so we just give canonical order of the monomials, essentially. So, answer your question? Yes.
Nice. Thank you, Julian. Right. Okay. So the general pattern that we've shown. So I've just shown you the basic definitions of what we mean by the polynomials. And the goal here is, because the goal here is to have a computable version of the non-computable definitions in MATLAB, we need our relevant ring isomorphisms. So what we do is we have our basic definitions. We implement a very basic API, just standard operations on like add, subtract, multiply, and I guess we'll see them in just a second. And then we have these functions that take your computable to the non-computable and back, and we have ring isomorphisms that we prove. So we have ring isomorphisms for all of these, and we have definitions for everything in the relevant theorems. So for example, in the univariate case, we have add, an add operation, which is exactly what you think it is. And then we have these theorems that show that addition, as long as you have a semi-ring, that if your polynomial coefficients are all in a semi-ring, then your addition is commutative and it's associative. And we go further, with the multiplication to prove all of the ring laws. The basic polynomial API includes getting the constant polynomial here, the variable getting just having a single variable, and the coefficient function, which gives you the coefficient at xi in x to the I in the univariate case. And then we have this function to and from. Oh, that's funny. Oh, you don't. Oh, good. You don't see that. Okay. There's a anyway. Right. So we have two poly. This was very hard to write in a way that would type check, and so I've just had lean output this very ugly version. But the point here is that we have a two poly function here. Right here, and we have a two impl, which takes you back to computable, and then we have the ring equivalence, which says C polynomial R is isomorphic to the polynomial ring. And part of that is to prove that we had to prove that addition over this isomorphism, addition is as you would expect, same with subtraction, multiplication. Anyway, just basic ring isomorphism. Proofs. So I guess we have our minimal definitions, and we define as much as we need to get the ring isomorphism, and then the goal from here is to delegate all of the proof infrastructure to MathLib, and basically none of it to comp-poly if possible. So proof strategy is if you encounter a computable polynomial in lean, you hit it with the isomorphism, and then you have this beautiful plethora of theorems from MathLib that you can use to your heart's content. So an example here is work that Julian here did for the Lagrange interpolation, and there's just part of this is defining a basis divisor, and then the relevant lemma shows that the basis divisor under the isomorphism is what. So this lemma proves that the computable basis divisor function is correct, and that is showing that it is the same under the two poly isomorphism as the one already defined in MathLib. And so the really nice thing about this is that in this case the proof is very simple, but it's taking advantage of all of these kind of isomorphism theorems that have already been proved. So the idea is with comp poly, proofs should really just follow from MathLib. Right. So we have all the definitions as of maybe a month or two ago. All of those are nice and done, and we're currently in the middle of phase 2 of trying to push efficiency as much as possible in comp poly. So we want these to actually run in a reasonably efficient kind of production mode. And so we have, like I said, many people in this room are already working on this. So for univariate, we have FFT, NTT, currently being, in fact, FFT was recently finished and it will be merged soon. Multilinear, we just started with folding, batch evaluation, efficient factorization of bivariate polynomials, fast field arithmetic, exponential optimization, efficient decoding, error correcting, all of this. So we're in the middle of this large push to make this a reasonably efficient library, and then we'll kind of fine-tune from there, which is very exciting. Which means that we're trying to push the limits of Lean as an actual functional programming language that could in principle run in production. And so we're very excited about that. And then, yeah, Alex has a lot to say about compilers and things like that to make it even more efficient, and maybe we'll just do everything in Lean. It's all very exciting. Right, so I have some slides. I'm running out of time, so these are code excerpts from some recent progress from people in this room to make these polynomials evaluate more efficiently. And then finally, I want to share that the goal of all of this, like I said, is to have really good specs in Lean, and that means that we should be formally verifying things in Lean. So we've been working hard, and by we, again, I mean people in this room, have been working very hard to get the extraction process from Rust into Lean, because most of the ZKVMs that we care about are all in Rust, and we want to verify them in Lean. And so we've been working very hard with people, experts in extracting this. And we recently were able, the tools are getting to a reasonable place, so we're able to extract some of the relevant crates in Plunky 3. So this last week, I extracted Koala Bear. And the process this looks like kind of in the wild on the ground is you have your crate, your Rust crate. You can extract the Rust, and it will extract into this proofs directory. And what it does is it gives you a Lean file. You build all the Lean infrastructure around it. And then you can import comp.poly, for example, and formally verify things. And so I've managed to get some, these are very basic proofs about Koala Bear that just essentially say that the relevant constants are what we wrote down in our specs, which is almost trivial to prove, but it is a starting point. And the goal is to expand on this and hopefully to bring all of the ArcLib specs into direct application to production code. And comp.poly is the vanguard of that, being the most basic, kind of computable, kind of most fundamental piece. And that's all I have for you today, so thank you.
Katie, do you want to switch over or do questions?
Okay. Is that about the kind of duplication with MathLib?
Yes.
So I was looking at the, I was trying just to teach myself Lean and to do elliptic curves as a starting point. And so I saw the bias trust curve definitions in MathLib.
Yes.
And they're not computable. But the reason why they're not computable is just one tiny thing. It's that the slope when you're doing the addition is that if you just add two, if you change 2 lines, then it's computable. It's so frustrating that there are nearly computable definitions in MathLib that we...
Yeah, it's
right.
It's because it requires decidable equality of
Exactly.
variables. So
Yeah.
if you substituted that in, you can trivially get... But the thing is, it's not efficiently computable, which is why we went for the extreme map.
I see, okay. So yeah, I see why the definition that you would choose for efficiency is different from the math one, but it does seem as though kind of you could still make the MathLib one computable. Is there any?
There's no reason for this. It's just that mathematicians don't want to care about decidability, so they just use classical everywhere, and they use the axiom of choice to be able to construct these computations.
So it's like some people, like Bavik was complaining about this.
Yeah, Bavik was complaining about
So there were historical discussions. If you go on the Lean Zulip and you search for
Right.
polynomials, you will find a yearly, it pops up every year.
Okay, so everyone complains about this. It's not just me.
yeah.
How do I think about these optimizations that you're putting into comp.poly to make it efficient? Like, so maybe in the context of a field, like we have these special fields that have these very, very inexpensive reduction operations. Is that happening as a special class that's extending comp.poly, or is it downstream of that? Are you somehow doing you're affecting the C++? You're generating C++, right? So
Well, yeah. So Lean compiles down to C, but we don't really touch the C. In our case, so for comp.poly, you have a definition of a polynomial, and then you have evaluation or something. And there's a naive definition, which is slow, and then there are algorithms that are more efficient. But as functions, they should, given the same inputs, they should give the same outputs. And so you have your naive definition, you use that as a spec for your more efficient definition. You define the function, and then you can prove equivalence, extensional equivalence.
So you sort of specialize the type on a particular prime, say, and then you give an explicit definition of the operation?
Well,
or
yeah,
is
you
there's a
either
proof that it's equivalent, or?
Make a new function, so you could get a function and make it more efficient, and kind of swap the efficient function out for the inefficient one, while keeping the underlying type the same. But like Julian was saying, with extensible trees in in the multivariate polynomial case, sometimes you do want to change the data type so that it is more efficient to compute over, in which case you need some notion of equivalence with your original. It doesn't have to be a type equivalence, but kind of for the purposes of the thing you're doing.
I think the question is if you do an optimized reduction that is field specific,
Yeah.
and then the field has to come in as a parameter.
How are we making that more efficient? Guess that.
Well, we haven't done it.
Yeah, we haven't done it yet. Yeah. Yeah.
Am I being completely ridiculous by kind of wanting to translate the whole Zcash protocol spec into Lean?
Yes, do it. Yes. Yes.
Okay.
Oh, and yeah.
Thank you for the enthusiasm. It's more likely to happen because of that enthusiasm.
So yeah.
First thing I need is elliptic curves.
Yes.
Computer.
Okay. Great. Oh, awesome. Yeah. Let's.
Use that time to go post-quantum as well.
Just to say that like transferring specs, AI is you need to guide it, of course. So pay attention to what it's doing, but it's very good at that.
It's also very good at comparing specs and implementations.
It sure is. Yeah. Cool. Okay.
Sorry, in your last example, you were extracting from Rust code and then comparing with the compoly, but why do you need to do that? You already have the Rust is already the executable part.
Okay, so the Rust is executive. Okay, right. So why do you need
So
executable
you can just use
specs?
the spec like the.
Yes. So so your spec, it's very hard to write a complete spec, and so for the case for just proofs of correctness, maybe you don't need computability, but you can also go further and do things like differential fuzzing.
Sure.
Yeah.
If you're not proving, then it's definitely useful to compare to executable implementation.
Exactly. Yeah.
We do actually want to run it. So
Yeah.
we're going to write a compiler from compoly and ROOM3 that goes down to x86 or RISC-V, whatever you want. GPUs actually, before the video actually, and it'll be the fastest.
All right, thanks.
Ask me next RClip Day2.
All right.
Cool. I think that's it. Yeah. Thank you. Yeah.
Okay, so then next up and last talk for this session before we go to lunch will be Katie, who's at Imperial College, and she's going to tell us all about the mathematical foundations that we had to build into RClip for coding theory and all of this.
Some overlap with what Alex said, but yeah, it's good because I can see there are new people in the room. So first of all, what is the vision of RClip? So RClip is aiming to provide modular and composable frameworks to formally verify snarks in Lean. You've seen already a lot about it, but basically we're mainly targeting hash-based snarks, which means we need a lot of coding theory. And yeah, the project is part of the ZKVM program, and we've got 32 contributors so far. So 2 months ago we had 20, and now we're already up to 32, and 9, 10 are regular contributors. And yeah, so basically the goal of RClip is to become the go-to library for formalized modern cryptography. So the way I think about it is we want RClip to be the MATLib of cryptography. And that's the overarching goal, but what are the blockers maybe? So as I said, we want to be able to formalize modern cryptography, so we want the papers, the theorems, the definitions, the protocols. So to do that, we need stable foundations to be able to talk about all these things in Lean. And firstly, we need mathematics that's involved in everything. Then we need computability. Derek already covered a lot about this. And we need probabilistic backend. So Julie and Devon already covered a lot about this. So these are the components. And also the last, so the computability and the probabilistic backends were kind of blockers, but now there's been so much work on it. It's already getting to a very good state. And the mathematics was also a blocker. I'll explain why. So this is one of my favorite slides. So we've got all the we've got all the components of RClip. I didn't know there is a new library, Polyfun, so I couldn't put it on there, but maybe I'll add it with, I don't know, appropriate emoji for fun. So we've got the computability, we've got Bluebell, we've got VCVIO, and of course, MATLAB. So MATLAB is a huge library of formalized mathematics. It started in 2017 as a community effort to formalize all type of modern mathematics. It has, I found out yesterday, 100,000, I don't know, a lot of definitions and twice as many theorems and 772 contributors. But because, as I say, the goal of MATLAB was to formalize modern mathematics as, you know, to aid research, to verify research, to fill gaps in proofs, because mathematicians, I mean, I'm mathematicians, and I could confirm that we love to say, oh yeah, that's obvious, or that's left as an exercise, and so on. And when you want to formalize this, it's an absolute nightmare. So yeah, MATLAB is helpful. And yeah, also another good thing is if you have all of modern mathematics formalized, you're going to speed up peer reviews, and you can learn a lot by adding detail to your own proofs, I also found out. However, since the emphasis is on modern mathematics, basically the content there is not evenly distributed across all the fields, and it's geared towards whoever's contributing and their research interests. As a consequence, a lot of foundational areas were not well developed. So I was actually shocked when we started working on RClip. I was shocked to see there was not much linear algebra in there, to the extent we had to define column and row ranks of matrices. And on the other end, there is like triangular categories and shift functors, but I guess no one really cared for row and column operations that much. And there was absolutely no coding theory in MATLAB, well, that's partly the new thing. In MATLAB, when we started RClip, the only thing that was there was the definition of Hamming distance. And another thing is that to get something into MATLAB, there is like, you can't just add one definition. You need to prove a lot of things about it. So there is a whole API that needs to be developed. And I found out the API for Hamming distance consists of 60 supporting instances and lemmas. And this is just to define the Hamming distance, and then the metric, and show all these things, like it's reflexive and so on. So yeah, that was done by Rena Robson, but I don't think she's done much after that. And of course, as we already explained, not everything there is computable. So there were polynomials, but they're not computable, and there are elliptic curves, they're not computable as far as I know, even though I know some people have started doing computable elliptic curves, but I don't know the status of that. So yes, long story short, we want to use MATLAB wherever we can, but we had to build coding theory from the ground up. And what I mean by this is we literally had to start with the definition of code. So here are a couple of definitions. They were the basis of the basis. So first you can see the definition of a code is just a set over an alphabet R. There are no assumptions on R. Even the decidability is not so needed, but it's needed in most things, so we can keep it. Then the second definition shows the linear code. So we have a finite type iota. This is going to be the length of the code. And we've got F, which is a semi-ring. So this is then the code is a submodule over an F submodule of iota to F. And basically what this is a subspace of the vector space F iota. And people might ask, why do you get semi-rings? So one of the things in MATLAB is that everything is defined in as high generality as possible. And if I define something as a semi-ring, then if I need it to be a field or a commutative ring or whatever, then Lean would recognize that this is a specific case of a semi-ring. So it's good to keep everything in the highest generality possible. And also having it that way, if we ever decide to PR these things into MATLAB, then they're already in the correct form. And then the next definition, this is actually due to Chung, is of a module code, which as far as I know is not a definition in cryptography, a term in cryptography, but it's kind of a very handy definition which helps us talk about, you could specify to linear codes and to interleaved codes at the same time. So as you can see, the difference is you've got, again, a semi-ring F, you've got a finite type iota, well, it's not even finite here, but yeah, iota is a fin type, and A this time is a module over F. So you're not just specifying to the field itself, you can take any F module. And of course, if you take something like f to the k, then you could do interleaved codes. This submodule f becomes submodule f of iota to k to f, and then this is exactly the interleaved codes. And then something that Julian spoke about in great detail, but I'll actually show you the definition of the Reed-Solomon code. Now you know everything else about it. Here is the basic stuff. So you've got, this is our definition. First, we define evaluation on a set of points. Of course, first, again, you have the semi-ring. I explained why. And it's the same idea with the domain. So the domain is just defined as an embedding from the fin type iota into the semi-ring F, but there is no condition on smoothness or anything. You could add those conditions wherever you need them. And then you can see the code itself is a polynomial, evaluation of polynomials of degree less than deg. So I've seen in the literature, sometimes it's less than or equal, sometimes it's less than. We have it as less than. So yeah, you have to be careful with theorems, whether you're one-off or not. And here it's a non-computable definition, but I suspect we could make it computable now. So other things, I've shown you the basics, but also there are gazillions of other basics to get anywhere. So we had to define dimension, length, relative distances, and all the supporting lemmas you might need. First of all, the lemmas you might need from the papers. And also there's so many lemmas you have to prove for these notions that, for example, that they're greater than 0 and all these types of things I never thought of proving. I just thought, well, it's the case, right? Then we define generator matrices, relevant theorems for them. So for example, existence of generator matrices, how you can define a code from a generator matrix. Basically there is an equivalence theorem between a code and how to extract the generator matrix if you want, then interleaved code definitions, and I think there is is it a full formalization Chunk did of the interleaved proximity gaps for interleaved codes paper? Yeah, so there is a lot of things on interleaved codes, then tensor codes. We've got the Burley-Welch decoder, the Guruswamy-Sudan decoder, they're proved now, and I hear they're going to be computable versions of them. Pulisic-Spielman fully proved by Alex. Then Johnson's theorem, which, and then blueprints. So blueprints first, we started last year after, simultaneously to developing all the basics of coding theory, we started writing a blueprint for the proximity gaps for Reed-Solomon codes paper. And what we mean by blueprints is that we would add all the definitions and prove as many supporting lemmas as possible, but leave the main statements unproved. So you just formalize it and you say by sorry, and then people can add proofs. And there has been a lot of progress on these theorems. I'll talk about this in a minute. And then many more things, plus a lot of mathematics that needed to be proved. We have whole folded to MATLAB, and then all of these, as I said, many linear algebra results, some probability theory, a lot of polynomial stuff. I added another version of Schwartz-Zippel, which I proved with Aristotle, actually, because it's just easy to auto-formalize, but it was a very convenient version. That was last week. I don't think it's been merged yet, actually. So yes, one of the goals of the blueprint of the proximity gaps paper is the proximity gap for RS code theorem. So we formalized that whole statement, but we didn't prove it. This is the formalization. And I'll go to VS Code in a minute. I don't know how much time I have, but okay. I'll go to VS Code and go through as much lean as possible until the end. But this is just a snippet of the formalization of the proximity gaps for Reed-Solomon codes theorem. So you've got all of these parameters are needed to define the RS codes, as we've seen before. And then you've got your delta epsilon pair. And then we split it into the unique decoding bound and the Johnson bound. So actually, in this definition, there are two cases hidden in the definition. I'll show it in VS Code. It's going to be better. Well, I'll walk you through most of the library, hopefully. Well, we'll see. And then ongoing work, what I'm currently working on is formalizing the polynomial generators paper. There's going to be a talk about it, which is the next talk, and I can see Alessandro's here. So the goal is to formalize everything up to the polynomial, the theorem that polynomial generators have mutual correlated agreement for Reed-Solomon codes up to list decoding. And the progress, yes, so far, all the definitions of I've formalized all the definitions of the generators, which is, the first section, and there were some lemmas about them. I'll show you all of this in a second in VS Code. So yeah, it turned out along the way we didn't actually have MDS codes. So MDS codes are maximum distance separable codes. So these are codes that meet the singleton bound, such as RS codes. And there was nothing about MDS matrices. Basically, these are Bayesian matrices such that every case submatrix is a full rank. So you could use that to prove an equivalence that if you've got an MDS code, then the generator matrix is an MDS matrix, which I actually proved. And I also have the proof that Reed-Solomon codes are MDS codes. Oh yeah, I said this. Yeah, and some missing mathematics was formalized. The Schwarz-Zippo counting lemma, for example, that was quite useful. So yeah, some examples of the generators definitions. So I don't want to give too much away because the next talk is on the paper, but let's just look at the definition of a generator. So we have a generator is a function so you have output size L, which is a natural number, finite field F, and the generator is just a function from S to F to L, so the vector space of dimension L. And this is how it looks in Lean. So you've got three types. There are no conditions on the type, and the generator is the type itself, and it's a function from S to L to F, where L to F is essentially the same thing as thinking as F to the L. Well, that's just how you write it in Lean, I guess. So another main definition, which would be very important for the main goal, is to formalize the generators that have mutual correlated agreement. So here you can see you have loads of components. So the generator we already have as a type. We have an F linear code, C, which we have. So we need an error function from the unit interval to the unit interval. And the condition is for every U1 to UL, which are words of length n, you have a parameter gamma in the unit interval. Then you define a matrix where these words are rows. And you've got this mutual correlated condition, which is, we've seen the definition many times yesterday, but this is just the formal, this is the way it's formally written in mathematics, and this is how it's written in Lean. So first of all, you had to split the definition in two definitions. So is MCA is just the condition inside those brackets, because it's easier to take it out rather than have this huge thing inside the probability. And we've got our generated type, we've got the linear code, then we take X is an element of S. We've got, this is the encoding of our matrices of words. So L is L, as it is in the paper, but iota is N, I think. Yeah, because I kept to iota from the beginning. For some reason, we chose that linear codes are going to be modeled as submodules from my from iota to F, so I just kept the iota throughout. And yeah, this is gamma in I, so it's very cool. I didn't know this. MATLib has a whole type and notation for the unit interval in R. So it's just this I is the unit interval in R. And yeah, you can see. So then V is this, the matrix multiplication, GX times U. And then there are these other definitions. So the projected word is what I called basically this, which is when you have a code word and you restrict to a subset of the indices to get another word. I don't know whether this has an actual well-known name in cryptography. If there is, I would like to know, because I just called it projected word. I couldn't find if there is another term people use. And same for projected code, which is, yeah, this C restricted to T sort of, where T is a subset of N. Yeah, so these are the conditions formalized, and then from there you see how you can get the MC generator. So you say for every matrix of that type and for every gamma in the unit interval, this is our probability notation. You randomly sample X from S, and then you say, okay, this condition holds, and it's less than or equal to my error at gamma, and this is just a cast, because probabilities live in the extended real numbers. So extended non-negative real numbers. So yeah, you have to just cast your real number to a non-negative real number. Okay, I don't know how much time I have, but I'll switch to VS Code to show you a bunch of other things. Okay, so this is you actually already saw. Okay. Is it okay, or maybe more?
You can do the sidebar.
This? I want it because I want to show things in it. So yeah, so you can see in our clip, you just go to data, and then there is a whole section on coding theory. And it's divided into many folders now. Before, there were just a bunch of lean files. So in basics, you can find the basic definitions. So the coding, well, they're coming alphabetically, but in linear codes, you have the definitions of codes, and linear codes, there is a file on distance, relative distance with all the lemmas. The MDS codes are in a, actually I've opened this one. So the MDS codes are in a separate file. This is the MDS matrix formalization. Then some theorems needed to prove the equivalence. We've got in Reed-Solomon, I don't know, this is some new file. Then divergence of set, this is in the proximity gaps paper, there was one theorem on divergence of sets, so we defined this and made a whole file for it. So you could see this is the preamble to formalize that statement, basically, which is, this is the divergence statement. Okay, so then Guruswamy Sudan, interleaved codes, there is list decodability, then the Polish-Spielman is here. Oops, it's not here, I lied. There was a file on the Polish-Spielman. And Reed-Solomon codes, this is all the basic definitions and lemmas on Reed-Solomon codes. So I showed you the definition. Then, yeah, then there are a lot of lemmas. You can make a code word into a polynomial by interpolating and so on. One cool thing that Julian proved was that the Vandermonde matrix is the generator matrix of the RS code. And back in those days, there was no Vandermonde non-square matrix in MATLAB. So we had to define it too, but now there is. Even though it's defined a bit weirdly, in my opinion. And yeah, then here you can also find the theorem that RS codes are MDS and many other things on RS codes.
Should we look at proximity gaps? And then
Yes.
What was the use of classical reasoning there?
Where?
It's not actually needed. It's just so I wrote this proof originally, but then the definitions shifted, and someone was clearly rewritten this with Aristotle. So a lot of the LLMs
What here?
This like reflex of always injecting things that are never harmful. So if you make things classical, so it's like classical, and there are things like use decidable and simp and these sorts of things. It always adds these in because it just increases the power of the tactics. And so they have these like weird idiosyncrasies that they always do. But yeah, it's actually probably if you remove it.
you can remove them quite a few.
Yeah, you can always remove. So if you remove classical, it will still compile like arrows.
So we have the.
Uh-oh.
No, you have to do some. You have to do some tweaks to fix it. You have to remove some.
Okay, so this
But this is.
Drag in some classical lemmas.
Yes, fair enough.
But Julian, this is our formalization of the matrix. This is not the MATLAB one, because I didn't actually, the MATLAB one is still not merged, because Kwong refactored, then my PR got lost, and now I have a new PR, but that's a whole other thing. So yeah, this is actually with our Vandermonde non-square. That's not the MATLAB one.
I see, okay.
But I don't know this classical business and where it came from.
In this case, it's actually needed.
Yes.
So, yeah, I'm not sure how that ended
No,
up.
no, but you can usually remove a sim call that's dragging in a classical lemma that you're not seeing.
Yes,
and then
yeah,
you
yeah.
control.
Yeah, because the thing is, there's some polynomial things here.
Yes, that's probably why it's happening.
So it's probably that. Very quickly, before people start for lunch, theorem 1.2, I already showed you the proximity gaps, but it has been proven now. I can see, and it depends on all the sub-results. I've not read the proof, I'm not going to lie. I don't know who proved it, actually. Oh, amazing.
I mean,
Well done. Okay, so then theorem 1.4 from the proximity gaps is that you have correlate agreement over lines. This is proved in unique decoding. Did you prove it, Alex?
Well,
Yes.
can't
So
comment.
due to
I thought we needed to get it done before real world crypto, so I did it the day before.
yeah, so we have this in the unique decoding. But yeah, I think in the list decoding up to the Johnson bound, there is most of the things are sorted out, and all the weighted correlate agreements from that paper seem to be sorted out.
We're missing a few things of proximity gaps over correlated agreement over curves.
Yeah, so I had this open, but somehow it's disappeared. It's in the file, proximity. So there is a folder on proximity gaps, then the proximity gaps paper. So the affine lines are here, then curves. Well, that seems to be open, but it's gone.
So I fixed some things in the rational functions files yesterday.
I see.
So Xing should make the curve ones doable now.
Oh, nice, very
That
nice.
is tentative.
Yeah, so it's still sorted. And yeah, the affine spaces,
Affine spaces is a Series 1.7 in the
I think that's proved. Affine spaces is proved,
That was
right?
done at the same time, because you needed that for the Reed-Solomon one.
I see, yeah. I saw so it's just the curves currently missing.
Yes, but I think the curves, I fixed some stuff in rational functions, which then fixed some stuff in agreement.lean, which should fix stuff that is needed for the curves.
I see.
My PR is still a draft.
Nice. So yeah, we've got a lot of these, but the weighted ones, so all the weighted agreements at the end of that paper, they're sorted, I think.
And then actually we need to change some of the bounds, because there was the on proximity gaps released on the Curtis paper at the end of that last year.
Yeah, yeah.
We need to update some of those statements.
And also we're planning to update the definition of mutual correlate agreement as well, and encode the proximity, the generators language in there too. So yeah, this is kind of the demo of things you can explore yourself. There is a lot. So this is the formalization of proximity gaps for interleaved codes that Chung did. There are some things from Ligero, then a lot of other things here as well. The Polish, no, I keep clicking on this. There is a whole folder on, there it is.
That's, I have the subfolder.
Yeah, yeah. That's the whole folder.
The main proof is nice, you can click on it. The main proof looks okay now.
Okay, so main proof. Okay, so this is the statement of Polish-Spielmann. So a statement begins here, and it goes up to here.
So we got that statement wrong twice.
Yeah, that statement was interesting. So that's the statement, and this is the proof. Oh, it's almost as long as the statement. The statement is almost as long as the proof, I meant to say. Yeah.
And the proof uses all of the intermediate lemmas, which
Yeah.
have hundreds of line-long proofs.
Yeah. So I can see there are 3 more files. As you can see, there is a degrees file, and then.
Did you get it wrong in instructive ways, or?
The first time we got it wrong was because there was an implicit you can divide by 0 in lean, as you all know. And the first time we got it wrong was that it was no, it's fine. It works. It's fine. The first time the way it was stated allowed basically dividing by 0, which on paper you would not do, but you could in lean, and then you could get basically a trivial proof, but it was the wrong statement. The second one was that in one of the bivariate polynomials tried to prove it, and it failed, and I was like, this makes no sense. And then I looked a bit more closely at the statement, and I was like, oh, fixed it, and then the proof went through. So it's a very
one
stupid.
interesting one.
Yeah, and this
The division by 0, 1 is now in a nice file for the agents to remember to consider.
yeah, so this is a statement from the proximity gaps paper, the correct one. As you can see, it's proved. So yeah, this is all I wanted to say. Thank you very much for listening.
Okay, maybe one question at most, and then I think everyone wants to go for lunch.
Hi, very nice work. I have a question about the definition of MCA. Since you mentioned that, I guess, we want to try to keep things as general as possible.
Yeah.
I think the MCA definition, we could state it for module codes, I guess, or at least it should be well defined for that as well.
Oh, yeah, that would be.
I mean, we didn't try to I suspect the following is possible. Surely the definition can be lifted to module codes. And then possibly, we didn't try to do it. I think the proof, at least in that paper, like I can't think of anything that specifically fails, at least at a higher level abstraction on whatever we stated. And I very much support the abstraction of module codes. They're very useful. Yeah, you can express matrix codes and like other things that sort of we don't normally consider, but for which these things hold, right?
Yeah, yeah, really. Yeah, so here I could try it with module code and see what happens. What now? Oh, okay. Where is it? I don't know whether I've got the correct imports. Let's see. Where is, 1 second. No, it's not here. 1 second, I think. Generator, linear code. So is MCA. So this is module code. What is it? Don't know how it's. Maybe I don't have the imports. Module.
On a module.
Ah, cool. Yeah. There it is. But it needs the F. Then what else does it need? I don't know. Well, yeah, we don't have the. Can I just say? Let me see 1 second. I wanted to. So I need the F. I need the iota first. So I have 2 parameters. I would need an extra parameter because here I would want something else, right? Kappa to F. Well, I don't have kappa, so of course it's gonna complain. Okay, so then done. Oh no, it's not done. Oh, because projected code is defined as linear. Oh no. Oh yeah, it has the wrong type. Okay, so then the projected code would have to be changed, but yeah. Yeah, I'll try this in the lunch break.
Spend 10 minutes thinking.
Also, does anyone know if projected code has a better name?
Restricted code?
Okay, okay.
Do you want to open a PR?
Okay, that's in another file. Okay, I'll do this in my own time if that's okay.
Okay, then lunch, and then the afternoon will be front ends, and then future and AI.
if you want to see. You prove the.
That's nice. So this is not specific to GKs, like it's RISC-V. Anybody using RISC-V would benefit from this.
Oh, is this in EVMSM?
Yes.
Nice. Okay, I think we're happy to start again. So this session is about front ends, that is circuits. And so the first talk we'll have is by James on ZK-Lean, and I'll let you.
All right. Thank you, Alex. Yeah, so this is a talk on ZK-Lean, which is a DSL in Lean for writing ZK statements and verifying those statements. This is joint work with some of my former colleagues at Galois, as well as Lisa and Carl. So why do we want ZK-Lean? I don't think I need to convince everyone here why ZK is great. It's being deployed in all these amazing applications like blockchain, anonymous credentials, voting systems, and post-quantum signatures. These systems are being used to protect billions of dollars in assets, so we want to make sure that they're actually secure and not vulnerable to being stolen. So as most of us probably know, writing ZK statements can be complex and difficult to write. So if you have a single bug, single soundness bug in your implementation, this can render your whole proof system basically worthless, and you can prove false or anything like that. So the solution we're proposing here is to use ZK-Lean. And you could use ZK-Lean to verify that your front-end ZK statement is correct with respect to some specification, and you can use this to verify soundness of your system. So just as an overview of what ZK-Lean is, so it's a DSL that's implemented in a library for Lean, and it's a way to easily write ZK statements. It allows you to, it supports most ZK features, so for instance, R1CS, higher degree constraints, lookup tables, MLE-based lookup tables, and we even support RAM if your backend supports that. There are two primary ways that you would typically use ZK-Lean. One is, let's say you have your arithmetization in some other language like Rust. You could say have some tool that extracts that arithmetization, converts it into ZK-Lean, and then once it's in Lean, you're able to verify that it's correct and that kind of thing. The second approach that hasn't happened too much yet, but hopefully this is the approach that happens in the future, is where you can write your statement in ZK-Lean itself, you can verify it correct, and then maybe you pass it to some backend, maybe through LZK or something like that to verify that your ZK statement written in Lean, you can run it in your actual system and you know that it's correct. ZK-Lean itself is it's agnostic to the backend. We don't really care what proof system you use. And then proofs in Lean can be a bit tedious to do, depending on what you're proving. So we've implemented some tools to help automate this process. And there's the link to the repo if you want to check it out. And I think we'll be updating this to the Ethereum one as well. Oh, it's already there. Is it public yet? Yeah. Oh, well, it's also there. Okay, so here's a really basic example, right? Let's say you want to witness a new variable, and you want it to be constrained to be 0 or 1. So here we have this monadic language. You can see it's a ZK builder. That's the monad it lives in. And here we're returning a ZK expression, so a ZK variable. This is polymorphic over the field. So f is our field here. And the first thing we're doing is we're just calling witness. So this gives you a new witness value. We constrain it to be equal to 0 or 1. So this is a constraint 0 equals x times x minus 1. So traditional way to do this in ZK. And then you return this new witness value that you can use in your larger computation. So under the hood, ZK Builder, it's a free monad implementation. We found this to be very convenient to express your semantics, but you could also do things like pretty print your circuit if you wanted to extract it into another system. The language provides many different combinators, so you can see how we use witness and constrain eq, and then there's also combinators for doing lookups, lookups with MLEs, reading from RAM and writing from RAM. So in ZK-Lean, we define a operational semantics for circuits. These semantics are executable. So here's like the type definition of the function of what the semantics are. So it takes as input the circuit that you want to run, and then it takes a list of witness values. And then basically it evaluates the circuit and then says, whether or not the circuit is satisfied. So this can be pretty convenient if you want to test out your circuit on different witness values and see if it's correct or not. So here you can see like different runs on different inputs to the witness 0, 1 circuit that we just saw. So if you pass 0 and 1, it returns true. And if you give it some random value other than that, it's going to return false. So the main purpose of ZK-Lean is to do verification of circuits. So this is how you could do soundness of your circuit. So basically soundness is saying that the circuit satisfiability is implying some specification for your circuit, right? The way that you write this in ZK-Lean is it's stated here in this formal proposition. But here we're using Lean's standard do notation. So this allows you to write composable proofs using this like do notation. And this is in like a Hoare triple style. So the way that this works is that let's say on the first brackets, these are like all the preconditions that are given to the circuit. Now we have your like monadic circuit evaluation. And then here you have some specification on the output so you can make sure that certain conditions and stuff hold over your circuit. And the nice thing about this is that it allows you to compose many different lemmas and statements together. So if you have a subcomponent of a circuit, you could easily write your circuit function over that. And then you can build up higher level proofs by composing all these calls using these Hoare triples and some built-in machinery that Lean provides. So let's look at a case study that we did. So we proved a circuit for Ketchak. So the first thing you need when you want to prove a circuit correct is you need a reference specification. So this is an excerpt of what Ketchak's implementation looks like in Lean. Here's the state of Ketchak, and here you can see you have 25 lanes. And notice that these are all over 64-bit bit vectors. And now you have your round function, where it's calling helper functions for theta, rho, and all the parts of Ketchak round. And then now for your overall Ketchak, you're just doing a fold over that Ketchak round, so you're doing 24 evaluations of that. So now if you want to implement this in ZK-Lean, it's actually, I think it's pretty nice and very close to the actual specification itself. So here we're defining a state again, and again with our 25 lanes. But in this case, we have a ZK expression over some field. So notice before, the specification was over a bit vector. And now we're just changing to whatever field you're using. Yeah, and again, if you look, we define the circuit for a Ketchak round in this case. So again, we're calling theta, rho, pi, et cetera. Except now we live in the ZK builder monad to build our circuit. And then you do monadic bind to pipe along the state between all these subfunctions. And then again, you can just do a fold over like the 24 rounds, and then this builds up the whole Ketchak circuit, and it's pretty nice and modular. Okay, so now that we've defined all that, we want to prove correctness, soundness of our Ketchak round circuit. So this is the soundness statement. You can see that, so it's taking, it's reasoning about two states, the state over your field elements that are used in your circuit, and then also the reference specification state. And again, as a reminder, these are over the bit vectors. So as a precondition here, you have a an equivalence between the bit vector representation and the field element representation. So the two inputs have to be the same. And then in the post condition here, you're saying that an evaluation of the spec of a round of Keccak, so this is over the bit vector representation, that's equivalent to the output of the circuit evaluation. So this is sort of doing a simulation proof over the reference semantics and the circuit. And you can see, since we're integrating with Lean standard do notation, this is like very nice and composable. So if you're not too familiar with Lean, you're introducing a few variables. You're doing a few simple rewrites based on unfolding the Keccak definitions that we've defined. And then here we're just doing a few spec calls to all the subcomponent lemmas. So there's one lemma for theta soundness, one lemma for rho soundness, chi soundness, etc. And then here you end up with like a pretty nice, simple composable proof of a Keccak round. Obviously, anytime you're doing formal methods, it's important to be explicit about what your trusted computing base is. So here in ZK Lean, you're basically trusting the operational semantics that I told you about earlier. It's pretty small, so you can inspect it yourself, but you're still trusting that that's implemented correctly. You also need to trust your extraction either to or from Lean. So you want to make sure that you're verifying the thing that you're actually running in production. You're also trusting that the specification that you've written is correct. And then, obviously, the Lean kernel. I guess Julian over lunch was saying they just found one soundness bug in the kernel, so you can ask him about it later. I think there's some overflow, and you could basically overwrite all memory.
No, that's in the runtime execution. It's not in the kernel.
Okay, so maybe it's fine.
Yeah, if you run a program, you can hit a bug, but it doesn't affect proofs.
Okay, well, it's good to know. Okay, so like I mentioned, there's like a few ways you could integrate with ZK Lean. So one thing you can do is you could write a custom extraction from your, say, your like Rust backend or whatever. So we've done this for Jolt. So we wrote a custom extractor from Jolt into ZK Lean. This is basically like a binary tool that links against Jolt's library. It extracts all the MLE tables for all of the instructions in their lookups. And then now we have basically Lean representations of all of Jolt's front-end semantics. So here's like an example of what this looks like when you run this extraction tool. So on the top, this is the lasso lookup table for equality. So this is like the RISC-V equality instruction. So like that's what the Jolt Rust code looks like at the top. It's basically taking its list of inputs, points, and evaluating the polynomial. When you run it through our extractor, you get this expression at the bottom, which basically works by linking against this function, building up an AST representation of the function, and then it just pretty prints the output. So you have pretty high confidence that the expression that you end up with in Lean is actually corresponding to what you're running on the Rust side. So while you can write custom extractors, they are like pretty intensive, and you have to do it for each system. So an alternative integration approach that we've taken is to integrate with LZK. So this is, I don't know if any of the Veradice guys are here, but this is a system developed by Veradice, and it's like a MLIR dialect for ZK. So the advantage of this is it kind of solves like the LLVM problem of like having a bunch of front ends and a bunch of back ends. So similarly here, like if you have a bunch of front ends like Circom or SP1, and then you have a bunch of back ends, it solves the n squared problem or whatever. So what we've done is we've actually implemented front ends and back ends for ZK Lean. So let's say you were to write your front end statement in ZK Lean, you compile it to LZK, and then you could use LZK to compile it to whatever backend that you care about, like I don't know what's currently supported, but maybe like R1CS or, yeah. But eventually probably air. And
so front ends we have airbender now as well.
Okay.
And
Yeah.
I guess Martian over there is working on more.
Cool. Yep.
And backends, I guess there's a Python backend now as well, or SMT backend in general.
Okay. Yep. And yeah, so, and then we've also implemented the ZK Lean backend. So like, if you have your SP1 circuit, you could run it through LZK, and then you'll get a ZK Lean representation of your circuit. So this is a much more modular way to get usage in ZK Lean. So just as another simple example, this is like, you know, a very simple is0 circuit in Circom. And then on the right-hand side, this is like what the LZK output in ZK Lean looks like. I mean, here, these are the two main constraints that you care about, right? You want to make sure that the negative input times the inverse plus 1, that output equals, times the input equals 0. So you can see it's a little more laid out since it's automatically generated, and this is also a bit simplified. But here you can see the input, negative input, times the inverse plus 1. You're constraining that equal to the output variable. And then you're also constraining that the input times the output is equal to 0. So it's pretty one-to-one mapping, and you can like follow it and make sure that it matches what you expect. Yeah, so like I mentioned earlier, we've implemented some automation to help with the ergonomics of doing proofs over belt circuits. So this work was actually just accepted to CAV, so Lisa will be presenting that later this summer. But basically, we've implemented a tactic in Lean called bitmod EQ, and this helps you automate some of these proofs between like field arithmetic and bit vectors. So yeah, helping you solve those kinds of problems if you're proving those about your circuits. So let's start with an example. This is Jolt's encoding of bitwise OR. Just to see like why this works, let's look at like 1 bit. So let's say, you know, 1 plus 1 minus 1 is 1. You know, 1 plus all right, I won't go through the rest of these, but you can see that the truth table actually represents bitwise OR. And yeah, so our goal here is to prove that actually, when you represent it, the finite field math of that actually represents the bitwise OR operation. So here you can see we have preconditions at the top that each of the bits of xi correspond to bit vector 1, and all the bits of y correspond to bit vector 2. And then here our postcondition, or our goal is that the bitwise XOR of BV1 and BV2 are equivalent to the field arithmetic of that MLE expression I just showed. So the way that bitmod EQ works is that initially we have some statement over both finite fields and bit vectors. We do some range analysis to basically convert all these into statements over natural numbers and bit vectors. Again, we do more range analysis to convert all the natural numbers into bit vectors itself. And then once everything's in bit vector land, this is very nice for like existing automatic solving tools. So we use like BB_decide to automatically bit blast, and then this will be able to automatically verify the statement for us. These are the rules that we use to do all these range analyses. The ones on the left are from the finite fields to natural numbers, and then on the right are from natural numbers to bit vectors. These are a bunch of range analyses. I don't know, maybe to highlight one, like if you look at disnat here, if you have 2nat of an addition, you can split it up into 2nat of the left plus 2nat of the right, given a, and if you add a modulus over the field. So, yep. So to evaluate the system, we did 2 real-world case studies. The first was the Jolt ZKVM, and then we also evaluated it on Cersei. So for Jolt, we verified all of the lasso lookup tables and all the 32-bit twist and shout lookup tables. And these, again, are encoding all the RISC-V instructions. And then for Cersei, Cersei is basically like a verified compiler for ZK. Previously, it only had like an SMT backend, and we've basically added a like lean verification backend for Cersei. So here you can like kind of look at like what we're able to solve versus the existing SMT solutions. So initially, like we do have a little bit higher overhead in terms of runtime on like the smaller instances, but then the SMT solver like caps out and isn't able to like solve all the problems. But you can see like with Bitmod EQ, we're able to solve all the jolt problems, even if it takes a little longer, but it's like trivially longer on the small cases. And then same thing for Cersei, we're able to solve much more of the Cersei cases. So. And yeah, if you're just comparing Bitmod EQ versus like manual effort of doing all these proofs, so Lisa did like one of these proofs manually by herself, and it was like, I guess 200 lines, and it took her 10 hours or something like that. And yeah, now on the right-hand side, I guess now it's 5 lines and it takes 10 seconds to run. I think you could get this down to 2 lines pretty easily. And then you can see like the savings, right? Like over 32 lookup tables. You know, that's how many lines of code you would save, and like that's how much effort you would save in terms of developer time. So I think pretty nice results. So yeah, in summary, we've been developing ZK Lean, which allows you to write ZK statements in Lean in a pretty nice and composable manner. It gives you a way to do compositional proofs, integrating with like existing Lean infrastructure around like standard do. We have this integration with LZK, so you can easily integrate ZK Lean with your existing proof systems, and hopefully more will be added as the LZK infrastructure continues to evolve and grow. And then we've implemented Bitmod EQ, which is this tactic to help you with these proofs and automate them. So yeah, I encourage you to give it a try, and yeah, let us know what you think.
All right, we have time for some questions. I guess, Mark, are you switching out? Yeah. Any questions?
Thanks for the talk. Really interesting work, especially with the tactic. How does ZK Lean relate to Clean?
I think it's a similar space. I think maybe there's a few design differences around how like statements are represented in Lean. Oh yeah, we don't support explicit witness generation. Although basically, since you could just write a Lean function that does witness generation, and then that like basically covers it. But we don't have like explicit like support in the language for witness generation. We don't have a separate notion between like subcircuits and circuits. So I do think that's nice, like in terms of the composability of using like standard do for these like core triples. Oh, there are no more subcircuits?
Still is. I've been lazy about this.
So maybe eventually they will be similar, more similar. So yeah.
And then, do you use it for formal verification, like to extract constraints and specify and verify?
Yeah. So all those like Jolt ones, like those are extracted from Jolt's code base, and they're verified.
Cool.
Yeah.
So it's in the actual Jolt repository.
Yeah.
Oh,
That extraction code is in Jolt source code, and I mean the goal eventually would be to like run in CI like extraction every time they make a PR, and then like in CI verify that the proofs still pass or whatever.
100%, yeah. Cool.
Why not do that now?
So they switched to 64 bits, and Lean can actually type check the 64-bit, some of the larger 64-bit polynomials just because of the size. So it would require more engineering effort to just fix that basically. So.
Any other questions?
All right. So yeah, thanks again, James, for the great talk. And so next up we'll have Marco, who's going to tell us about clap. We can switch to Bine if we need to.
I think last before the talk, don't suspend the Linux system.
But I use Linux as well, and it turned out okay. We've had quite a high percentage of Linux users actually present.
Then use the first laptops then.
I have
Can
an
I use
X1
yours?
Carbon. Yeah, yeah. I have an X1 Carbon as well.
No, but I had this first specifically.
Oh.
This one.
Oh.
It has this great property that if I watch a video on YouTube on Firefox, it shuts down. Only on Firefox. It's a productivity hack.
You haven't asked Claude Nicholas.
Can you hear me well? Yeah. Okay. Hello everybody.
No,
so I'm gonna
it's not working.
It's not working. Okay.
Yeah, the microphone isn't working.
Test, test.
This one works. I can yell to the end of the room. No, it's okay. I'm going to use this one. Okay. Blah, blah. All right. Okay. Hello again. I'm going to try to make up for the lost time. So I'm going to present. Okay, good. So I'm going to present CLAP. Some of you might remember CLAP from an older work a few years ago. This is quite different. Same spirit, same lesson learned, but more lesson learned. And so, and this is going to be very oriented to verification and lean, like the other works in the session. So this is joint work with Nethermind, the formal verification team at Nethermind. They are still, so this is very much work in progress. So we are still doing a lot of work. They're doing amazing work. So thanks to them. So what is CLAP today? So CLAP is not anymore like an embedded language or a DSL. It's just a subset of Lean. So today you will write circuits as a subset, it's just pure Lean. Okay. Of course, Lean is a very generic programming language, so you can write things that would not be expressible as an arithmetic circuit. And so, of course, if you write those things, we're not going to compile them. Okay. But if you restrict yourself to what can be what is an arithmetic circuit, then we should be able to compile it down. Then there might be some little problems on like limitations of our compiler pipeline. So maybe if you're using some, for example, for loop syntax, we still for in syntax, we still don't support. We might in the future. So, but I would say that we support a very large subset of what you can be written in Lean. And so right now, what CLAP is a meta compiler that is going to take your Lean code and is going to produce constraint system and witness generators. So why this is kind of, if you have to remember one thing, remember this. Why this is the core idea and the core differentiating factors also with the other existing DSLs. Because if you, basically what you're going to write is very similar, or in my head it almost coincides with what could be an executable specification of your circuit. So what you're writing is not a builder, like we saw in the previous example, is not constraints, as you're going to see soon. It's really, I think, the cleanest possible mental model that you can have of a circuit, of an arithmetic circuit. Which means that if you need to do verification on top of it, you're sort of starting from the best possible place. Like nothing of the compilation pipeline is going to pollute whatever theorem or properties you're trying to prove. So I'm not saying that it's going to be easy. So if what you're trying to prove is very complicated, if you have an incredibly optimized implementation and a very high level spec, well, there's still a big gap to prove. But the point is that any Lean developer can do that, even if they don't know what a circuit is, or maybe AI is going to be able to do that, because there is less of the backend that pollutes the specification. This also, okay, an old topic from CLAP was automatic optimization. So again, like we start in a very clean state, so it's easier to do many of the optimization that we want to do. I'm not going to talk too much about this today because there isn't enough time. And okay, we care about, the reason to do this in Lean was because we want to verify the circuits that we write, but also that we want to verify CLAP itself, so the pipeline that is going to bring everything down to a constraint system. And so for every step for every transformation, we have theorems and properties to preserve that preserve the semantic of what we're trying to write. So the idea is that you will be able to take your lemma from the highest level specification and bring it down to the cryptographic proof system. All right, so this is very much work in progress. So I'm just going to try to give you an idea of the status of what is there today and what is not there today, what is vaporware promises, and what is actually proved. So this was, again, last summer, I decided that I wanted to retry CLAP in Lean, so, and I did some experiments, and I ended up doing a complete redesign. I was planning to do the usual embedding, and then I ended up doing something very different. I'm going to describe this later. And right at that time, I need to thank Nethermind and Julian in particular for funding a grant from the Aptos Foundation to develop this more seriously and with more energy, with more people for 6 months. And we're almost at the end of this grant. And kudos to the Aptos Foundation that really believed in the project. That was not even an embryo at the time. It was really just, it was very, pretty much a sketch in my head. They believed in it, and Alin Tomescu has always been a very great supporter of our work. He's been following us and helping us to do actually the core of the grant, that is to replace their Circom R1CS circuits that are used in their Aptos keyless products. This is kind of, I must say, it's kind of a hard nugget as a first exercise, because it's a lot of circuits. It's a lot of code, and they're the nasty kind, in the sense that it's not nice elliptic curves, or like this is like classic primitives, so like SHA and like, so a lot of bits, a lot of so pretty tricky. And just in size, like it's a lot. It's a complicated circuit with a lot of checks and a lot of ingredients. So this is what we have today, is that we rewrote all the circuits in Lean. And so far, so we have a first iteration of the compiler, but it doesn't scale to what we require. So I would say that we don't produce constraint systems yet, if that's what you expect to see. And we're just started writing specifications, so we don't really have done a lot of work on proving that the implementation corresponds to a specification. This is still a work in progress. So yeah, I wanted to give my usual speech about please do things correct by construct. I'm not sure I have a lot of time. But I just want to repeat that doing things that are correct by construction and building a system with formal methods at the design stage, it's absolutely not equivalent to building something using maybe a fantastic Rust pipeline, maybe a terrible amount of horrible code that produces some constraint system at the end, and then knocking on the door of a formal methods person and say, can you please fix this? Can you please prove that there is a specification of some kind? So even if they do, the result is not the same. You're not getting the same, okay? And I think the real world example that the grown-ups have shown us is that you can move from TLS 1.1 and to 1.2. There were a bunch of attacks, a bunch of researchers, cryptographers, and formal methods people, symbolic protocol, or like hardcore cryptographic primitives. So there were a bunch of attacks, and like the research community reacted, and they sort of fixed the attacks, but it was a catch-up game. And things changed completely with TLS 1.3. There was much more involvement from the beginning of the design phase, and the result is completely different. So I'm very happy that all these languages are coming up to do the right thing from the start. Okay, I'm not going to get too much into the history of how I got here, but the point is that I already did 2 embeddings of circuits in very different settings, learned a bunch of lessons in the process, and what I was trying to do with CLAP in Lean was to do something a bit different. And so let me explain so embedding, there's nothing wrong with embeddings, I love them, but when you try to do formalize things on top of them, they get a little bit in the way. So, and the point is that, actually, I mean, the previous presentation was amazing. It explained what I wanted. These slides much better than what I did. So what they have is it's a builder. What you, or I mean, what I already had in my previous projects. What your circuit ends up being a monadic builder that is going to build a deep embedding, or like if you don't know what that is, just a data structure that contains your constraint system. And so that's perfectly fine, and it works very well in practice. And I know people that have, so yesterday I was talking to the Tachyon guys, and they have a beautiful Rust code base that does this. So this can be done very well. The problem is that when you build a deep embedding, at every step you need to sort of convince yourself that what you build makes sense. So at every step you have a sort of well-formedness when you need to say, my constraints do what I think they do, and like my wires are all allocated correctly, and I'm not messing up, sort of. And you need to do this at every step, which is why we were saying in the previous slide, there was, actually I can show you an example for my terrible things that I wrote in the past. This is a piece of F-star, don't ask me why. So this is a very simple num to bits gate that is supposed to take a field element and explode it to bit. So this is what I was trying to, sorry? Sort of, yeah. I said, don't ask me why. So anyway, you can. It doesn't really matter what this is written in. The point is that you can see that this implementation is like 4 lines. It's pretty simple. It's nothing too fancy. This is this is like the pre and post. So you can see that again. It lives in a state monad. So I am carrying a bunch of state with me, which is what the usual. There's nothing weird. And so every time you want, basically up to here, this is craft just needed for the monadic builder. I need to say what I got was already well formed, everything was in bounds, and then I'm going to give you something that is still in bounds, and blah blah blah. Okay, this is not fun. And then this is the bits that it's interesting. And even in here, because I have a deep embedding, I need to always talk about evaluating things. I always have a denotation function that gives a meaning to the data structure. Okay, there's nothing wrong with this. This is like what you do in these embeddings, and it's perfectly fine. But when I did this, I said, okay, I don't want to write this again in my life. And the point is that I could fix this with a lot of automation, which is what they brilliantly did in the previous work. So in ZKLean, this is completely hidden. There are tactics that do this for you. And it looks very nice. When we were looking at the Hort triple before, they were not this horrible thing. Okay, so there are definitely ways to do this properly and effectively. I just decided to try and do something differently. Okay, so the point is that proof assistants that are based on type theory, they are very good at, I'm not going to go into the carrier correspondence, but the idea is that if you want to prove something, you need to build a program, and this can be very complicated, and so they give you a bunch of facilities to build programs, to transform programs to programs, and so so this is what we call tactics. And I mean, these languages are meta sort of by construction. They need to be able to reason about their own programs. And so they also help you to do this correctly. And so they are sort of a great playground for certified compilers. Lean Meta is famous for being very, very good. In particular, at the same time, it's very expressive, and it can also be very efficient at what it does. And so I thought, let's build a meta compiler. So finally, let's look at the meat of the story. So what a clap circuit is, or rather, like what would you like a circuit to be? I don't know. If you ask me, I would say I don't want it to be a relation. First of all, like don't give me a relation. I would like it to be a function, and because we know that we're going to check something, that our circuit is going to add a bunch of assertions, then I know this is going to be a partial function. Okay, so I'm not too surprised that it's going to live in an option monad. And if I'm doing an intermediate computation, then I expect to receive a value, so it could be an option alpha. But anyway, if an assertion false, it's going to get a none. I think this is familiar also for people using Rust. So there is nothing Lean specific about this. And then, of course, if a circuit terminates, then the only thing that it can return is an option unit. So it's going to say some unit. It's equivalent to say accept. Like all the checks passed, let's say the cryptographic proof system should accept. So if I want to write, and of course, this is just what it means to be a circuit, the number of inputs that needs to be statically known, and it has to be fixed. Okay, so I cannot just receive a list and do unbounded recursion to go through the list. Okay, so this is what. Sorry. Okay, so this is what very simple circuit. So you were laughing at James' example, but this is words. So this is just an addition. So yeah, so again, this is just an option unit, and I'm just receiving my arguments, and this is an equivalent of writing a constraint if you want. And as you can see here, there is no builder, there's nothing that regards compilation or anything else. This is a clap circuit, if you want to call it a clap circuit. This is a lean circuit today that clap can compile, okay? I'd rather say that. You can, of course, you're not limited to using field elements. You can use the structure that you have in lean. So this is just lean. This is not something that we defined. And as long as you use something that is bounded. So they have to be vectors of a known size. What things that are not in the subset? Well, again, no lists. No, you cannot return something from a circuit. It doesn't make a lot of sense. And there's a little some more subtle things. Of course, you cannot branch on an input and say, in one case, I'm going to do a huge circuit, and in another case, I'm going to go a small circuit, okay? But these are not limitations of clap. This is limitations of circuit. These are not circuits to begin with, okay? So there are a few gotchas when you write these things. Okay, so just I want to underline the fact that there are no constraints and there are no witnesses yet, okay? So when, for example, E0 in this case, it's a basic construct for us, okay? And the definition of E0, I'm very sorry there is a monadic arrow here. This is a limitation of our pipeline right now. This should not be monadic. Like E0 is a pure function, and the definition is exactly what you have in your head. If the expression is 0, then 1, else 0. Okay, that there is nothing. This is the definition of E0 that is used here. And the point is that this is a function that returns a value. So there is no inverse, and the B is an output, is not an input that you're going to put in a relation. Okay. All right. So now that I have my executable spec, I can of course execute it, so I can test it, or I can go a step further and I can try to prove that indeed my check add is the same as the lean addition. Okay. And again, the important thing here to remember is that this is as simple as it can be. Like clap is not adding anything on top of it. I'm going to repeat it again. So a circuit sort of coincides with this denotation or with its executable specification. There is no state mono, there is no constraint system, no witness generation, there is no embedding, and there is no evaluation of that embedding. Okay. This is the thing that I expect the user to write. So these executable specifications, and then the rest is going to be derived. Okay, just to make it extra explicit. So to have a look at the architecture. So now we're going to look what happened after you wrote that. What is it that we're doing? So there is a first phase that I call the front end. I don't know, to make it sound like a compiler, where we are reducing the circuit to basically a list of very basic operands, like the E0, for example, or EQ0. And then once we have that, then there is the part where we split. We produce a constraint system and a witness generation. And so this part is, for this part we have a complete equality. So for this is done using the lean simplification framework. So we have proof of equality that is basically done for free by lean. And then from here on, we define our own properties of soundness and completeness. I'm going to explain more, but just to give an overview, we prove that the constraint system is sound with respect to the reduced circuit, and this is our refinement. Okay. While for the completeness, we prove that if you take the constraint system and the witness generator and you put them together, you use them together, then they're perfectly equivalent to the circuit that you wrote at the beginning. All right. So so let's go in the front end now, and let's see what I meant with simplifying. So this is so the circuits that I gave you before, they were very simple. Sorry, this is a bit more of a more interesting example. So what if there is some control flow that is not obvious, like here, for example. Here there is a little loop. I can fold. and I want to check that all the elements of a vector are 0, and I want to accumulate this. So this, like off the top, like here on the spot, I wouldn't know maybe how to translate it to constraint, and I don't have I don't want to write an algorithm that is going to do that. Okay, what I can do is I can just use the sim framework from Lean to actually reduce this into this form. And so what happens is that a critical thing. So for many simple things, they can just be reduced. It's not that hard. The key ingredient is to notice that the vectors. We know the size of the vectors. Okay? If we know this, we can write some simprocs that are going to explode them into things of known size. And at that point, simp can really simplify all the way down. Okay? And it can give us this completely unrolled and flattened version of the circuit. Again, these things, we mark them opaque for simp, so that it's not going to go in. So for them, at the level of the circuit, we have, like I said, the very intuitive and simple definition. So if the expression is 0, then, but this, we're going to compile them later. We're going to transform them into something very different in constraints. And so we don't want them to be unfolded and unrolled. Okay, they need to remain little black boxes so that we can do our own transformation later. So what we get here is flat linear sequences of black boxes. Okay. And this is, so this step of reduction is currently the bottleneck that we have. The thing that we need to try to make to scale to reach the size that is required by Aptos. And okay, I'm happy to talk about this. This is not a sort of a secret sauce. Like, I'm happy to talk about this. It's just that it's very technical and very Lean specific, and I don't think everybody's going to care. I'm going to skip the automatic optimizations because so far we haven't done a lot of work on them, so I don't have data to substantiate my claims. But I mean, we are planning to recycle some of the old optimization that we did in previous versions of CLAP and see if they're as effective. They were over Plonk, so the question mark is, are they going to be as effective on R1CS? We'll see about that. So we can go in the back end. So right now, what you will find in the code base is FOSS representation. So what we're trying, we go down to a deep embedding that is higher order. So we transform the reduced circuit into this parametric higher order abstract syntax, which is something from that I think Adam Chipala is the most prominent user of this and that has popularized it. And the idea, so this is a higher order representation. So it simplifies a lot of things, like working with bindings. It can be very cumbersome. So this definitely helped a lot. I'm not sure this is going to stay in the future in the sense that it's a bit tricky to use, and I don't think it's going to scale to so it forces you to work in a sort of a CPS style, which is nice for some things and very annoying for other things. So I think the plan is to move also this backend to become a meta compiler. Okay. But it's not done yet. So the theorems that we proved are over this FOSS syntaxes. So because it's a bit unreadable, I try to write an example where this is what we would do with the new meta compiler that is not written yet. Okay, so this is vaporware. Okay, but there is a one-to-one mapping, very simple, from the FOSS syntax to this. It's just that it would be impossible to go through in a presentation. So to give an idea, an intuition of what happens is that so this is the same reduced circuit that I showed earlier that was unrolled from the fold. So what we do is very simple. So each is 0 is exploded into 2 constraints, which is what you expect. So one is here, one is here. And then the EQ0 was already a constraint, so we don't touch it, it stays the same. Of course, like at the beginning, so this function, the original circuit used to take 2 inputs. Now we still take those 2 inputs, but we need a bunch of extra stuff. So there are these 4 extra inputs that correspond to these 4 guys that we don't know how to compute. So I expect somebody to give them to me. Okay, otherwise I don't know what to do. And that somebody is going to be of course the witness generator, which again is going to compute the result and the inverse. The result and the inverse is going to put them in a list or a vector, and that's what's going to be produced. So I think this is not surprising in any way. But this is just an example of how the pipeline continues. And so what is that we proved over this? So again, soundness is I'm going to repeat it even if it's boring or obvious. So the point is that we want the constraint system to not be more accepting than the circuit. So if you give me a garbage signature, if the constraint system says, yes, this is great, and the original circuit said, no, this is a garbage signature, then we have a big problem, okay? So it cannot be more accepting. It can be less accepting, okay? So a constraint system that always fails is very safe. Not very useful, but very safe. So the problem is that so you saw earlier, the original circuit took 2 arguments, and now the constraint system takes a bunch more. It took like, what was 6, right? So how do you compare a function that takes 2 arguments with one that takes 6? So the intuition, the way I like to think about this is using simulations, or what is used in, I don't know if you're familiar with compilers, how you prove equivalences of compiler passes usually is with simulations. So if we try to imagine this as a label transition system where a function is going to take an argument. This is what you see this is the event that you see, and it's going to step to a next state. And then it takes another argument and step to a next state. So here we can imagine this is the circuit and this is the constraint system. They will take the same argument and they will step, and then there will be a problem at some point because the circuit doesn't need auxiliary arguments. It can compute its own. While the constraint system is going to need some help. It's going to need an inverse, for example. So, and in this case, we need to we cannot force them to work in lockstep. So it cannot be a strong simulation. It has to be a weak simulation. So we need to allow this guy to step while the other one is waiting. Okay, this is to give you an intuition. In practice, the way this is written is as a relation and is a relaxation of functional extensionality. So you can see that just receiving an argument and stepping into a state that is still related, it's just what functional extensionality does. So we just need to relax it on asymmetrically on one side. So one side can step more than another. Okay. And so the other modification relaxation that we need to do is the fact that at any time the constraint system can fail, and there is no problem. And actually it must, in the sense that, so in the previous case here, let's imagine that the constraint system is waiting for the inverse, okay? It gets the right one, it actually gets an inverse and can step, and we can continue. But it has no guarantee that it's gonna receive the real inverse. Maybe it received garbage. So in that case, the only thing, the right thing actually to do is to stop and to halt, okay? So in a sense, we need to allow it to fail, otherwise it cannot possibly be in the relation with the circuit. So these are the two relaxations that we do of functional extensionality to prove the soundness. And like I said, we can always cheat and say that CS that never accepts is sound, and so that's why we like completeness. We would like to make sure that it actually does something useful. And so this property, it's actually simpler in the sense that if you take the CS and so the constraint system and the witness generator together now, and you put them, the one that we produce, and you use them together, then they're completely equivalent to the circuit that you start with, okay? All right, so just a final word on Aptos and the work that we did. So like I said, so Aptos keyless is a fairly complex protocol. We only focus on the circuits that they have. So the statement that is, frankly, is a simple part compared to the rest of the story. But the statement itself is pretty complex because it has to work over. Again, the main problem is that you need to work with the objects that come from another tech stack. So you have whatever Google produces a JWT, and it's going to be JSON, and you need to parse this JSON. There are a bunch of tricks and attacks that you can do in parsing this JSON, so this is expensive and complicated. It's also pretty hard to actually to formalize, so we're trying to really find ways to how to explain this in a terse way as a specification. And then there is the problem is that if they're going to sign something, it's going to be signed with the SHA-256. So now you need to deal with SHA. And if they sign something, it's going to be with RSA. So this adds quite a bit of complication. So what we did was again rewriting the full relation. The statement has been completely rewritten in Lean, and we have we proved the soundness and completeness of the gates. So there are a few basic, very ridiculous gates that are needed in CLAP, and those I proved sounding complete pretty easily. I'm very proud of that. And then the hard stuff like the binary decomposition and the multiplication modulo large prime, this is mostly Julian's work, and the first one is completely done, and the second one is mostly done. And he actually found also probably, I want to jinx it, but an optimization to reduce the number of constraints needed for this. So this is pretty, I consider this done. And then there is a lot of work left to do. So for now, we can only test our circuits. So we still need to prove something more interesting about them, about the functional correctness of the circuits, and of course, extract them to something that I can fit to a cryptographic proof system. That's it. Questions?
Yeah, yeah. I was curious, or I didn't get the part where is0 was compiled into something that is non-deterministic or that uses a witness, or at all. I didn't get at all how you do this automatically. You know.
So the point is that you can. Okay, so in the current implementation, this gets transformed into a deep embedding. So I have this FOSS syntax that represents this, like it's a mapping one-to-one. It's not, there's no transformation. It's just a bit uglier to look at, okay? And then I can step through that. So I have constructors for each one of these guys. So I can step through them and I can say, okay, whenever you see one of these, you actually produce 2 of these, okay? That's all there is to it. I would like to write meta programs to do these steps. So the meta programs in Lean, you basically can look at this as an expression. So Lean can inspect its own syntax. So I would just say, let's go to meta. This is now just an expression. And if I navigate the expression and it turns out that I find one of these guys, that a particular function application that is called 0, then I will replace it with the, so it's a very mechanical process. That's it. There's no, and the same thing for the witness generator. You just generate the does it answer?
Yeah.
Oh, okay. I can repeat the question.
Yeah. So I have 2 questions actually. One is if you have any plans or intentions to expose witness hints to the circuit.
Witness what? Sorry.
Witness hints, like the ability to inject the witness value into the circuit to the circuit authors.
Okay, so that's a good question. Sorry. Why for RSA? In which case, I don't know. The thing is, okay. Let me answer the question, and then I can. The thing is that you can already do this. So you saw there is an EQ0. So I can check an expression. Okay. So whatever you want to. So this is basically correspond. This is all you need. So I can take an input, and I can check that corresponds to something. Okay. This is how you do this. So maybe I don't know if it's clear for everybody, but the point is that there are the main trick that you do in circuits is that some things are expensive to compute. And so you just ask for the result and you check, and sometimes it's cheaper to check just the result, okay? So which means that I can transform any function that takes one input and gives you one output. I can transform it in a relation, becomes a relation. So you have 2 inputs and no output, okay? Do we agree on this? The point is that every time you do this trick, you get in trouble, and you need to prove soundness and completeness of this thing, okay? So you can definitely do it, but you're basically, I would be moving the responsibility of soundness and completeness to the user, okay? So you can totally do it. So you can take I can write now a circuit where you give me the inputs, and I check them for you, but then if it is sound and complete, it becomes your problem, and you need to prove it as an extra property. So this approach in CLAP, is basically saying, I'm going to take your whatever it is that you need to do. I'm going to make it a gate. I'm going to prove soundness and completeness for you. Because, I mean, the point is that, in my experience, this does not happen every 5 minutes. There are a few very important cases that you need to deal, that sort of hot paths in a circuit where you really need to do this, because otherwise performances are completely, some things are impossible. But there are not a million of these cases. So you write, so for example, for the whole keyless, we had the 2 gates that I showed. So one is num2bits, which is kind of obvious, and the other is fbmul, which was a bit more annoying. And that's all we needed to make everything else work. So we proved soundness completeness of them, and then that's it. So you can absolutely do that. It's just that you're pushing more problems towards the user.
No, but like let's say I'm a library author that like I've come up with with a new subcircuit that I would like others to be able to use, and like this actually happens. Like
Sure, all the time. Like if I try to verify something that is not keyless, I'm gonna find new. I don't know. Sometimes we call them oracles. You will find more of these guys for sure.
Okay, so like, how do I express this nicely in CLAP? I guess is the question. Like,
So
as a library author, like, what's the API that I expose?
Exactly. So this is another motivation to. So right now in the backend is an embedding. Okay. So I have like maybe I should have answered better your question. I really there is actually an inductive where I say case 1, case 2, case 3. I have my constructors. Okay. So I can write a compiler that goes through them and compiles. The problem is that if you come up with a new thing that you want to use, I need to add a constructor in there. And I need to explain how to compile it. And this is it can be, I mean, it's not very extensible, what I'm saying. Like I need to extend the language sort of for you. While with the meta compilation pipeline, if also the backend is meta compiler, then it's much easier. If you give me 2 definitions and you give me a proof of the proof of soundness and the proof of completeness, then I can plug them in pretty easily, and I can extend the compiler for you and compile your case. And you can also say, I don't care about completeness. You don't prove it. Okay, so like the overall guarantee of the compilation pipeline is weaker, but I mean maybe it's okay for your case. Yes.
So the compilation is done by metaprogramming, and when you do the compilation, does the metaprogramming also generate a theorem proving the refinement relation? And then this happens every time you do a compilation. So there is no general theorem for like, it's not a verified compiler, but it verifies itself every time you compile it. Okay.
Yeah, it's a proof generating compiler. Yeah, I don't know why that is particularly useful. I mean, the point is that this is sort of comes from, so for the front end, this comes from Lean. So because we applied the simplifier, applying the simplifier is just basically applying a bunch of lemmas and theorems repeatedly, and they carry their own proof. So this is simp at the end of a run is going to give you a large proof of all the things that it used. And then for the backend, basically there will be, if we do it in, so right now there is a theorem that says, because right now it's a concrete path. So it's a function that takes the reduced circuit and produces the constraint system. And we have a theorem that says, if you apply this function, then you get the soundness property. Okay. So these are just proved over the correctness of that function. If I were to do it as a metaprogram, then the metaprogram would read the circuit. It would write a constraint system, and then it would also write a proof that it were connected. Okay.
You mentioned that it's invalid if like you branch on secret data or something like that. Since you have a meta compiler over just like Lean ASD, have you thought about adding checks that like the user does this by accident?
Yeah, that's a great question. So right now what we do, we have a type class over the field so that we can abstract. So for example, you don't have this decidable equality. So if you Lean is going to tell you like, no, this if is not, the guard of this if is not okay. So it's not even that we don't compile it. Lean doesn't let you write it. This is sort of, it's not clear if we're going to keep with this because basically so having a type class that abstracts a bit some things gets a bit in the way of proving, because every time you want to punch through the abstraction to do proofs, you sort of have to say, no, by the way, I have an instance of this, or you can open it in this way, unfold, unfold, unfold. So this is a bit inconvenient. We could write, like you said, in Meta, we could just write a linter, something that goes through your code. As you write it, it's going to give you a warning, like, are you sure you want to write this? This we're not going to be able to compile. So great suggestion.
I just want to add 2 small things. It's not actually a question. I just wanted to add that for a bunch of small circuits, particularly relating to the parsing, we've already actually been able to formally verify them, just as a small point, because that wasn't made entirely clear. And the other thing is, thanks to Leo's recent work on the simulation monad stuff, symbolic monad, sorry, rather stuff, we very much expect that the meta performance issues will be resolved shortly. Sorry, I hope you don't mind I added that in.
No, I didn't want to nerd with too many details about sleep. But yeah, no, absolutely. We're one of the first users of SIM-M.
The signal shot stuff is all using SIM-M as well. So there's some integration with, so MVC Gen is going to use SIM-M and Loom 2.0 as well. Yeah, it was Ineos uses MVC Gen. That's the link. Do you want to switch over?
Yeah.
And then I guess there was a point about RSA, but it's I guess it doesn't matter too much. Yeah, seems to work. I think I'm standing next to you, so I don't know. Maybe not. I mean, this still works.
Yeah. Does it work? It works. Nice. All right.
Okay, so Gregor is going to set up. So Gregor will be the last talk of this session, which is about clean, which I guess they've been working on for over a year now at ZK Security. And I think there's some VS Code in this presentation.
Might be.
Might be.
If there's time.
If there's time. I think there is time. After that is coffee, so there's time.
Cool. Smooth. Yeah, hi everyone. Thanks for the intro. So, yeah, we've been working on this since 1.5 years, and it's kind of related to the 2 talks before, but I think there's a large chunk in this talk that is about like extending circuit DSL into something that covers more, and so I think I'm going to focus a bit on that because it's kind of a new thing. So that's why it's called from verified circuits to verified CKVMs. So here's the hello world of a circuit DSL. The is0. So this is clean in a nutshell. It's embedded DSL for CK circuits that are verified. So there was this idea from the start that we want to. It should not be like a verification pipeline, but it should be a circuit front end. So I wanted it to look nice as a circuit front end, and it should also kind of force you into verifying your circuits correct. So it's like that's why we bundle everything together. There's with every formal circuit, you have like the circuit here, and then you have your soundness and completeness to fill in at the bottom. So it's the state monad kind of circuit DSL, I would say. As you maybe see, then it gives you these like what was called a post condition before. You fill out a spec. There's also a precondition that you don't have to use, and then yeah, and then we also have a bunch of automation to make these like easy to prove. So a core tenet that I had is that if your circuit is simple or trivial, or the statement that you prove is trivial, then the proof should be trivial. It should, like, also you expressed, Marco, that you shouldn't have to worry about the boilerplate of the state monad or something. You should just be thrown into your mathematical statement And if the mathematical statement is easy, then grind will get rid of it. So that happens in these proofs. Yeah. So maybe I'll also give some history on where I'm coming from and why this project looks like it does. So I've been working on sort of circuit DSLs for 5 years, I think. So I've been working on something called O1JS for over 3 years. Put a lot of energy in that. So at that point, I also already had a lot of like hard-won experience, and I really liked this project. So if you're, I think we see this in our ecosystem as well, that if you invest a bunch of energy in some ecosystem, then it's kind of weird to start something completely new. So for me, this was like when I started this, another circuit DSL, it was kind of clear that this would be my last one, you know. Because yeah, I'm not going to start from scratch another time. So this one kind of has to be perfect for me. These things that I put on this slide, they represent pretty strong opinions that I have about what it is required to be perfect for this circuit framework. So I put 2 chilies there for 2 parts that are different from my previous talks. But yeah, we all agree that it should like look nice. That's one thing I gained over TypeScript. Now in Lean, it looks like mathematics. I can do plus and not dot add something. Much better. It should have good PX, proving experience. What we saw before, like a nice tactic. Yeah. Thanks. Is it better? Okay. So I very much strongly believe that what I build has to be low level, and it has to talk about constraints, and it has to give you a witness command and so on. It definitely not going to be compiled. I think, but that's just a different I think use case for circuit DSL. So it's my thinking is that for many programs you want a compiler to not think about like assembly at a low level. Circuit is kind of an assembly, but for very precious programs, the assembly is really you want to be able to program in assembly, and because it has to be as efficient as possible, and yeah, you know. And I just want to target that direction. I want to target a ZKVM that's implementing core infra, and they will write their circuits by hand, and they will not use a compiler to create a compiler, so to speak. So then the next thing we kind of all agreed on, I think, it should be like general purpose. That's why we write it in Lean. That's why it's not Circom, where you're passing 3-dimensional vectors of signals from the very starting point through to all the, I don't know, circuits. It should give you nice abstraction capabilities. You should be able to define higher level types that are kind of circuit types and so on. So, and you should be able to define loops and so on. You should be able to use the full power of Lean to write your circuit builder. And then the other chili is that it should definitely model completeness, and it should have proof of computation, so which is different from ZK-Lean, I guess. Yeah. Because we'll come to that later. So and the non-goal is that it kind of abstracts circuits away and make them look like normal programs, because circuits are an interesting model that I want to preserve. Okay, so that was the part about connecting to the other projects, I guess. Now I want to describe roughly like the basics of clean to prepare you for the rest. So, but I will keep it short. So a circuit is a function from this number, doesn't matter too much at the moment, to like basically a list of operations. So it's basically a circuit is a list of operations. And an operation is either a witnessing operation or an assertion, like that's the equal constraint, or a channel interaction, or a subcircuit. And a subcircuit is actually just, again, a list of these three. So it can be nested, and nesting was important for scalability, basically, so that we can compose circuits and not reason about the whole deeply nested thing every time, but kind of stop at the subcircuits. Yeah. And then, for example, we can define what constraints mean for each one of these these expressions. We have that the expression evaluates to 0. So it's a zero check. That's what it means that the constraints hold. All right. Maybe I can have some water. Yeah. Okay, thanks. Thanks. Soundness and completeness is not surprising. We have sort of preconditions, then we assume that the constraints hold, and then it follows that the postconditions hold, and this is very rough, but importantly, the assumptions and the spec are about the inputs and outputs of a circuit, and the constraints are about everything in between. So we kind of want to abstract away, looking from the outside, we want to abstract away all the things that happened inside a subcircuit. We only want to talk about inputs and outputs. Yeah. Okay, now when we started out, we basically had plain constraints, what we saw before, and we had we wanted to model lookup tables as well, because all of the real circuits use them. So we had some weird lookup operation as well, but it wasn't very nice, and we wanted to model it properly, the whole concept, and that's what this talk is really about. So we started to think about what's the common abstraction, or the best way to represent all of these different multi-set equality arguments in a circuit DSL, which should cover things like lookups, the Planck permutation argument, and also all kinds of cross-table interactions in ZKVMs. So maybe prior work, or where this comes from. So there's this concept of there's kind of an architecture for ZKVM that the industry kind of landed on. There are similar across different projects. So in Cairo, for example, like in Starkware, they call it flat air. In Binius, they used to call it M3. OpenVM calls it air with interactions. So the concept is you have different tables. We call them components. And these tables, they basically use one row constraints. So the old VMs, they used like adjacent row constraints every time. But nowadays, we have a circuit on every row. And the only way that two rows communicate with each other is with channels, with these multi-set relations. So channels mediate both between rows of one table and between different tables. And then there's a sort of channel balance that is proved as part of the proof system. So we prove for every channel that all the elements added to it cancel out. So it's a multi-set zero check. And also interestingly, typically a ZKVM like that has there's a channel that becomes a central point of the whole system. So we used to have VMs where there was a CPU table, and that was like the core, the central point. And the CPU table used other tables to spawn out computation. But the whole trace was in the CPU table. And nowadays, we have multiple tables that share the trace, and the thing that holds it together is the state channel, the VM channel. So we have like the add instruction will have its own table, and the multiply instruction will have its own table, and they will both pull from the state channel, perform a transition. The add table will perform an addition. Depending on the opcode, we will use a different table to perform a transition, and they will push back to the channel their result. So that's kind of, it seems to be more efficient that way, I guess. How am I on time? This was about a third, maybe. So yeah, I prepared like I worked for a couple of weeks or even months on an example that I tried to make like a toy example, but still representing the whole thing I want to model in its generality. And that was this Fibonacci example. So just to recap, I want to show you the components of it. So we have 3 tables. One is like a classical lookup table, which has bytes in it. It's a range check table where you can check that your element is a byte. Then we have an addition table. So this is Fibonacci on 8-bit numbers, and it stays in 8-bit numbers, 8-bit Fibonacci. Okay. So there's an addition table which pulls an element from the bytes channel, which means this is a byte, which will be the result. And then it will constrain this result of the addition to be the sum of two of its other inputs, the sum modulo bytes, and then it will push, it will emit to this addition channel. So there's one table there's one channel that's consumed, the bytes channel, and there's one channel that's the output of this, the addition channel kind of. And then there's the Fibonacci table, which is sort of like the VM here. It performs a state transition. It pulls from the Fibonacci state channel, performs an addition by also pulling from the addition channel and pushing to the Fibonacci channel again. Is that kind of clear? So these yellow boxes is what we would call the component or a table, and the blue things are channels. And yeah, there's sort of a hierarchy here, and there's a main channel, the Fibonacci channel, and these are the ingredients I think that we find in ZKVMs basically. There's slight generalizations of this, but this already gives you a good implementation of a ZKVM. And then, I should not forget then, there's like a public input and public output to the whole system. And in this system, that's typically like an initial push that you perform to the VM channel and a final pull. So you push like the beginning state that might be a constant, like your constant, like 0, 1 Fibonacci starting state. And at the end, you pull out the final result of the whole computation. That's like your public output. So the problem with modeling channels in a circuit DSL is that your soundness of we have three circuits here, right? We want to treat these like little things that are self-contained. Like the addition shouldn't really know about this whole ZKVM structure. It should be just an addition gadget. But it needs this property that this output value is a byte. It needs the range check to prove its own soundness. So it relies on something that cannot be checked by local constraints, because ultimately the fact that this output is a byte comes from some global multiset check, which we can't nicely represent in this local circuit. That's a problem. So we want to, yeah, I keep it at that. So a first obvious attempt is that we just associate some property with a channel. We just have this structured channel, and we define this function from, it has some type, some message type, and then we define an arbitrary property that is the guarantees that you get when you take something from the channel. Yeah. So for the bytes channel, this would be that the message is on a field element that's smaller than 256. So there's an arbitrary property, and then in your soundness proof, you just use this new statement, where in addition to your constraints, you also assume all the guarantees from for all the pulls you did for any channel. Okay, and that's basically what our initial lookup operation was. Just kind of get it working, you know? But I wasn't really happy with that, because this guarantees property can be anything. It's not anchored in anything else. So, for example, I have this. I could define this very dump channel, which has the property false as its guarantees. So every time you pull from the channel, you obtain the property false. And so you you can define a false circuit where the constraints of the circuit imply the statement false, which is sort of frustrating, right? And it's sound, you know, according to our definition of soundness, this is easily proven to be sound, because it assumed the false statement. So not happy with this. So it would be better if we at least model both sides. If you pull, you get the guarantees, but if you push to a channel, you have to provide the guarantees, right? You have to, if you push to the false channel, you have to prove false. Okay? So you can't really push to it. That kind of gets us towards modeling the whole system, where some tables will push to some channel and other tables will pull from it. And then there's this grand vision, of course. So now we want to write many gadgets that maybe some of them pull and use this, some of them push, and then we want to combine them into an ensemble of which is an air or a multi-air, a flat air, and then once we have assembled everything in the right way, I want us to get rid of all the assumptions that we made and actually prove a real soundness theorem. So we want to prove global soundness, which when you have the assumptions that all the tables need and the constraints that all the tables produce, then you add an additional, basically a global constraint, the channel balance for all your channels. Then you can directly prove the spec. You no longer have these ugly guarantees. So the guarantees were kind of just a little helper device to get you there. It's like sometimes when you prove an induction, sometimes when you prove a statement by induction, you make the induction hypothesis stronger than the output, because it kind of smoothens the way to proving the output. And that's very similar, I think. So with this setup, if you can prove this, then your guarantees can actually be anything. There are no restrictions, as long as they help you prove the local circuits. And since you get rid of them in the end, they don't hurt you, right? So how did this work out? Why should this be true? So channel balance means that for every pull you do, there has to be a push. Otherwise, you wouldn't have balance. No, if you would only pull from a channel, then it would just be all multiplicities minus 1. So our balance condition actually has an extra condition that the number of interactions are smaller than the field size. So it can't, with a lot of -1 multiplicities, you can't underflow. So balance actually is structured so that it implies that for every pull, there must be some push somewhere else. So for that push, we had to prove the guarantees. And so that's why we also have the guarantees for the pull, because they're the same message, so it's the same statement. Right? What can go wrong? Okay. Well, we had these guarantees of the push came from somewhere. They came from another circuit, but that circuit also had some assumptions that it made from some other pull that it did, probably. So it's not that simple. There are simple cases, though. There are cases where we have a strict hierarchy of channels. You know, the first channel doesn't pull from anything. So that's already the next slide, a simple case. We have a list of tables in some order. We have to say what the order is. And we require that for every channel, or for any channel that participates in this argument at least, the tables that push to the channel have to come before, and then the tables that pull from the channel have to become after. And no single table can obviously pull and push to the same channel. So that gives us kind of a way to prove this thing by induction, because the first table is like a base case. It cannot pull from anything. So its pushes are unconditionally carry their guarantees. And so in the Fibonacci example, we kind of have a partial hierarchy. The bytes table pushes to the bytes channel, the add table. So from that on, the bytes channel is no longer pushed to, only pulled from. Then the add table pulls from the bytes table and pushes to the add channel, and from that on, the add channel is no longer pushed to. Okay, so these channels are done. And now any table can pull from these channels, and it's fine. And we proved this, we formulated this ordering in a way that can be easy to prove, like for the user. And that's what we call is sound channels. And then the theorem is that the interesting soundness theorem, which is table soundness, follows from sound channels. Which means that all the guarantees for these channels, even in the Fibonacci table, we can deduce that all the guarantees for these channels are satisfied, even though the Fibonacci table doesn't fit fully the hierarchy. So now there's the harder case. What do we do here? So we have these nasty VM channels that are pulled and pushed to from the same table. So you can't always prove what we want. What do you mean by that? So I thought, I didn't think about this too hard from the beginning. So I thought I would prove this table soundness for every table, for every channel. We will prove that all the guarantees hold, but that's not the case in general. So in a VM, we can actually, there are many VMs that support transitions that loop. Like one transition, there's a couple of transitions that end up where they started. You want that if you have a real VM, you want to have the capability for infinite loops. And so you have closed cycles, and if you get a proof of a VM trace execution, in practice it can contain such cycles that that's not ruled out by any of the proof systems that I've seen. And in these cycles, you have the guarantees. They form a cycle of implications. There's no base case where you know the guarantees actually hold. One transition assumes some guarantees and proves some other ones, and it goes around. But in general, we don't know that any of these hold. So that was disappointing to learn. Yuichi kind of immediately noticed that and pointed me to this. That yeah, there can be cycles. What do I do about this? Yeah, it's sad. So, but in fact, it's not that bad. If you try some time, you prove what you need. Because in the end, we don't care about the cycles. We just have to formulate a soundness statement in a way that we care about it. So the public input and output of a VM is this initial pull and final push, the other way around, sorry. And they can't be in a closed cycle for reasons. Okay, so because if the final pull was part of such a infinite loop, the balance doesn't work out. There would be a loose end. So from the construction of the thing, you know that the initial and final thing are actually part of the same path that has a beginning and an end. And it's a nice soundness statement to say that if you assume the guarantees of the initial push, it follows the guarantees of the final pull, right? So that's basically, typically this, the guarantees are there exists a VM trace that leads to this state. And this is what we understand as soundness for a VM. We get the statement, there exists a valid trace from the initial to the final state. Okay, so the proof actually goes through, and I have a. This is a pretty long proof. I have a nice argument in Lean for this, which doesn't talk about cycles at all. It's just an induction that just works. Maybe I can show you that later. How are we in time?
Coffee break is in 20 minutes, so you have.
Cool. Yeah. So, without further ado, here's basically my main result. Assume I already defined these Fibonacci components, and I proved them sound, and it's not very hard. Then everything I have to do in addition to prove the end-to-end soundness property that I promised is these 10 lines of Lean. So that's because the things we assume about the things we have to assume about these components are very simple properties, like you don't pull from that channel, or you don't push to this channel, or in the case of VMs, we have to know that all the pulls and pushes are -1 or +1. Or no, that's exactly 1, -1, and 1 +1. So it's all it's all just simple properties of the channels, how these channels are used. So all of these just proof by simp, and here you see two of these proofs in one line, and here you see 2 proofs, and here you see more, and they are all about using our sim set, our custom sim set, which is called circuit norm, and then unfolding definitions in addition to that. That's how it's supposed to be, I think. And if you're at that stage, you could actually write some automation to just unfold the definitions and just get rid of the proofs altogether, of course. That's just an exercise. So you don't have to do any proofs on top of your local circuit proofs. Just combine them in the right way. And combining in the right way, I mean, it's here. So we add, I mean, that's the main thing. We add the tables in the right order. We add first the bytes table. Then we say, okay, now this channel is finished. We add another table. We say then this channel is finished. We kind of tell it the right hierarchy at the beginning, and at the end there's the grand last step where we add all the VM tables at once. And that works on top of the existing hierarchy. Yeah. Cool. Where am I? Okay, this is. Yeah, maybe just to show you how kind of the final thing looks like. So this is kind of the main theorem of the. So this is where I did this was of combining all the components, and then just to prove that this is actually an interesting statement, I wrote it out here concretely. So if I take this Fibonacci ensemble and assume the statement, so the statement is kind of what the ZKProof is supposed to give you. Like it's the channel balance and the constraints. So let's look at the statement to be convinced this is not some garbage. Statement for an ensemble is there exists a witness, so that the public input of the witness is what goes in, and the constraints hold and the balance channels. Probably. Okay. I don't know if that was convincing. And then if you assume the statement about this number n, x, and y, then essentially x and y are the output of Fibonacci. So it's a bit ugly because I have to avoid the overflow, kind of avoid the overflow here. So that's for me to fix. It needs more theory in this framework, kind of. But yeah, we actually can directly prove the interesting relation from the statement. So that's cool. So a little interesting after observation. Why is completeness also important? So yeah, I should show you this in code. So let's go back to this grand construction that I was so proud of. So we would expect that. I mean, what if I comment out the bytes channel at the bytes table? It works. It's still sound. If I also remove the addition table, it's also sound. So interestingly, kind of the assumptions that the Fibonacci table does, they come out of nowhere in this case, sort of. Why? Because the fact that there are tables that fill these channels, this is a completeness property, not a soundness property. Okay, so in this case, we just have a meaningless channel balance condition. The channel balance could never be satisfied with this setup because there's no table that pushes 2 bytes. So okay, if you have a trivially false assumption, the channel balance, we can prove whatever we want, obviously. So kind of unexpected for demonstration's sake. I also proved the false circuit that I showed before to be part of a sound ensemble. So for the same reason, because you just can't push to this channel, so you just can't have channel balance. So the false. So I motivated my whole talk with the fact that we don't want to have these stupid circuits, but in fact these are still sound end-to-end systems, just not complete. And that's why proving completeness is a very good idea to avoid meaningless soundness proofs. All right. Okay, that was fun.
Thanks for talking about this topic. I met this at Maiden. They called them buses. I think it's a good name, but I mean, it's exactly what you. And I was really learning about this, and I was a bit puzzled that you can push, but actually you can pull before you push, and so it's a bit unintuitive. This is what you so that. When things are to be pushed before being pulled, that was a simplification that then it was lifted later, right?
I mean, there are basically two different soundness arguments that I established for two different cases that are just disjoint. The VM case was it had assumptions that the lookup table case didn't have to make, and the lookup table case had assumptions that the VM case didn't have to make. So so it's a bit abstract without seeing all the theorems, but this case of doing both pushes and pulls, it works under the condition that it's just one pull and one push.
Sure, that they need to add up at the end. Okay.
Yeah.
Okay. And so the other thing is, so does this become a sort of trace property in the sense that you need to unroll the whole thing before you know if, so that it sort of removes a little bit of the local reasoning that you can do, right? The fact that at some point, I don't know if up to here we're good, because maybe I'm pulling something that somebody's going to push later. So unless you unroll all the trace, like you can never be sure if everything is okay. Was this a problem, or is just?
Yeah. I mean, this kind of permeated through all my work. For example, I introduced a relaxation of this balanced channel assumption, which is to say the channel is balanced if we assume that there are more elements coming in later where we already assume their guarantees. So it's kind of like conducive to this sort of induction.
Okay.
Yeah.
Thanks.
Any other final questions? Okay, coffee break. Thank you, Gregor. And then we'll be back after the coffee break. And then we'll also talk about AI.
So everyone, at 4 o'clock, which is in 5 minutes, we're gonna do a picture of everybody together. So if you could all just come to the front of the hotel. And bring your best smiles, guys. I mean, come on. Hello, hello. Yeah, he's getting it. Hello. Yeah. Should I turn it down here? I am done. I turn it. This is LIBRA. See, see.
Morning is already uploaded, just the one in the afternoon, and then I will copy just the last one and we're good to go. Yeah.
Hello, can you hear me?
Hey. Yeah.
1 second, we'll put you on the screen.
I can also share the talk.
Yeah, share your screen, but we're gonna put you, like, I'm gonna put you on the screen in the room. In 1 second. Okay, perfect. Everything is fine here. I'll let you know when you can start when the people are here.
Yeah.
Just a couple more minutes. Before we start, guys, I just want to ask if anybody saw a phone. Let us know, because someone in the conference lost their phone. Thank you. Okay, Kwang, yeah, you can start.
All right. Okay. So people can hear me? Okay. I hope
Yes.
that's good. All right. So yeah, thanks for this opportunity to have basically all of us who are working on RClip to talk about our work today. And so I will round it up by talking about how the foundations of RClip are changing. And this is very much ongoing work. I will try to keep this talk concise so that we have plenty of time for questions. Okay. And of course, this is not possible without all the wonderful contributors to RClip, which I list here, although I'm sure that I'm missing many others. So let me go ahead. Yeah, so the RClip, what I think it's worth to maybe take a step back and think about the context of why something like RClip exists. And the reality is the snarks, as we all know, they're now being used in production. And that means that any bugs that occur at any layer of the stack can have devastating consequences. It can lead to soundness breaks, which leads to loss of money, and so on. So the only way that we know how to reliably eliminate bugs is to formally verify these snarks. Now, on one hand, on the arithmetization or the circuits end, we have many verification frameworks already. And I list some of them here, and some of them I might have not been listed. And so all of that is on the circuit level. What about the protocols themselves? How do we formally verify them? And once you look into the protocols, it turns out that, of course, they have many non-trivial mathematical contents, especially in coding theory. And so as we formally verify these, I think we're also contributing an independent contribution, not just to the snark community, but also to the broader crypto, CS, or mathematical community. And that means that we should be formalizing these beautiful results on correlated agreements, proximity gaps, and so on. And finally, a bit of a historical note is that RClip, as of right now, has been in development for basically 2 years. I started this as basically a side project on my own, and it's gradually grew to be part of the verified ZK-EVM effort since 2025. And just a personal anecdote is that when I first started knowing nothing about Lean, I was wondering, like, how hard could this be? You see all these protocols that people write on papers. You see all these proofs that go along with it. And, well, it's probably not too difficult to encode them into Lean, right? And, well, turns out, as with everything, it's a lot harder than one would expect once we really get into it and try to build a good framework that can capture basically every protocol that we know of. So let me also go to what RClip is right now, and or at least the goals of RClip that we hope to provide now and in the future. And I think we would like RClip to be basically a place where any snark protocol can be specified in a modular way, achieving specifications that are executable. So you can actually run it. You can it can be tested against production implementations. And right now, our focus is on these generic polynomial IOPs, and also on the hash-based polynomial commitment schemes, although these focus may shift in the future as well. The second goal is that we can't just specify these protocols, we have to prove their security. And if we are modularly constructing these protocols, we should also have composable security proofs for these protocols. So it's sort of like going the same way as we build these protocols, that's how the security proofs needs to go as well. The third thing is that we can't just have individual components. We must find ways to glue them together and to compile them into actual snarks that can run in an end-to-end manner. And that means that we need to formalize these fairly complex compilation steps, which includes the interactive BCS transform, where you turn an IOP basically into an interactive protocol. And then you turn that into a non-interactive protocol with Fiat Shamir. So I'm sure everyone in the audience know these transforms, and it is part of ArcLib's goal to formalize these once and for all so that you only need to specify the protocol at the IOP level, and then all the rest go through. And that means, in particular, you would eliminate all kinds of bugs due to the application of Fiat Shamir, for instance, because you start from something that is already interactive and you fully specify them. And this compilation step to snark with Fiat Shamir is a completely generic transform that we prove secure once and for all. And well, finally, we have something in Lean that is end-to-end, only in Lean end-to-end formally verified, but the final part is you have to connect it to implementations of production code bases. And I know this is ongoing work. People are using hacks, I think, among other tools, to extract the Rust code in popular libraries like Plonky3 into Lean, and then formally verify that it matches the specifications in ArcLib. So these are all the goals. These are, I would say, fairly ambitious goals. And it's worth noting what is our progress in achieving these. And in some sense, I would say our progress is non-trivial, but we still have a lot to go. The core of what ArcLib provides today is that we give a framework for specifying interactive oracle reductions. And so a quick refresher on what IORs are, you can see on the right here. You basically have two parties, prover, verifier. They start with some statement and some witness. The statements here consist of two parts, one that is public to the verifier, and the other one is only available to verifier as oracles, with some specified interface going along with each oracle. Now, the two parties will exchange messages. Verifiers' messages are random. Provers' messages are either oracles as well or some public data. And these kinds of oracles are basically, you have vector queries, polynomial queries, and so on. Okay. So that's the general interaction. And at the end, prover and verifier is going to output some new statements and witness. And this reduction viewpoint is basically how we can compose these smaller reductions together to form bigger reductions, and that leads to whole protocols. So it means that now we have specifications of various protocols in ArcLib. Of course, we also need to define these generic transforms. So we have defined the Fiat Shamir transform, and especially the variance that is used in practice most often using a duplex sponge. And we have stated the security properties for them. And finally, we have a large and well-contributed coding theory sort of sub-library within ArcLib. So we have all the important definitions written down. We have proved, we have made very good progress improving some of these, as you may have learned about in Katie's talk and others' talk as well. And yeah, it becomes an important independent contribution of ArcLib in its own right. So this is what we have. What I would like to point out next is what we don't have. And these become, or these are caused by some of the choices when you go into the deepest level of how we formalize IORs in RClip. So let me go just straight to these, I would say, pain points. The first pain point is that if you look at RClip today, the structure of a protocol is fairly dependent. So a protocol depends on the number of rounds n, and then within each round, or within each message exchange, you have who is speaking and the type of that message. So for fairly standard, this is how you would define, say, like a 3-round Sigma protocol. So that's okay. The problem is that you have this dependence on the number of rounds here. And Lean is a fairly fussy theorem prover, as with many others. What it says is that so this is something that's a little bit technical to Lean, but the upshot is that you have to be casting, you don't have equalities for free. Some equalities come for free, others do not. And the ones that do not, you need to provide a non-trivial proof for them. And when you provide such a non-trivial proof, as you can see here, 0 plus n is not definitionally equal to n. It means that you have to be inserting a lot of cast into these protocols. And this is just the cast at the structural level. Imagine the cast that's going on when you specify the provers algorithms, for instance, and then you have to compose these provers. Here's what this composition actually looks like in RClip today. What you should see is that really the main contents are these green boxes that I put in here. But in order to get to these green boxes, you need to do a bunch of simplifications and a bunch of casting. And this has real consequences. The consequences are that it's nearly impossible to prove any theorems about these definitions. So yeah, you can see that here are other snippets in RClip. It turns out we are not able to prove these yet. Perhaps if we try really hard, we can. But this sort of points to a need for better definitions overall so that we don't run into these issues. And so, yeah, even something like a general sum check protocol do not have an end-to-end proven security in RClip today. Because we can specify everything, we can prove the security of, say, a single round of sum check, but we don't have these generic theorems to conclude that the security of the whole protocol is complete and sound. Okay. So that's the first problems with RClip today. The second problem is that RClip doesn't quite support some kind of protocols that start arising in practice. And the problem is, here I give you this definition. It has a fixed number of rounds n, and within each round you have some predetermined direction and the type of the message. This suffices for most protocols, so that is great, but there are some protocols where this just doesn't apply. For instance, you can think of, say, like a ZKVM, where as part of the proof, you send some metadata, say the number of rounds, how you arrange the polynomials, and all kinds of stuff. And then the rest of the protocols, for instance, the number of sum check rounds would depend on these parameters. A second line of work shows that, well, if you if you work for snarks over the integers, what you often do is that the verifier would then send a random prime, and then the rest of the protocol works over that random prime. And so it means that in later messages and later structure of the protocol depends on the values of earlier messages between either the prover or the verifier. So, and currently we have no way to represent these protocols in RClip. The second problem within these larger pain points is that it's perhaps a technical point on how we actually define what it means for this Y2, this output oracle statement or output implicit instance, how is it actually defined in terms of everything that we've seen so far? Okay, so note here that the verifier doesn't see technically what these Y2 are. That's the whole point of them being oracles. And one way you could say, and this applies in most cases, is that this Y2 is simply a subset of all the oracles that verifier sees so far. This works for many protocols, but not for all. If you want to take a particular example, you can think of the batch fry protocol or batch PCS for any kind of PCS, like hash-based PCS. What you have is that the prover will have a bunch of polynomial oracles, and they want to have a batching step where it would send another polynomials that is supposed to be a linear combinations of the ones so far. So that doesn't quite fit with the subset kind of semantics. And just in general, if you think about what does it mean for an oracle family to be defined in terms of other oracles, that gets you into some interesting territory. And yeah, the general approach here is that you say you have access to Y2, it can be simulated by using the public information and using the oracle access to all the prior oracles. And that should be the general way in which this is defined. Okay. The third problem is basically a usability problem. What we have right now in RClip, for instance, when you try to when you formalize the subject protocol, or any protocol for that matter, is that you have to define a bunch of definitions. Of course, you need to specify it. And what the specification looks like is that first, you need to specify the protocol structure, and then you specify how the prover works, how the verifier works, and then you have the reduction, which is just the combination of these two. And when you try to build further reductions, what you do is you do one of these composition operators that we provide, for instance, sequential compositions. So subcheck is a particularly nice example because you just sequentially compose all the individual rounds. But, well, if you look at this, this is okay. I basically didn't expand out all the definitions of the prover and verifier and so on. But if I do, then it easily gets you to a few hundred lines of code. Some of these are inevitable, but if you think about how these protocols are defined on paper, it's a lot more concise. And importantly, what's concise about it is that you can see the full protocol structure and how the prover and verifier interacts within a single definition, like a figure. Whereas here, it is split between prover, verifier, reduction, protocol structure, and so on. And this makes it harder to read for the reader to keep in mind all these different definitions. You have to go back and forth. And of course, this would increase the risk of misformalizations. And it is actually something that misformalizations do occur in RClip, and we have been very vigilant in addressing them. And this is one of the things that can increase that risk, and we should be fixing it. Okay, so those are, I would say, the main pain points that you would see in RClip today, and I would really like to address. So let's try to evolve the foundations of RClip to a place where these pain points go away, and potentially other pain points that I didn't mention yet. So in this quest, well, how do we know if the new definition that we choose are the right ones to build upon? So the definition of right here is certainly subjective, but we can sort of asymptote it by looking around say, not just in the cryptographic community, but you look at programming languages, category theory, game theory, etc., anywhere where people have been dealing with the problems of, say, well, how do you formalize things in theorem prover? How do you formalize an interactive protocols? How do you formalize Oracle access and so on? Then that gives you pretty close to what I think would be the consensus of how these protocols should be defined. So I will just mention two things here. The first thing is that it turns out there's this kind of object called polynomial functors and free monads over them that provide a really good base for specifying both Oracle access and for interactions. And really, they are two sides of the same coin, as you'll see. The second way, the second innovation in PL that we bring or are hoping to bring is that of choreographies. And what that means is precisely the concept that you could specify an interactive protocol in a concise manner using a single definitions that look like the figures that you would see in Stark papers. You have every definition sort of put together in one place so that you can easily see the structure of the protocol and how it is defined. So this is a very active rewrite of the library, and I don't have the full ready version yet. There are some open questions that I think is remaining, especially how these general formulations interact with the particular formulations or of particular compilation steps, say Fiat-Shamir and BCS, and so on. So I think we need to work these things out and make sure that they are the way that we think they should be before we could really supplant the foundations of ArcLib. So for the rest of the talk, I'm going to go briefly into these two things, these two techniques, and sort of preview what the improvements are. Okay, so polynomial functors, what are they? They are really, you can think of them in many ways. The way I like to think about them is that it's just describing a dependent types of protocols. So a polynomial functor itself just consists of two things. One is the type of, say, the head, and the other thing is the type of the family for each value of the head. So here you can see the dependent types is baked into the definitions. This B here is a function that is dependent on the particular values of something of type A. To make it more concrete, you can have the free monad over this polynomial functor. And what that means is you take this structure provided by the polynomial functor, and then you do a sort of free construction or some kind of recursive definition on them. So this, what you should think of is you are describing an interaction tree. At the leaf, you have you can return some values, and more importantly, at each branch of the tree, you can have it can be decorated with a value of the head type, and then you specify what would happen with once you receive sort of the corresponding value of the child family, the child type corresponding to this head value. So you should really think of it as a branching interaction tree where the branching can be determined by the structure of this polynomial functor. This is in fact the viewpoint that we took for this VCVIO library that you may have seen in Devin's talk, which is that this is really like an Oracle computations. You specify this is basically the dependent Oracle type, and then this is you make an Oracle query, and then you continue with the response. For ArcLib, you can reinterpret this as the base for the structure of a interactive oracle reductions. So to be concrete here, I give you sort of an unrolled definitions of how an IOR should look like, at least protocol-wise. You would be instantiating this with a particular polynomial functor, and what it looks like is that it can either be done, or the prover sends a message, and then the rest of the protocol may depend on that message. If the prover sends an oracle, then it needs to come with an interface for that oracle, and then the rest cannot branch on that oracle value because the verifier cannot see them. And finally, for the verifier, it can send a challenge, and then the rest of the protocol may depend on that challenge. So this solves the representation issues that I alluded to earlier on how protocols are dependent nowadays, and this cleanly solves that issue. You just encode that dependency directly into the definition. What this also provides us is that now the prover and verifier can be defined inductively based on just pattern matching on these various constructors. So what this means is that, this definition allows you to have, let's say the prover has some side effects, which is encoded by this M. For those in the audience who know, these are just an arbitrary monad. And the point is, the prover is now just a type. It is not a structure with many different fields. We do not need to provide sort of an implicit state for the prover. We do not need to manage it. We just say, here is the behavior of the prover at the input-output level, at the interaction level. We don't care about its internal. All we care about is that when the prover sends a message, it must send a message, and then it continues with the rest of the protocol. If the prover is expecting to receive a challenge, then it would need to provide output a function that can answer any challenge that it receives. So this becomes quite an elegant type definitions, and it gives you real advantages. On the verifier side, I should note also that it's a little bit more complicated than this because you also have all these oracles going around. So technically, what you need to have is that this monad here may grow after each round to accommodate for the new oracles that the verifier have received. But in any case, the important point here is that when you define everything in pattern matching manner in this way, the sequential compositions that you would write, the definitions of them, they require no casting. They just require pattern matching on the protocol specifications. And the same thing happens for the security proofs as well. You just do the pattern matching, and that gives you a nice decomposition of the protocols. Okay, so that's actually led to quite far. At least what I can credibly claim is that in the branch that I'm developing this, I have proved an end-to-end round-by-round soundness of sum check in a generic manner. Of course, there's some debate here on what is the truly generic notions, and I'm happy to talk about them after this if anyone is interested. But basically, here are the headlines. The second thing that we try to solve is with, well, readable specifications, using this idea of choreographies in PL literature. And the idea is that here you have some protocols you define in this compact figure. Here I take a very simple example of Schnorr. You define the protocol in this way, and intuitively you see this and you know what each side is doing. You can also make this precise via a concept called endpoint projections. It just means that you have this unified definitions. It automatically gives you projections to a full description of the prover and of the verifier. Okay, and we can actually do this in Lean. So with the help of some sort of lean meta programming syntax and macros, we can write something that is fairly, what I would say it's very readable. So the point here is that the flow of the prover and verifier, it's all in one definition. And you can see in each round what each party sends. Here you see the structure of protocol baked into this. You can see what the prover is doing, what the verifier is doing, and you see what happens at the end of the protocol. So yeah, this is how you would, I hope that we could move to a place where we have a very succinct definitions or specifications of protocols in RClip without losing on any kind of generality. And of course, this notation needs to expand further to account for, say, Oracle access, Oracle queries in the IOR setting, and so on. This is just interactive protocol with no oracles. So that's another axis that I'm trying to push on, which is to get choreographies working well for these Oracle protocols. Okay, so let me summarize here. Well, as said at the beginning of the talk, we would really like RClip to have formal specifications and security proofs for all SNARK protocols, especially those that are deployed in productions. And we are making really good progress towards that. We have many active contributors. We are heavily benefiting from the progress in AIs that can now write Lean extremely well. So even if you don't know Lean at a sort of an expert level, it is really easy for you to get started on writing Lean with the help of LLMs. And to support all of this growth, we need to be rethinking and rewriting the foundations of RClip in the right manner. What that means is that we need to make sure our definitions are the right one. And what the right one means is that this must be something that is sort of independently gotten to by people in other communities who have thought long and hard about similar problems. And what that would enable us is that we can finally have end-to-end security proofs, and we have specs that are readable to a regular cryptographer, not someone who needs to know the intricacies of Lean. So this is RClip. We always welcome new contributors, and we welcome existing contributors as well, of course. And yeah, you should check out the library, and thank you for listening.
And questions, please raise your hands, otherwise we won't hear you.
Testing, can you hear me, Kwang?
Yes.
On the Schnorr diagram that you wrote, I think it's 2 slides back.
Yep.
Yeah, so when the prover samples a random number, what is the right-hand side doing? Like the Schnorr, yeah, that part there. What is this?
This. Yeah, it's just like syntax sugar for random sampling. So what this means is that you would choose R independently at random from the whole finite field.
Oh, so when you said that there's no Oracle access here, what did you mean by that?
Oh, right. So the prover here sends an actual message, like it sends this R times G, or like G to the R, instead of sending an oracle to G to the R, for instance.
Okay, thanks.
So the oracle part is like, yeah.
More questions? I guess that's it. Thank you very much. No more questions. If you have anything else to add, you're welcomed.
Thank you.
Thank you very much in this case. Kwang, it was a pleasure to hearing you. Thank you for sharing your knowledge.
Does this work? Yeah. All right, so second talk of this session and last talk for today. We've got Elia from Logical Intelligence. Logical Intelligence is a company that does serial improving for mathematics with AI. And so we'll hear a bit more about this, as it's been kind of mentioned throughout the day. And we'll see what the state of the art is.
Do you hear me? Okay, so hi everybody. It's a slightly different pitch than the previous ones. So I'm basically going to show you Aleph Prover, short demo, and would be glad if you join our waitlist. We're in the middle of testing it right now. So in a few words about the company, we build alternative AI. We have a team focused on formal verification, and basically Aleph is a sub-product of what we do. We have a very smart team, 6 ICPC medalists, 3 of them actually world champions, 10 PhDs. Jan LeCun is our founding chair. Michael Friedman, a chief mathematician, also awarded with the Fields medalist. So benchmarks. Currently we lead all of them. A few more are gonna be published very soon. Among those benchmarks, I think Putnam benchmark is like the most difficult one, which is the Olympiad for Math Olympiad for students. And what's also important to say maybe, the first 20% of the theorems that we prove are not as complex as the last 20% of them. So the scale grows, the harder the problem it is, the more difficult and the more expensive it is to solve it. The model rankings on the official Lean site also. Right now, Harmonic is actually catching, but we are still leading it. I think they solved 24 problems, if I'm not mistaken. Very soft bench is slightly different benchmark, but also almost 100%. We're probably going to resubmit it again for 97%. And a few more words about Putnam benchmark. So what I wanted to highlight maybe in this slide and a few next ones is the flexibility that you gain if you use Aleph. So most provers, they stack once it doesn't matter which budget you put in, they kind of stack and they loop endlessly. So it's gonna be like a waste of money and a waste of time, which is slightly different from what you can see on this slide. So we basically resubmitted the whole benchmark for giving it a bit more budget. So on this run, we had like $400 budget per problem. We submitted it again with like 1,400, and we solved more problems. Yeah, and this is another representation of that. So average proof time, jumping from 5 hours to 6 hours, utilizing the budget more efficiently or more utilizing more of the budget. And yeah, basically, this is how it looks like. So we are not, there is not specific like point where we kind of just stop proving. The more budget you can put, the more problems you're gonna prove. It has a UI. I will show it. Yeah. So how is it used currently? We have many mathematicians as users, and we're like exploring more in partnership with the universities. It was used in RClib, and basically, like if we get back to RClib and the Ethereum Foundation, basically, Aleph Prover can make pull requests. It can offer, and you can review them, submit. You can, by the way, you can run. If you are not like happy with the result, the proof, you can rerun it. You can ask it to improve or to fix stuff. Specifically about RClib, Alex, if you want, you can elaborate. But basically, we merged. I think it was like 10 PRs, with like in total 7,000 lines. I have a short video of the UI. Hope it's gonna be working. Yeah. So you can select a repository, set up the branch, specify the path to your lin file, the theorem, and basically that's it. You can provide some suggestions. Set up the budget, time, and with some time it's gonna prove it. By the way, we're giving up like grants with credits, so talk to me after the talk. I would be happy to add you. So this is the pull request. I know some of the lemmas are like they have too much details, but yeah. So that's it. Way shorter than other talks, but we'll be happy to talk with each one of you. By the way, I was curious how many of you actually use Lean day to day? So almost everybody, yeah. So please talk to me. We'll be happy to work with you guys. And yeah, this is the QR code to join the waitlist. Thank you. Mm-hmm. This one? No, the other one. Yes. So number 4, there's Aleph Prover again. But so the cost of the proof jumps by almost 3 times from position 4 to 1. Right. But then the limit is only a percentage. Oh, sorry, it's not 1,000. It's 100. Yeah, I was just curious about this number and how it scales. So the harder the problem it is, the more expensive it's to prove it. So yeah, the jump is not linear at all. But yeah, I mean, what's... So the last 150 problems basically reduce the average? Yeah, this is why I said, like, getting it to 100% is like considerably more expensive because the problems are getting harder and harder, and it's... yeah, LLMs are not helping here.
What's you say hard and harder, what's a good measure of complexity or difficulty? Is it field type of question?
This is the measurement, right? Like we are seeing
Yeah, but we can't see the problems we're trying to solve, right? Sorry, because I remember some of the early alpha proofs efforts, but then they just sucked at combinatorics, right?
So, yeah, maybe the way I can answer this, so MATLAB is not full. Yeah. It has many gaps. And sometimes the prover has to prove things which are basically missing in MATLAB. And it gets longer and more expensive. Yeah.
It's a type of question based on like what's in master.
Yeah, this is one of the things. Yeah, definitely, definitely. By the way, we also have a CLI and a cloud skill, so you can use it through the terminal.
So basically, depending on the type of problems, you can say that okay, these are the most common tactics in this field.
Yeah, it will make it cheaper and faster. Yeah.
I'm not sure what these things are trained on. So sometimes I wonder if it was marked and you figured out the answer, or if you just copied a proof that was already published somewhere else.
No, no, no. So we don't disclose fully how it's working. We do use LLMs inside. We also have an AI team in the company building IBMs. Vadim can elaborate on that more. But you can also, there is a feature you can disable web search if you want in the UI. Yeah. I don't hear you. It will be trying to solve it until the soft budget is like reached.
So then is it aware that it won't solve something and cut off that?
No, it will try. It will try to solve it.
Question on the way you interact with the tool. So I guess presume that the theorem or problem that you want to solve has to be specified in Lean, otherwise you wouldn't have like a precise objective function of like when
Yes.
you're done.
Mm-hmm.
Fine. But then the way you give suggestions, can you give suggestions in terms of just Lean or like
No, no, can just whatever English, yeah.
Could also be like, you know, here's a PDF that might contain some useful information.
Yes, yes, you can in the additional instruction you can basically specify files in your repository, like go read this file, go read this MD, and so on.
Okay, and can you like I don't know, suggest also like code-based explorations? Like some questions in combinatorics, I don't know, they might benefit from exploration of finite size, smaller problems. I'm just trying to understand what kind of inputs can you use to kind of push it in a direction you feel like it's useful.
Yeah, you can do it, definitely.
And on the output side, is the output just the Lean proof or some other immediately interpret? Because you said like some of the proofs are long, so maybe I get like a, let's say a positive result. Okay, yeah, I have a proof, but I don't want to understand it. Like, what do I do?
So in the output you have the generated proofs here, like the proof summary. You have the pull request. It's something I ran with Yoichi. And yeah, basically.
So it's like a summary and
yeah.
Give you like a LaTeX thing in between?
No, you generate LaTeX from the Lean.
It's like a separate independent thing you can do.
Yeah, there's also some logs, I think, while it runs that you can observe how it thinks.
Yes, actually, you can see it add new lemmas.
Yeah.
If you stare at this long enough.
And this is.
So another question, let's say you have a theorem and a Lean proof for it. So it's a true theorem and there's a proof. What about finding a better proof? Like, or a proof going through in a different direction? Like maybe there is one, and can you use the tool for finding it?
You can specify it in the additional instructions, yeah, but it might be eventually proving the same proof. So maybe, like, frankly speaking, this is not something we have at the moment. Yeah, but I will talk to the team. Maybe we'll do it in the roadmap. Yeah.
I've known people who did math competitions, and they described them as being like very good training for doing research in terms of being challenging and forcing you to try out different perspectives and so on. But also, what I was told is that it's a big difference between doing math research and these kinds of competitions in terms of problem solving. One thing I was told is like it's kind of like a bounded set of techniques, and maybe you have to be clever in how you apply them. But you learn enough tricks, and then you can do it.
So it's capable on a variety of tasks, not only on math benchmark, but also software verification. The Putnam is just the hardest benchmark among those that we found. We also scored #1 on matharena.ai, which is going to be like published, I guess, within the next few days. There are the easier ones, like mini F2F and so on, will be, yeah. Yeah, it's a very simple one. But I can disclose how we exactly trained it. Yeah.
Do you find it difficult to generalize or to move maybe fields or techniques in math? Like, are the skills that maybe it learns for combinatorics or for Putnam, are you finding that they're pretty readily available in other branches?
Very good question, actually. So we have some IP issues, like doing basically any client that wants everything to be solely for like proven for him. We cannot reuse stuff that we already prove. But it's on the roadmap, but it's rather a legal question. At least this is how I understand it at the moment. But yeah, there's so much things that the prover is capable of proving, and we just cannot reuse it due to legal considerations.
Do you see the capabilities leveling off in any ways, or how optimistic are you on the capabilities for these to be doing research level mathematics?
I'm optimistic about that. It's growing, and it's growing quickly. The speed increases. Yeah. How quickly is it going to be? It's hard for me to say. Yeah.
In relation to this, I see one of yourselves, Aristotle, Axiom, Massing,
Yeah.
whoever else has started a startup. So obviously, the thing is that you have to kind of protect, I suppose, your IP and how your harness is set up and all of this. But obviously, we're getting close to a point where we're able to use it in RClip. We do a lot of productive work with it. Very soon, I think I saw Axiom published some new papers or something. You're going to get new results which are faster than with these tools before anything else. And I remember that from the early days of the four-color theorem being proven. There was a lot of debate in the mathematical community about do we trust a program that is generating this proof by case exhaustion and things like this. And I can foresee questions around like do we trust maybe the proofs, but maybe we want to, for the sake of mathematics, understand how they're generated and what the process is. Have you thought about, obviously you're building your own models, about kind of open weights, open sourcing, more aspects of the harness, of how things work in general, so that mathematicians and photographers and everyone else gets a better sense of how things are working?
So whether we're going to publish a model with open weights, in other words.
How you see, I think, maybe this contributing to science and where that fits within, kind of open science and access to science and things like this, right?
Yeah, well, it's a good question. I'm not sure we have a direct roadmap right now. We are being used by scientists, by mathematicians, and by the open source community. And it's kind of like one of the questions, where do we go from here? Are we making it convenient for day-to-day use, or are we making it more and more capable and smarter? But then it's kind of harder to find clients, right? So it's one of the things we're currently thinking about.
I had a question about kind of the gap between what is given as known mathematical knowledge and what is sort of discovered. So you mentioned MathLib as being lopsided in the way that it provides known facts that can be used for exploration. And so when you are asking a problem that is on the less rich side of MathLib, maybe it struggles a bit more. So Putnam problems typically are like synthetic problems. They are not like interesting math theorems. They're more like some whatever set up to test, to flex some math muscles within about amount of time. So I guess those types of facts don't appear in MATLAB, because why would you have them there, right? So is that the point, that somehow in MATLAB you have like standard theorems of general interest, and Putnam would be the synthetic problems that you don't expect to appear in a place like MATLAB, and this is about bridging the gap using MATLAB type knowledge to reach proofs of the synthetic problems like Putnam, or like huh? Or yeah, but okay, it's marketing, but it's a benchmark. Like I, for example, I find it of limited marketing effect because the.
Oh yeah, it's the same for me.
So I'm wondering, like, how do I, get confidence in the ability to kind of deduce new mathematical knowledge, conditioned on already having all the knowledge in MATLAB.
So, but I mean, so how do we compare then? Is there any?
No, I didn't say I'm offering another. Like, how do I interpret the Putnam benchmark
into real math problems, real world?
Yeah, or I guess the reductionist view is that, in my mind, is like the distribution of Putnam problems to me are not interesting math theorems. Therefore, they don't appear in MATLAB. Therefore, there is a greater than zero gap between the knowledge you're starting from and the knowledge you acquire by solving these problems. Okay, so greater than zero. Good. What else can we take away from there? Or are there other benchmarks that let us sort of infer like a more interesting type of step in acquiring knowledge?
Yeah, so just to repeat, so you're correct, and these benchmarks come to be saturated with powerful models. So everyone needs a new big challenge and new types of benchmarks, and Lean AI is making one of them. But everyone is looking for big challenges to work towards. So you're correct, and the answer, yeah, you must try it and see how it works for your problems. Yeah. So yes, exactly. So that's the only way.
There are occasions of hours or TANSTAL put some secret questions in a secret benchmark set.
So yeah, I will be granting credits. So please try it. Let's see. Maybe you find something. We'll be happy to.
I'd be curious too. But I think as well. So I think something that's come up with all of these is also that there are many interesting questions, which are obviously just derivative of things that are known, and so there are many things that are actually interesting and potentially low-hanging fruit.
Have you guys done any work on the Erdos problems?
The Erdos problem?
Erdos problems, they've been...
oh.
No, okay. Okay, would you see those as like a good next benchmark? I think we also discussed that they are also very different. Some of them are interesting, and the vast majority are super obscure and specialized. Yeah, may not be useful. Yeah. The previous question, and so maybe some few of them are interesting, unsolved. Yeah, but in general.
So just one question, as a user, what about ownership issues? Like, let's say that I submit a proof to an open source library, and then the proof is written by Aleph. Who owns it? And or in a different situation, let's say that some kind of software becomes profitable at some point, and they used results from an AI model. Could you have some leverage on either the open source software or?
Yeah, good question. We're not claiming ownership over the proofs right now. You're basically paying for them by using the...
Okay, so through the subscription, basically, I take ownership of the output of the model.
Yes, right now, yes.
Okay.
It would be very painful if not, right?
I want to comment on the example that was shown. It was not from Putnam. It's actually about RISC-V assembly verification, so not at all Putnam. And then another interesting thing about this code is, this is just one sample, but one thing I observed is this uses a tactic that's a custom tactic for assembly verification that exists only in this repository or not only used in here. So yeah, that's one run block thing. So yeah, this thing can like follow the style of the repo, at least in this example. So like that makes me feel a bit yes. I didn't do anything. I think maybe you can do this. Sorry, that was my
I
suggestion.
didn't give it any additional instructions. If this is your question, just Aleph has access to the repository, to all the files of it, so it's capable of seeing how things look. And but if you get a result which you're not satisfied, you can use the additional instruction and guide it through, like reusing some of the tactics, for example.
Yeah, looking at everything and adjusting itself is a very nice behavior as a contributor. So very welcome, I think.
Just want to say overall, we are interested in feedback. Yeah, so we are interested in feedback. So yesterday we already chatted to like if you had an experience with interactive provers, like other products as well, or AIs in general. So like what are pain points in the workflow? We are eager to hear, and so like the prover, like we try on formal verification benchmarks, and that's also one area where we want to apply it going further. So we don't have a product around that yet, but we're looking for feedback.
Yeah, we are a very early stage company still, so this is why we need your feedback so much. Yeah, there hasn't been yet a public round, even. That's very like the beginning of everything. Cool. Thank you very much.
And then I think that's the end for this room. I think there's some closing remarks of some kind in another room.
You're giving them, so.
Oh, which room? Over there. Over there. There we go.
But it's not. It's
30 minutes or so.
Like 15 minutes.
15 minutes. Okay.
Thanks for organizing.
How did it go?
It was good. Long day. I have to go now. Oh, because the flight. Oh, if my flight is not cancelled tomorrow, I will see you Tuesday. Yes. If my flight is cancelled tomorrow, I will see you the Tuesday after. Right. Well, this has been very good. They called me because I have to get the cab. But yeah, see you on the Google Meets. Yeah. Yeah, I think it was good. In the end, we had obviously met several non-lead people show up and come and listen to the talks and have interesting questions. So I think it was Quant's talk went well. It was a very good talk actually. Even there was some new stuff for me in there as well. So it was good. It was productive. I think it was a good. Yeah, we went to microphone. It was fine. So that all went pretty well actually. It was very smooth. It was good. I think obviously you saw. I mean, even the main conference track had Yoichi talking about lean. So the takeover is slowly happening. I think same. I think ZK Summit as well had another talk that mentioned like we would have formalized in lean. So slowly shifting. I think there'll be a paper like crypto this year where someone like, oh, we would have formalized this in lean or something. It seems inevitable. So I think it was. There's a bit of a turning point. Yeah, and I think it's nice that like the fact that you can do this kind of transmits much faster when people go to conference and they hear about it. So I think that makes quite a big difference. That, like people are gonna same reason for having the like AI people, because then someone's gonna see this and someone's gonna go and try it, and then we'll have faster progress and it'll be good. So yeah, no, it's good. Good day.
You have time to rest. We do 5 minutes of like
Yeah.
thank you.
Perfect.
We will start the thank yous at 5:55 just not to drag.
Yeah, then we finish at 6. The benchmarks are all irrelevant.
Yeah, and they all these problems are quite computational.
Depends a bit on the benchmark.
Putnams are set up with a trapdoor so that if you guess the trapdoor well by virtue of being sufficiently experienced, then you can find like a nice
The IMO stuff is quite similar. It's very much like I mean, it's hard stuff, but a lot of it is like knowing tricks because you need problems that are simple to state but hard, and so a lot of it then gets